Dr. Seema Vinayak. She holds the rank of an outstanding scientist and the position of the director of solid state physics lab in Delhi, which comes under DRDO. And I'm happy to introduce her to this audience. Dr. Vinayak obtained her MSc degree in physics from Punjab University, Chandigarh in 1985 and joined DRDO at Solid State Physics Lab in 1986 as Scientist B. She later obtained MTech and PhD degrees from Department of Physics, IIT Delhi in 1991 and 2007, respectively. And with an illustrious academic and professional career, she rose to the position of Director SSPL on January 1st, 2019. Dr. Vinayak has more than 30 years of experience in indigenous development of high-frequency semiconductor devices and monolithic microwave integrated circuits for strategic applications. And she successfully established several MMIC technologies for production. Her specific areas of expertise include development of group third arsenide and nitride-based high electron mobility transistors and MMIC technologies. And also, she had contributed for MESFET-based 12 to 18 gigahertz MMIC technologies and W-band gallium arsenide and shortwave barrier technologies. She has received several prestigious awards that include getting 2 DRDO Outstanding Teamwork Award for path-breaking research, first in 1999 as a member of the core group working for gallium arsenide-based MMIC technologies, and very recently as a leader of the group working on gallium GaN technology. It's a very prestigious award. She also got DRDO Technology Award in year 1995 for the development of millimeter wave devices, and gold medal for the development of nichrome thin film resistors in 2006. With this short introduction, I invite her to deliver her talk on wide bandgap semiconductor material growth and device processing. The floor is yours, Dr. Vinayak.
Thank you very much, sir. It's wonderful to be introduced by you, and I would like to share with the audience that the position that I hold today was handed down to me by Dr. Sharma himself, and his guidance and his best wishes are always invaluable to me. I'm really thankful to the organizers of this conference to provide me with this opportunity to share the work that we are doing in wide bandgap semiconductors at SSPL with you all. So I will just share my presentation. So, is my content visible?
Well, Dr. Vinayak, it is not seen in full screen. Can you please make it full screen?
Okay.
Because we can see only the part of the presentation.
Okay. Check control. Yeah.
You may press Control L for the full screen mode.
Yeah. Is it okay now? I hope it is okay now. Okay. Okay.
Yes.
Okay. So I'll be talking about on the wide band gap, material growth, and device technology. This is the work that we have achieved at Solid State Physics Laboratory, Delhi. I would just like to say that as the globally the trends are from moving on from the towards the wide band gap semiconductors as a solution for smaller, faster, and more reliable components with higher efficiency than their silicon counterparts. SSPL has taken up work on gallium nitride for high frequency, high power RF applications, and also on silicon carbide for growing substrates for GaN technology. At SSPL, we are involved in algan GaN hemp material growth, device fabrication, all kinds of electrical characterizations, device modeling based on these characterizations, development of a process design kit so that these models can be used to finally design MMICs for different applications. So a typical technology development cycle I would like to share with you is to start with a silicon carbide substrate, which right now we are getting from a commercial source. We do not have an in-house silicon carbide substrate growth facility. And based on these substrates, we then grow algan GaN heterostructure. And then the device technology is developed on commercial as well as on indigenous sources, indigenous wafers. And a typical technology development for a device would mean that you develop all kinds of unit processes, seeing what are the different parameters that each one of them is dependent on, and how we get the best possible for any unit process for a given parameter, and then see how these parameters then interact with each other to be able to give the best device performance. This is a typical cycle, and one continues to do that till one achieves whatever is the best in a particular unit process. Like for MESA isolation, we would look for typically a 40 nanoampere at 100 volts between any two devices. Similarly, all of them, we have a go, no-go criterion for qualifying a process. And this continues till we are able to achieve this. That would mean repeating the process, doing the characterization. SSPL incidentally has a very, very strong characterization group. So you characterize and see how the heating or the metals that you're using are interacting to find out what are the different intermetallics that get created as part of the heating cycles during the process. And you understand that, yes, to be able to use these devices for high power applications, you must have the device design and the process to be able to have a very high breakdown voltage and absolutely minimal leakage current. So we move ahead to see how these can be achieved. And once we are okay, this is just to show that once we are okay, that yes, we have the qualified unit processes, that is the time when we move to volume production. And in volume production, one can see that what one has achieved in the R&D mode is probably not always immediately repeatable in the production environment. And therefore, you have to do certain changes to be able to get what you have been able to achieve in R&D. At the same time, when you are establishing these unit processes, you know that what you have got as a complete, say, in this case, I'm saying a complete current recovery post-passivation may give you an absolutely absolutely a device which cannot be used with a complete collapse of current. And sometimes these things in production happen just because of certain processes, like we see a small residue left here near the gate that can cause a complete current collapse. So the purpose of my sharing this is that when we go from R&D to a concurrent implementation in volume production, this is something which is very, very important for technology development. So what we have achieved in R&Ds, when we take it to production mode, say we run the batches on multiple wafers in production environment, how it helps us is that you can actually see, you can have a lot of data on your own process, on the characterization of these, and based on this data you can actually design or redesign your active and passive components for the circuit, and also model each component of the circuit, each passive and active component of the circuit, to be able to finally achieve circuit design. Based on this kind of a technology development cycle, SSPL today has different discrete HEMTs of different wattages, and we have also achieved a very good control on the front side processing and the backend processing as well at SSPL in this area. These are certain devices that I'm just sharing the images. A single device is delivering 12.5 to 15 watt, and this is a 12 mm device which can deliver up to 50 watts. What I'd like to share here is that the observations that get reinforced during the production, they are the ones that actually aid technology development process. So to be able to actually to be able to achieve perfection or in the technology development, it is extremely important to go for volume production of what you are doing in the R&D level. Here I'm just showing that we may have an optimized passivation, and but when done on wafers coming from different sources, we may have a complete knee walkout showing even for an optimized passivation, and this may require the change in the material growth parameters. And also, if you have this optimized passivation doing on the same set of wafers from the same source, say if it is a commercial source, there also we see this kind of a breakdown, which is very, very low. In that case, one has to realize that you may have a very good material and you may have a strong process, yet you will have to change the design to be able to get a improve the VB off, and that can be corrected with field plates alone. So that means you have to either improve the material, and even if the material is totally improved, you have to change the process, you have to change the device design to be able to get what you require. This I'm just sharing with you how we could simulate the presence of field plates and their implementation in the process changes the electric field at the gate edge. The complete electric field profile can be changed. This is a very strong electric field next to the gate edge, which can result in a very, very low breakdown. And this profile can be changed of the electric field using multiple field plates. This is just showing how the presence of the field plates can actually improve the breakdown voltage. At the same time, you're seeing this blue curve, which is showing that yes, you have achieved something by improving the breakdown voltage, but your FT has really dropped. The same thing we see in the experimental conditions also. These are the devices with multiple field plates, source and gate, and they have been connected to the source in two different ways. This is the source field plate. We're using two source field plates here, a single a gate field and a single source field plate here. And what we see is that without field plate, we are getting the FT of about 16.5 gigahertz. But with the field plate, there is definitely a drop in this. That means you are not letting the device usable at higher frequencies, and therefore this can be improved by using a double source field plate, which we are seeing we are maintaining the FT here. So this field plate implementation in the device provided us with the technology where we could apply a voltage of 20 from 28 volts. We could increase the drain source voltage up to 50 volts, and one can see how the power output from the same device then improves. Without field plate at 28 volts, we are getting 6.7 watt per mm. And the same device for a 50 volt VDS gives us 11.3 watt per mm. Also, this is a slide that I'm sharing from the presentation of a young scientist from our team. This is just to show how the volume production can actually give you so much of insight into how the device design can be changed. Here we are seeing that the temperature is very much high on the drain side of the devices, and therefore it was found that, okay, if this is very high, or if the gate is placed more towards the drain, then it can be even worse. It can be catastrophic and it can lead to this kind of a failure. So this led to some changes in the device design. Also, if in the process you have any residue left in the gate region, this we have been able to image using a CL. You can actually, from the same device that can actually deliver 10 watt per mm, you get these kind of devices on the same wafer, and which is process related. So basically you can go on improving all this from the data that you get from volume production. So using this data, you can have different configurations of the devices on the wafer. You can measure those, and you can use this data to be able to get an appropriate model of these devices and extract the parameters from this, see how good is the model or do changes. And this requires about 160 to say more than 300 measurements on a single device to be able to extract such models. We worked closely with IIT Kanpur, Professor Chauhan's group, to be able to draw such models. At the same time, we also have a team at SSPL who've been able to do modeling for passive and active devices that are being fabricated here. So this is the model that has been created at SSPL for different passive components and the active devices. One, for the designers, they can just pick up the elements from this kit and actually design their circuits. This is important because if you have actually improved your you have almost perfected your front-end processing, the back-end wafer process is very, very critical. That involves the thinning and the dicing track, and also the via hole integration. And a lot of the device performance depends upon your backside performance, backside processing. And here I'm just showing that this is these are two wafers which have been lapped using two different techniques, and how in one case you can actually maintain the current after lapping, and in the other case you see a complete collapse. So this back end, how you are actually lapping your wafer and thinning it down to 100 micron, is affecting the performance of the devices. This is to show that not just lapping, it is also the dicing that can actually change the, at least the GaN based devices are so sensitive to the surface treatments that even the way we thin them and the way we dice them, that can change the results. Right now, I would just like to say here that we are in a position to achieve 28 nanometer, 280 nanometer gates, and form the field plate of the dimension of about 600 nanometer here. We are now in the process of moving to KU band, and therefore these are just technology enablers where we are going down to lower dimensions. However, there is a lot to be done to actually move to KU band, which I'll come to in the end. This, I just want to show that how our devices could show on-wafer X-band performance. And this we have been able to give measure only up to 24 volt, and we've got about 4.5 watt per mm power density on this. At BDS 28 volts, it has delivered 5 watt per mm, 10 gigahertz with at 10 gigahertz with the maximum gain of about 10 dB, and FT of 25.6 gigahertz. This is the wire hole process. So right now the GAN kit that we have is without the via. This is just showing the deep, this is the nickel which is protecting the via on the top, on the back side of the wafer. And this is the via that we have achieved by etching 100 micron of silicon carbide. There are certain issues that we still have to deal with in this area. Now, I would just like to say that this volume production, how we have utilized it to be able to improve the material growth at SSPL. This is the intrinsic carbon doping in these areas. So this is the AlGaN GaN structure that is grown on silicon carbide using MOCVD at SSPL. What the team has done is that they have worked extensively to improve this interface based on a certain inputs that we received from the process teams. Also, they have, this is the channel layer. This is where the 2DG gets formed. And this layer, they have tried their best to be able to minimize the carbon doping in this area. They've done the process optimization to be able to get the best in the aluminum nitride barrier, where this interface they worked on, and also on AlGaN, which I'll just share the results. So carbon, in fact, comes into these structures not by intentional doping, but it is just part of the growth process. And carbon during growth can come from the sources of the growth, like the trimethyl gallium or the ammonia. And here, which position it takes depends upon what kind of a defect it creates in this material. So this is just showing that when the team measured after processing an indigenous wafer, how in one case, this is, I think, indigenous, which is showing something like 37.12 degrees centigrade. It is not shown here, but this was much higher. So what we found that there is a very high heating in devices fabricated on in-house wafers. So that could be because of a bad interface here that is not allowing the heat to dissipate. And this could be improved by improving the growth conditions of the aluminum nitride. And by this, the team has achieved by varying the 5:3 ratio during the growth. And as you increase the component of the ammonia in this, what one sees is that the FWHM reduces, and you have a better interface and a better, and these growth conditions actually are very favorable to the three-dimensional growth conditions. And this, they've been able to see that for certain ammonia concentration, they've been able to achieve this. However, they have also developed these aluminum nitride layers for different thicknesses. For 40 nanometer, it is a completely strained layer. But if we use only a 40 nanometer aluminum nitride, what the team has achieved is that the GaN buffer on top of a very thin aluminum nitride does not have enough resistivity. Therefore, they have chosen about 70, and with the conditions that are favorable for low carbon doping. They have also studied the intrinsic carbon doping with the effect of temperature and the 5:3 ratio. This is just showing that the Cl that you do is very much reflective of the carbon concentration in this. They've kept the thicknesses same of and grown different GAN layers at different conditions of 3:5 ratio and different temperature, 5:3 ratio and different temperatures. These are just showing that a low 5 ratio is giving you a low carbon doping, and a high temperature growth is also responsible for low carbon incorporation in the films.
Dr. Vinayak, I would like to request you to conclude your talk in next 2 to 5 minutes.
Okay, fine. So I would just like to show that by improving these in different areas and using and applying whatever they have done to the GAN channel layer, they've been able to achieve very high mobility and very sharp interface, which can actually give rise to a high 2DG concentration. This interfaces you can see as seen by STEM HADAF, that it is of the dimension of 1 to 1.15 nanometer, and the same kind of improvement in the top ALGAN layer also has given a run-to-run repeatability of a very high 2DG mobility and a very high concentration, 2DG concentration. And with these kind of improvements done on all wafers, so I would like to say that in a batch of say about 5 wafers, if we put 3 of commercial and 2 of our own indigenous, we can actually have this kind of an improvement. And finally, we are very close to what is achievable on a commercial wafer. This is how a feedback from a device and the measurements on the wafer on the device performance has actually resulted in this kind of an improvement. And based on our own PDK, then we have been able to design different power amplifiers. This is based on SSPL GAN kit, and we've also been able to design on this our own 130 watt discrete HEM. These are the different circuits, MMICs, that have been designed in X and C band. In C band, these have been designed for about 40 watt, and in X band from 20 to 30 watt, it is ranging between that. This is what I would like to say, that this is something that we've done in collaboration with the foundry as well as a private partner to be able to get a single device delivering 130 watt. And this was a lot of learning. These have been now delivered to the user. Now we are moving on to wideband TR chip technology. That means to have all the MMICs on a single chip, which is a very difficult technology in itself, and which will be again a big learning, because what we have now will only feed into what we plan to do. There will be a lot. I mean, this is just to show that how much more needs to be done to be actually going to a wideband power amplifier or the TR module technology. It will not just be the same design. Everything else, the material will have to be different. So the complete HEM structure with back barrier, we'll have to design and achieve that. For smaller gates, the ALGAN thickness will change, and we'll have to work on our ohmic contacts again to be able to get lower RC values, and the feed plate technology will have to be simulated and implemented again. At the same time, I would like to say that we are trying to indigenize the silicon carbide growth, so that in this area of wide band gap, we have a total self-reliance. There are miles to go before one sleeps, so there's a lot to be done yet. I would just like to share that this is our material team who has worked on the material improvisation, And this is the complete design, fabrication, and measurement team. Thank you very much.
Thank you, Dr. Vinayak, for comprehensive description of the work being done at SSPL and the technologies from material to devices being evolved and transferred. There is a time not for any question, but I would still feel that if there is one question we can entertain here. Okay, I think since there are no questions, I had several, but I can ask SSPL in private. Thank you very much for a very comprehensive talk, and all the best.
Sir. Thank you very much, sir. So, how do I stop this?
So our next speaker in this session is Dr. Ashutosh Kumar, who is a scientist at Rice Research Institute of Sweden since October 2020. Very recently, he joined there. His research is focused on exploring 3-5 semiconductor materials and devices at varying dimensions, ranging from bulk to atomic scale for various technological applications. And before joining RICE, he was a postdoctoral fellow at National Institute of Material Science, Japan, where he worked towards development of gallium nitride-based devices with leading companies like Fuji and Sony for high power and solid-state lighting applications. His current research interest at RICE involves growth and processing of 3-5 materials, followed by device fabrication as well as characterization. Dr. Kumar earned his doctorate degree in semiconductor physics from Indian Institute of Technology, Delhi in 2016. And during his doctoral studies itself, he was awarded with prestigious DAAD fellowship under German Academic Exchange Service to work on gallium nitride nanostructures at Max Planck Institute for Science of Light, Germany, for a period of 6 months. Until now, he has contributed to various research projects on nitride semiconductors, which mainly include electrical transport at metal gallium nitride interfaces, low frequency noise characterization, gallium nitride nanostructures, graphene gallium nitride interfaces, microstructural and atomic scale investigations of defects, and so on. I have pleasure to invite Dr. Ashutosh Kumar to deliver his talk on atomic scale investigations of defects and dopants in gallium nitride. The floor is open, Dr. Kumar, to you.
Hello.
Yes, please.
Hi, am I audible, Dr. Sharma?
Yes, please.
Okay, and can you see like full screen? Just wait a minute. Not yet.
Not yet.
Okay, just wait. So, can you see now the full screen?
No.
I don't know. Actually, I'm not been used to this. Just wait a minute.
You may try opening the presentations first and then sharing it and then going to full screen later.
Yeah. Okay. Just wait a minute. Just something weird. So share is screen. Okay. Oh, I should be setting here. So is it okay now? Hello.
It's fine. Go ahead.
Okay. Yeah. So thanks a lot, Dr. Sharma, for the kind introduction. So in fact, before starting my talk, I would like to thank the organizers, Professor Khare, the convener, Dr. Professor Rajendra Singh, and the other organizers. In fact, I did my PhD with Professor Rajendra Singh, and Professor Vikram Kumar from IIT Delhi. So it's just like a home for me. So thank you very much. So as Dr. Vinayak has already told about the technological advances in the field of gallium nitride and what the SSPL is doing towards developing AlGaN GaN based power amps. So my talk is basically addressing some basic issues in the gallium nitride, let's say defects and dopants, and what they do, how you characterize them, and with some advanced combinations, let's say atom probe tomography, which we haven't heard much of. So myself, like just this October 2020, I joined RISE, Research Institute of Sweden, where I'm working on the growth and the devices, and we have collaborating with the printed electronic group, so targeting for packaging also. So what I'm going to present here is my postdoctoral work at NIMS Japan, which was in collaboration with the Fuji Electric and Sony for addressing the defects in magnesium implanted gallium nitride layer. So I can just make my pointer. So the outline of talk, my talk is just the basic introduction about gallium nitride, and I would be majorly focusing on the p-type defects and dopants analysis in magnesium implanted GaN layers, completely on the freestanding GaN substrate. So we are not looking on the silicon sapphire or the silicon carbide. And other work is, can you give a direct evidence of magnesium diffusing along a threading dislocation? Because this is believed to be one of the major cause of device leakage, especially in the vertical devices. In just couple of slides, like what we are targeting at RISE. So why do we need gallium nitride? Although Dr. Vinayak has shown a lot of device development, but all the devices like we are using right now, our laptops, computer, they are being enabled by silicon. And if you see this, the curve between demand and the innovation, the computing and the communication are getting merged up. It means that you want your computers for the communication and you want your mobiles for the computing. So the idea is every device should communicate and compute, and silicon has served us for like 50 years in this, more than 50 years, but now it has some fundamental challenges, which is like it has the limitation in the power electronics. So because of the band gap, which varies as the which is proportional to the breakdown field, you can't do much of the band gap engineering, and being an indirect band gap, you have to you have to look for the separate materials for the lighting applications. So gallium nitride offers a solution to these problems, and I'm not going all into all those typical gallium nitride properties and everything. Just one thing, I'm directly switching to the p-type, because if you look of any modern device, like most of the device have this PN junction as a building block. Either you look as a vertical PN diode or a PN junction based LEDs, but the p-type doping in the gallium nitride has been a major issue. So that's why I'm showing this curve from 1998, which says that achieving a reasonable amount of the whole concentration in the gallium nitride is pretty tricky, because of the fact that prior to any sort of doping, unintentionally doped gallium nitride is n-type. We have tried a lot of dopants, but now magnesium is a proven technological dopant in the gallium nitride, but it has a ionization energy of about 200 MeV. So you have to put a significant amount of magnesium to get a reasonable amount of holes. But what happens that if you start putting more than 1090, something like 5E19, the whole concentration starts dropping out, and it is believed that like magnesium starts forming defects in the gallium nitride, although it has inherent defects, but this magnesium starts interacting with those defects, and the whole density starts dropping out. There's like the formation of the magnesium precipitates. Ideally what you want your magnesium to go into the gallium nitride lattice and replace the gallium atom on the substitutional sites. Only then it can give you the p-type conductivity. But what happens that it is maybe starts going to the interstitial site or starts forming precipitates which are proven to be electrically inactive. So these are the issues in the case of the p-type doping in the gallium nitride. Then the another issue is how do you incorporate magnesium? The one way is like epitaxial doping with the MOCVD or MB. But if you want to target gallium nitride for the commercialization, vertical PN diodes, we have to look for the ion implantation and bring the technology as close as possible to the silicon. But when you try to put magnesium via ion implantation, the one issue you have to address is the damage. Um, it creates a lot of damage, and then you have to do a high temperature annealing step in order to activate magnesium. So when I say activation, it means that the magnesium should go to the gallium substitution sites and give you the reasonable amount of the acceptors. So there are a lot of reports available on the defects characterization, electrical characterization of magnesium doped gallium nitride. But the question is, can we extend the findings of the magnesium doped gallium nitride to the magnesium implanted gallium nitride? Because there are like lot of reports on magnesium doped GaN, but not very much reports on the magnesium implanted GaN, especially the characterization of the defects. So the first study we tried to do was just to compare the magnesium doped gallium nitride with the magnesium implanted gallium nitride. So we started with the same kind of structure like freestanding GaN substrate on the top of this MOCVD grown gallium nitride and on the top of this magnesium doped GaN, and we did the STEM measurement. This is the same profile of the magnesium. We haven't seen any big kind of like those defects, but when we did the same thing on the same substrate and put magnesium via ion implantation, we started seeing a lot of defects, and the concentration of these defects was directly correspondent to the concentration of magnesium. So it means that the first thing, the defect dynamics or the nature of the defects is completely different if you compare the magnesium doped gallium nitride with the magnesium implanted gallium nitride. Secondly, is the concentration of the magnesium linked with the concentration of defects. So these defects may have the magnesium in them, and how can you do the quantitative estimation of the magnesium in them? And this is like the one typical high resolution image of one of such triangular pyramid. So how can we quantify the amount of magnesium in such kind of structures? So let's say we pick one of those defects. The one typical way of doing it to do this STEM EDS, energy spectroscopy, which is the chemical analysis of the elements. So we did the STEM measurement at two positions, let's say out of the defect and one at the defect. At the defect, we could see a slight signature of the magnesium, but this magnesium peak lies very close to the gallium tail, and when we did the EDS mapping on such kind of defects, we could see a signature of the magnesium. But quantifying magnesium via EDS STEM is difficult. You have to be very careful, because let's look at these numbers. If you are putting 1E19 of magnesium via ion implantation or doping, it corresponds to the 0.01 atomic percentage of magnesium, and EDS gives you the atomic percentage. It means that, and this is the kind of the limit, or maybe 5E19 that we tend to put into the magnesium. So it means that if you are putting one order higher, let's say 20, still it corresponds to the 0.1 atomic percentage of magnesium. And here we are already hitting the limit of the EDS STEM measurement. So it means that if you have a very tiny magnesium clusters, or having even 1020 or 1021, it's very difficult to detect them with the STEM EDS spectroscopy. So you have to be very careful if you want to detect magnesium via any such technique. So with this, what we try to do, like in the case of magnesium implanted GaN, what are the conditions of formation of those defects? Can we estimate the amount of magnesium in those defects? What are their microstructures, and how do the magnesium distribute inside the gallium nitride matrix? So this is how we studied our material system. We designed two studies, starting with the freestanding GAN, MOCV degrown GAN, and put magnesium via ion implantation. In one case, we varied the amount of the magnesium, annealed them at the same temperature. In the second case, we fixed the amount of the magnesium and varied the annealing temperature and tried to see the evolution of the defects and their characterization using STEM, which is scanning transmission electron microscopy, and atom probe tomography, which is a powerful combination that we have seen for analyzing defects and their atomic scale characterization. So this is what I'm going to talk about first, is when you varied the amount of the magnesium. So this is the structure where we started by putting different amount of the magnesium, 17, 18, 19, annealed at 1300 degrees centigrade. So this is the SIMS profile where you can see the box kind of implantation in 500 nanometer deep, so 17, 18, 19, and then those are the STEM images. So as you can see, as you increase the amount of the magnesium, we see the number of the defects were increasing. So let's say here, but our question was that whether they contain the magnesium or not. Secondly, STEM can only tell you that they are clusters, but are they the vacancy clusters or are they the magnesium clusters, and what are those loop kind of features? So those kind of things we try to address with the atom probe tomography. So in the case of atom probe tomography, we prepared our specimen in the form of needle to get the high evaporation field. So this is how we started. Like we with the FIB focused ion beam, we pick our one specimen like this and then put it on a silicon coupon and then cut those in those coupons and then do the annular milling to convert that structure in the form of a needle. And then we place that needle under the high voltage, under the influence of a laser pulse on the basis of field ion microscopy. So this high voltage under the laser pulse starts evaporating the material atom by atom, and they goes to a position sensitive detector which detects their XY position, and this time of flight is linked to their mass. So by recording X and Y and the time of flight, we can essentially reconstruct the whole of your material using atom probe tomography. So this is what we did. So when you analyze the same specimen 17, 18, 19, we can see that in the case of magnesium 18 and yield at 1300 degrees centigrade, we haven't seen any of those magnesium clusters. But in the case of 1E19, we started showing all those clusters. So if you go back to all those STEM images, it means that all those tiny clusters we were saying, those are not the magnesium clusters, they are the vacancy clusters. And all those loops we are seeing, they are basically the magnesium enriched loops. So this is the way how you can differentiate between the vacancy clusters and the magnesium clusters, and you do not have such type of clusters at 1E18 and annealed at 1300 degrees centigrade. So from STEM and APT, we can basically differentiate between the vacancy clusters, magnesium clusters, and the magnesium clusters and loops start appearing at 1E19 at 1300 degrees centigrade. But our question was that even if we kept the magnesium concentration same and annealed at a lower temperature, can they form? So it means that we designed another study where we put the same amount of magnesium and annealed at 5 different temperatures between 1000 and 1300 degrees centigrade. And this is the SIMS profile where we can see a significant variation in the amount of magnesium with the annealing temperature. And when we started doing the STEM measurement on them, we could see that the defect density starts decreasing with increase in the annealing temperature. It means that as you increase the annealing temperature, those kind of vacancy clusters starts agglomerating, and few of them may be the magnesium clusters, but STEM doesn't tell you like whether they are the vacancy clusters or the magnesium clusters. So again, for that we did the atom probe tomography. So in the case of non-annealed and 1000 degrees centigrade, we haven't seen any such kind of the precipitate of magnesium. As we go to the 1100 degrees centigrade, we started seeing very tiny clusters which are more evident at 1200 degrees centigrade and 1300 degrees centigrade, we could see the magnesium clusters as well as the magnesium enriched loop. So this is how the evolution of the magnesium. So probably what happens, like magnesium starts interacting with those vacancy clusters which were kind of agglomerated by increasing the annealing temperature, and they offers a site to the magnesium to get attached, and then the formation of the magnesium clusters. So this is just like, we don't need to go into the detail of this. We did a frequency distribution analysis just to confirm that whether the magnesium is uniformly distributed or not, just dividing the whole analyzed volume into the blocks of 500 atoms, and then comparing the distribution of the magnesium to the binomial distribution, which is assumed to be random. And what we found the same thing. At 1100 degrees centigrade, this deviation starts deviating from the binomial distribution, which confirms that the magnesium clusters starts to form. So we analyze the amount of the magnesium in the background as well as within each individual cluster. What we found that when there was no magnesium clustering as expected, the amount of the magnesium was same as the background. Once clusters starts form, the magnesium in the background starts decreasing. But when we estimate the amount of magnesium within each clusters, it starts to increase as the clusters are getting bigger and bigger and eating more and more magnesium. So when we talk about those specific loops, we did the line profiling along a single loop. What was interesting that those loops was having about two to three orders of higher magnesium as compared to implanted amount of the magnesium. So they are super rich in magnesium. Second, we could see that the amount of the magnesium which was increasing along a cluster was kind of corresponding to the decrease of the gallium. It means that on these particular clusters, we can see the single atomic replacement of the gallium by the magnesium atoms. So the question was that when this gallium is getting replaced by the magnesium, does it lead to the formation of another phase? So that we tried to investigate with the nano beam electron diffraction. What we did, we magnify one loop. This is a high resolution magnification image, STM image of one such loop, and we did the nano beam electron diffraction at 4 positions, the 3 at the loops and 1 away from the loop. The idea was that this B4 and this B1, B2 and B3, B4 corresponds to purely GAN, and this is B1, B2, B3. So if there is a formation of any other crystalline structure, we should see another diffraction spots, but we haven't seen any diffraction spots. It means that this replacement of gallium by the magnesium at the loops does not lead to the formation of another crystal structure. And other than the loops, we have those dumbbell-like shapes, such kind of elongated structures. So we magnify one of them and did the inverse Fourier transform analysis just to see like what are those kind of structures, and when they form inside a lattice, what happens in the lattice. So this is like by doing inverse FFT, one corresponds to each atomic planes, and we evaluate the atomic separation. What we found that there's a slight expansion of the lattice, which means that when the magnesium, which is bigger than the gallium 3 plus, incorporates into a lattice, it tends to expand. So these structures are basically very tiny magnesium clusters. So with this, I'm just kind of coming to the end of that. So with the STEM and APT, we found that both magnesium level and annealing condition affects the magnesium segregation. You cannot say like one affects. So the formation of defects and those kind of loops, for example, if you say 1E18 and anneal at 1300 degrees centigrade, they're like no formation of the magnesium precipitate. But if you put 1E19 and anneal at 1100 degrees centigrade, the formation of the precipitate starts. So this is what I said. And so we could see the loops at 1E19 1300 degrees centigrade, and we could confirm the atomic scale replacement of gallium by magnesium at those loops. And there's a direct evidence of lattice expansion. And there's like one another problem that we try to address just in a couple of slides, like magnesium pipe diffusion. So in a typical vertical GaN device, you have a drift layer and you have a top p GaN layer. What we want magnesium to remain within this layer, but it is believed that magnesium tend to diffuse along this layer inside the GaN layer, but there is no direct evidence. And what is the path of such kind of diffusion? So we tend to investigate that. So this was our structure, like 500 nanometer NGAN and then NGAN substrate. So first we confirm that whether the magnesium is really diffusing into these layers or not. So for that, what we did a slanted cut. So with the help of the slanted cut, let's say this width was only 4 micron, but if you cut it like this, you can increase it to 40 micron. So, and then we did the cross-sectional CL observation on such kind of the slanted specimen. The idea was that the magnesium appearance is linked to the DAP emission. So if you are seeing any DAP emission, it means that in those regions we have the magnesium. And surprisingly, what we found, that we found the DAP emission both from this layer and even from the substrate. It means that the magnesium tend to diffuse all the way up to the substrate. And what is the path of that? So we believe that the path of such kind of diffusion could be those threading dislocations. So we try to confirm that. So this is the again the starting layer, and then we did a slanted cross section. And so we believe that if we remove the P layer, we should see those hexagonal pits, and those hexagonal pits are kind of formed. So we expect one threading dislocation under each hexagonal pits. So this is like one of those pits, and we selectively pick 3 of those pits and try to confirm that whether there is a threading dislocation under those pits or not. And what we found, that we found the threading dislocation under each of these pits. And then with atom probe we kind of confirm that yes, there is a magnesium diffusing along a single threading dislocation. And in this region we expect a magnesium of about 10E18, but it was about 10E21. So like about 2 or 3 orders of magnesium going in the regions where we don't want the magnesium. So with this, I come to the end of my talk. Like with FIB, STEM, and APT, we can figure out like what is the magnesium clustering and what are the conditions of the formation of those magnesium clusters. We can differentiate between the vacancy clusters and the magnesium clusters, and no other combination would address such kind of issues. We can quantitatively estimate the amount of magnesium within a single defect, let it say loop or the magnesium clusters. And there's a direct evidence of atomic scale replacement of gallium by magnesium at those kind of loops. And we can give a direct evidence of magnesium diffusing along a threading dislocation. So with this combination, let's say you have a atom probe tomography STEM image, you couple with the STEM, and you can confirm like what are those defects. The more about those defects are is given in this book, which is the AIP book, which is recently published, and I have written a chapter in it on the APT and STEM, where you could also see how this combination can be applied to the InGAN-GAN multiple quantum wells. So this is what I did at NIMS. Then I moved to the RISE Sweden. So this is the research institute in the Sweden, and we are basically working on a facility called the Pro Nano and targeting 3.5 nano structures for various applications, just like power, LED technology, and here we are looking for the deep AlGaN based LEDs, which are kindly supposed to be good for killing viruses, bacteria, and all those things, and also for the bio sensors. So thanks a lot. Yeah, thank you very much.
Thank you, Dr. Ashutosh Kumar, for an excellent talk.
Yep.
And it's an excellent work combining STEM and atom probe. I couldn't see any questions in the chat box, but if there are any questions by any of the participants, it is welcome. Okay, I think I have one question. That
Yep.
during ion implantation, you expect all sorts of defects to form, like, both gallium vacancies, nitrogen vacancies, and gallium interstitials, nitrogen interstitials, etc. why
Yeah.
only the vacancy clusters are expected?
Yep, because actually what we expect that since all of those magnesium, when we put the magnesium via ion implantation and it starts annealing them. So with the positron annihilation spectroscopy, we have also seen that because of those thermal subjection, those vacancies starts agglomerated and forms the vacancy clusters. So those vacancy clusters are essentially formed of the nitrogen vacancies, the gallium and all those things, but they are in the form of the clusters. So because of the agglomeration, and yes, there are the point defects which could be the gallium vacancy or the nitrogen vacancies, but with even with the TAM and STEM, we cannot target all those individual point defects. We could always see the clusters because they kind of induce the strain, and strain is what we see in the TM. So
Oh, thank you very much for an excellent talk. All the best.
yeah, thank you very much, sir.
So it's my pleasure now to invite Dr. Alison Mattioli, who is an assistant professor in the Institute of Electrical Engineering at Ecole Polytechnique, EPFL, since 2015. He received a BSc degree in applied physics and applied mathematics from Ecole Polytechnique, followed by a PhD degree from the Materials Department of University of California, Santa Barbara, in 2010. He was a postdoctoral fellow in the EECS department at the Massachusetts MIT until 2014, and he has received the UCSB Outstanding Graduate Student Scientific Achievement Award for his PhD work in the 2013 IEEE George Smith Award, the 2015 ERC Starting Grant Award, the 2016 SNSF Assistant Professor Energy Grant Award, and the 2020 University 2020 University Lexus Prize. This brief introduction, I invite Professor Mattioli to deliver his talk on towards the limits of gallium nitride electronics from efficient power electronics to efficient thermal management. The floor is open, Professor Mattioli.
Thank you. Thank you very much for the. Thank you very much for the introduction. You can see my screen before I start. I don't know if I.
Yes, we can. We can.
Presentation mode.
Perfect.
I hope so. So thank you very much. I would like to thank the entire committee for having invited me, Professor Rajendra Singh as well, in particular. And today I'd like to discuss a bit of our results on going towards the limits of gallium nitride electronics. And the main motivation for this work is the huge losses in power conversion. So for example, you take your laptop, the laptop needs only 60 watts to turn on, but you actually need to provide 86 watts, and the difference go in losses. And actually, most of these losses are related to power devices, both in non-states and switching. You have some losses also in the passive components. So the main goal is to reduce these losses. Another main goal is in the power density of these power converters. So if we look at computational power from the 80s to 2012, we see a massive increase in computational power, but we didn't see nearly as much for power converters. So basically, we only see a factor of 14 in their power density. And what are the limitations? If we look at a typical power converter, what we see here is very large components. We see large heat sinks. We see large magnetic components, transformers, and inductors. And we see large capacitors. So if you want to increase the power density, we need to reduce all of these components. And to do so, we need to improve the efficiency of the device themselves. so we can reduce their size and their losses. We need to increase the switching frequency so we can reduce the size of inductors and capacitors. And we need to enhance the thermal management so we can also eliminate these bulky heat sinks. And that kind of sets the goals that I will present in this talk. And here, gallium nitride is an exceptional material. I don't think I need to convince anyone in this session. It's already changing the world with LED lighting, and its properties can make a significant impact in power electronics and wireless communications. The main point is that all of the properties of gallium nitride enables them to switch really fast to block large voltages in a very small footprint and do that with a high efficiency. That's the main point that these materials enable. And another thing about gallium nitride, especially GaN on silicon, is that this is a lateral device. So what this enables is for us now to integrate power devices on the same chip. By doing this, we not only get a larger power density, but we also can switch at much faster switching speeds. We can go to tens of megahertz of switching speeds. But what's the challenge? What are the problems? So if we look at a device level, despite the fact that gallium nitride offers a very nice potential, when you see the device published in the literature and offered by companies, we see a huge distance between, or a huge gap between what we are today, where we are today, and where we should be. So if we want to get to the limits of GaN, we do need to increase the breakdown voltage and reduce the own resistance. And in addition, we do need to reach normally off operation. This is extremely important for power devices. So we need to have a positive threshold voltage while having a small R1. We need to have a high current density while having a positive threshold voltage. All of this must be provided in the same device. So our goal here and the outline of this talk is to discuss about technologies to increase the breakdown voltage, to reach normally off operation, to achieve ultra low ohm resistance, and to provide an effective thermal management. So let's start with the first one. And our approach is to use nanostructures for high voltage operation. So the idea when I talk about nanostructures is to pattern nanoscale patterns on some specific regions of the device. For example, we can pattern nano trenches, and by nano I mean anywhere between hundreds of nanometers to tens of nanometers. So it's a general term. So if we pattern these trenches in a specific region of the gate of a transistor, after depositing the metal, we actually form this tri-gate structure. The idea is that you have the top gate, but you also have two side gates. So you can control much better the two-dimensional electron gas in this kind of structures. But what it does that's extremely important is that it enables us to design the threshold voltage. So this region provides a smaller threshold voltage than the rest of the gate. And this threshold voltage can be controlled by the size of the structure. So if you make it smaller and smaller, you go towards zero threshold voltage, regardless if you have an oxide or without an oxide. And the main point of having two different threshold voltages is that, in this one being smaller, is that you convert the rest of the gate into a field plate. If you do that, what we observe is a much larger breakdown voltage of the tri-gate device compared to a planar device, while the ohm resistance is completely the same, despite the fact that you're actually etching these trenches under the gate. So we don't lose anything in R1, we gain quite a bit in breakdown voltage. And our question was, well, this is something that has been of interest for many groups in the past, from MIT, HQST, Hokkaido University, and others. But our interest was, how can we actually design these things for high voltage operation? So let's understand what the problem is. So first, if we take an electrode device, the main issue is that the electric field is highly inhomogeneous. So when you're blocking high voltages, there's a peak of the electric field right at the edge of the gate. And typically the gate breaks here. Then you can include a field plate, which is basically another transistor with a higher, a more negative threshold voltage. So by doing that, you actually create, or you split this peak into two. So you have a higher breakdown voltage. You can keep going. You can include another field plate. You have three peaks, larger breakdown voltage. But the ultimate configuration of this should be a slanted field plate. So you basically have an indefinitely number of transistors with different threshold voltages. So you can have a homogeneous field under this region. And this is the concept of a vertical slanted field plate. It has demonstrated in the past. It works quite well, but it's extremely challenging to make. It's very, very difficult to make an angled oxide with typical clean room tools. And also you're very limited on the design of the angle that it can do. So you can only have very, very shallow angles. So here we borrow this concept to demonstrate the concept of slanted tri-gate. So the idea is quite similar, except that it's in a lateral fashion now. So if we take a planar device and introduce a tri-gate region, we are creating two regions of two different threshold voltages. So we split the peak into two of the electric field. And we can keep going. We can change the width of the tri-gate and create three different regions, so three different peaks. But the ultimate configuration would be one where we change the angle in a very linear fashion. So we have this slanted tri-gate. And the idea is that it can hold now a homogeneous electric field under this region. The advantage compared to a vertical slanted field plate is that now this can be engineered in a single lithographic process. And you can actually have the angle that you wish for. So it improves the design, and it improves a lot the complexity of this process. So here I'd like to show three different results. So it's a planar device, tri-gate device, and a slanted tri-gate. You can see the slanted angles here. And what we observed is that the breakdown voltage for a planar device was at about 900 volts. When we introduced the tri-gates, we improved that to 1100 volts. And by introducing the slanted tri-gate, we went to 1400 volts. We're not doing anything else. The devices are all the same in the same chip. All we are doing is actually changing the design of the tri-gates. So we basically got an increase in 500 volts in breakdown voltage. Or another way of looking is we reduced the size of the device by 5 microns. So we reached the breakdown voltage of a 15 micron LDD with only 10 microns. So we basically improve this R1 times A figure of merit, which is quite important to reduce the size of the device. So if you look at this, what we're doing is basically going towards a higher breakdown voltage without really degrading the ohm resistance. So it's a very promising way to push for higher voltages in lateral devices. And as a matter of fact, this can be applied to any lateral device. So if we take the case of Schottky diodes is actually much more sensitive to high electric fields right at the anode region. So that's why typically Schottky diodes have lower breakdown voltage than transistors. But what we can do is, by including a tri-gate in a slanted tri-gate region, we can now design the electric field at the anode. So you can see that basically you can design the potential playing with the threshold voltage of each one of these regions. And as a matter of fact, the threshold voltage of this tri-gate region is going to fix the voltage that the anode sees. So as a consequence, we're going to have a very flat leakage that depends on the width of the tri-gate. So basically, by changing the tri-gate width, you change the threshold voltage and you change exponentially the leakage current. So this also enables us to design the kind of leakage that we would like to have. So we show this device, they have a breakdown voltage above 2 kilovolts for Schottky diode. That's quite amazing. The on performance is quite nice. You can see here the point that I was making. The leakage current is basically flat for very large voltages above 650 volts, completely flat leakage. And then it starts increasing. And we can start having this high breakdown voltage devices for Schottky diodes as well. It's a quite promising way of achieving high voltages. So second topic is how can you get normally off operation? And here, the first idea that we worked on is a combination of tri-gates and gate recess. So the idea is that you have a gate recess. If you only have a gate recess, you need to recess quite a long region to have a good threshold voltage. But when you combine with tri-gates, this combination allows us to go to higher threshold voltages with a much thinner recess length. So you can observe here the gain in threshold voltage. So if we go from a planar device to a recessed planar to a recessed tri-gate planar, so we reach very nice positive threshold voltage, so good normally on, normally off device. This device also presented very large breakdown voltages of 2 kilovolts, and you see a nice current density and on resistance that's actually comparable to the D-mode device. So we have an E-mode device that has a comparable resistance of the D-mode device. So you basically didn't lose anything in terms of on resistance. So this shows that by combining these techniques, we can now start having higher current and higher threshold voltage together with the low on resistance and together with the high breakdown voltage. It's actually really hard to get all of these elements in the same device, but this combination of tri-gates and gate recess, for example, is one possible way. But we can go much further. Up to now, we've been talking about these tri-gates of hundreds of nanometers, but we can actually go for very, very tiny dimensions, so below 40 nanometers, all the way to 15 nanometers. So you're actually forming a nanowire under the gate. And just by doing that, you can completely deplete the 2DAG in each one of the wires. So you can push the threshold voltage towards positive values. But actually, you can see that the value is not that positive. So it's near zero. So it's not a real E-mode device. But then what we've done is to replace nickel by a large work function metal, like platinum. And we see a shift in threshold voltage. And this shift occurred for all of these different tri-gate widths. And the shift corresponds exactly to the difference in work function between platinum and nickel. So this enables us to really push a bit more the threshold voltage towards positive values. So this device presented very similar on resistance and current levels as the D-mode counterpart, so the planar device. So we don't see any degradation in the device, despite the fact that we are actually etching 15 nanometer wires and under the gate. And the reason for this is that now not only we have the 2DAG, but after we apply enough positive bias, we actually form an accumulation at the sidewalls. So you can see here in the transconductance a peak of the 2DAG and a second peak corresponding to the accumulation on the sidewall. So that compensates for the etching of these nanowires. And this device presented also very nice breakdown voltage, 1.4 kilovolts. So it shows that we can use these nanowires for a high voltage operation. And finally, I would like to show a concept that we just demonstrated recently, which is the combination of PGAN and tri-gates to form MOS transistors. The idea here is that if you, by combining a PGAN to a HEMT, we can actually lift the band structure on the 2DAG, so you can deplete that region. And what we are going to show here is that by combining the tri-gate, we can actually reduce the length necessary of the pGaN. Short pGaN is actually a necessary thing. So we've done an experiment here where we have a gated Hall on a pGaN wafer. And what we notice is that if you look at the sheet resistance, even if you apply a very large bias, we never really decrease the sheet resistance to the value of a standard GaN HEMT. So that means that that pGaN region is always more resistive than the standard GaN HEMT. So we do need to reduce that region as much as possible if we want to reduce the ion resistance. So what we've done is that if we combine the pGaN with tri-gates, what we see is that we can get another a lift of the conduction band above the Fermi level. So we completely deplete that region, so we can reach normally off operation. So we demonstrated this device. You can see very nice normally off behavior, good threshold voltage, a good gate stability. And now, unlike typical pGaN devices, we can now apply gate biases of 8 volts and the gate doesn't turn on. So this is not a gate injected device. It's actually an MOS device. And what you can see is we can reach very nice current densities, above 500 milliamps per millimeter, nice RON performance. So this device, the main point is that the pGaN MOS tri-gate, the threshold voltage is much less sensitive to the pGaN length compared to a planar pGaN. So what this enables us to do is, if we want to have a threshold voltage with a pGaN tri-gate device, so the same one with a typical pGaN MOS, a pGaN planar device, it means that we need to have a pGaN length that's 1 micron instead of only 100 nanometers for the pGaN tri-gate. And that means that now we increase the resistance from below 9 ohm millimeter to 11 ohm millimeter. So you do pay quite a bit in ohm resistance by doing this. So this device can actually switch really fast. And the reason is that now the pGaN is not doing any, so the top gate's not doing any control over the channels, just lifting the band. So all the control comes from the sides of this tri-gate structure. So we can have very nice, very high switching frequencies. Breakdown voltage is also very high, so we can reach the limit of the buffer that we used in this case. So this is a promising way to have fast switching and to prevent the gate injection by typical pGaN devices. All right, so up to now we've been talking about ways to increase the breakdown voltage, but we still see that we're really far from the limit of GaN. And if we do want to reach this kind of limit, we do need to reduce significantly the ohm resistance. So how to do that? Here we proposed the concept of multi-channels for ultra-low resistance in power devices. So if you look at the challenges in reducing the ohm resistance, there's a common trade-off. So between the carrier density and the mobility. So if we increase the carrier density, you lose in mobility, and the sheet resistance is about the same. So for all GaN, it's about 400 ohms square, I mean, give or take. If you change the barrier, you can gain a little bit to indium aluminum nitride or aluminum nitride, but the trade-off is always the same. If you increase the carrier density, you lose in mobility. So to solve this trade-off, we propose to stack multiple two-dimensional gases in the same device. So you can form 2 decks embedded inside the device. So we can completely increase the carrier density independently from the mobility. You can break this trade-off. But actually here, this technology comprises 3 different aspects. So one is the multi-channel. The second one is how to control these multi-channels. And here is the use of tri-gates. And the third one is how to hold large voltages, which is the use of slanted termination. So I'm going to show all of them. So as I mentioned before, if we use the same kind of all-GaN barrier where we're limited by 400 ohms square, we now make a 4-channel device. We see an increase in 4 times in carrier density with basically the same mobility. So you can reach now 82 ohms square, so almost 4 E13 per centimeter square carrier density, and almost 2,000 centimeter square volts second of mobility. So it's a huge increase in sheet resistance, or reduction in sheet resistance. And actually, this is valid if you compare to other barriers as well. So here's indium aluminum nitride and aluminum nitride. So it does allow us to go much beyond this the level of sheet resistance from compared to other barriers. The main problem is that just having a low sheet resistance is not enough if you cannot control these channels. For example, you take a typical device, multi-channel device, and you put a planar gate. The device stays always on, even if you apply minus 40 volts to the gate. Actually, the gate breaks before the device turns off. So it's a useless device. And here is where combining tri-gates offers a very nice solution, because now you can control all the multiple channels simultaneously from the sides. So you can have a very nice on and off with a very low threshold voltage. So here we showed how we can actually design the width of these fins to completely change the threshold voltage of the device. And an interesting thing is that if you take large widths, we actually observe the different peaks of the different channels being turned off at different voltages. But as you reduce the size of these wires, all of these peaks merge into a single one. So all of the channels are being controlled simultaneously. This is extremely important for the device. So we actually made this device. You can reduce the size of this gate region to even reach normally off operation. So you get a very nice threshold voltage and extremely large current densities. So it's over 1 amp per millimeter. So that leads to a very low ohm resistance. So we're talking about 2.5 ohms ohm millimeter for D-mode device and 3.2 for E-mode device. This is more than a factor of 2 compared to single channel devices. So it's a huge gain. But now the question is how we maintain large breakdown voltages. If you take a single planar device, as I mentioned before, you use those planar field plates. We reached 1.4 kilovolts, extremely good. As you include more and more channels and you reduce the sheet resistance, what we see is a reduction also in the breakdown voltage. Actually, for the very highly conductive wafers, we only get 40 volts of breakdown voltage. That's also not really good. And the reason for this is that a planar field plate or a two-dimensional field plate is not suited for highly conductive wafers. So the simulation shows that if you use a typical planar field plate, actually the field accumulates under this region, and that's where the device breaks. So we do need to have a three-dimensional field plate for this multi-channel device. And here's where we follow this slanted tri-gate that we proposed before for high voltages. So here you can see for a planar device, the breakdown was at about 40 volts. By introducing tri-gates, we could increase this. By introducing this slanted tri-gate, we increase this even further. So if you take that previous plot that I showed before, we actually got an increase of 25 times without really changing the sheet resistance. So if you design this nicely, we can now reach 1.3 kilovolts for this multi-channel devices, and while keeping the same kind of RON that I showed before. So this is extremely exciting. And finally, we can also passivate these devices. So we developed this LPCVD silicon nitride passivation that conformally covers all the multi-channels. And this is extremely important if you want to passivate the fin sidewalls. What's interesting is that if you take a single channel device and if you reduce the size of these fins, what you observe is that the dynamic performance degrades very, very fast. And the reason is that if you reduce the size, you're actually introducing more sidewalls. But for multi-channels, the size reduction is actually much less sensitive. And the reason is that we have many more channels, so many more electrons per trap compared to a single channel device. So we're much less sensitive to the number of sidewalls. It only starts increasing when when these dimensions are really small. So we show that if we passivate, we can get a very nice dynamic performance, which is basically very similar to the passivated planar device that we have in the same system. So that's the best that we could do. So to conclude this part, we can see that now we can reach this high breakdown voltage and much, much lower on resistances. So we can, for the first time, really cross these limits of the silicon carbide and go towards the limits of gallium nitride. So this really offers a pathway for efficient power electronic devices. So the last part of this talk, I'd like to present efficient thermal management for this device. And the main problem is that we're talking about reducing the size of the device, increasing the current. And when we reach this point, actually, the thermal management becomes the bottleneck as the power density increases. So we need to find ways to actually extract the heat out of this very compact and high power density devices. And in our lab, we're actually trying to basically convert the silicon substrate from a carrier wafer into an efficient heat sink. And we're following three different strategies. One is a system level strategy. Another one is a packaging level, so it's directly on the device itself. We can combine this microfluidic channels where we can flow fluids to extract the heat. And we have a device level approach. We actually make this microfluidic channels in close contact with the gallium nitride. And of course, the level of heat fluxes that it can extract go from 100 watts per centimeter square all the way to 2000 watts per centimeter square. So here in this talk, I'd like to focus only on this device level approach. So here's an image of our device. You can see the GaN device with the microfluidic channel underneath. What we're doing is to create these voids where we make the channels from the top. And then when we finish the device, when we deposit the metals, we actually close those channels and we can flow fluids inside. So the way the processing works is given by this video here. So we flip the device over. We make large distribution channels for the fluids combined with micro channels in close contact with the gallium nitride. So we flow liquid from one side, we extract the heat, and we take the liquid from the other side. So all of this is integrated in the same device. So here is the schematic of the final device. Here you can see the fabricated device. So it's a tiny little chip. We see the top, we have the electronics. On the bottom, we have microfluidic channels. And the main idea of getting this microfluidic close to the GaN is that we can completely eliminate the thermal resistances that we see in typical heat sinks. So the junction to case, the thermal interface materials, convective and conductive thermal resistances are completely eliminated by this approach we call the co-design. So the electronics are co-designed with the microfluidics. And as a consequence, we can reach now extremely large coefficient of performance for a very large heat fluxes, near 2 kilowatts per centimeter square. It's extremely, extremely good. And finally, what we can do by having the heat sink inside the device is that we can start integrating multiple power devices on the same chip together with the microfluidic cooling. So here's an example. We demonstrated we combined basically 4 high voltage diodes. So those are 1200 volt diodes that I showed before, those tri-gate diodes. We made a full bridge rectifier. And we converted the silicon into this very effective heatsink. Basically, we have one die that has the entire converter and heatsink. We designed a special PCB, so the top layer actually distributes the electronics, the middle layer distributes the fluids. All of this in the same thing that has a form factor of a USB stick, but can convert hundreds of watts. So you can see the rectification that works really nicely. And the advantage is that if you compare to an air-cooled chip, well, after only a few tens of watts, the temperature would be excessively high. But the liquid cooled, we actually can maintain a very low, relatively low temperature for even going above 100 watts dissipated in the chip. And that means that not only we gain in cooling, but also we gain in efficiency. So the peak efficiency of the entire converter increased by quite a bit. So this shows the potential of going towards integration of power devices by also taking the thermal management into account all the way from the beginning. So with that, I would like to conclude the talk where I hope to have shown these 4 strategies to increase the high voltage with slanted tri-gates, to get normally off operation with the nanostructures, to get ultra low on resistance with multi-channels, and to get an efficient thermal management with micro channels. So with that, I would like to thank you all and thank my entire group at EPFL and all our funding sources. So thank you very much.
Oh, thank you, Dr. Mattioli, for an excellent talk. A novel way of tackling the devices on gallium nitride on silicon. It was very, very interesting. I just lost the track of the time also. There is one question from
Sorry.
Professor Rajendra Singh.
Yeah,
that he's asking.
I can hear you.
Oh, okay. Okay. So there is one question from Professor Rajendra Singh. How do you deposit conformal metal layer in tri-gate HEMTs?
We use electron beam evaporation.
Okay.
That's just a typical method. That's the typical evaporation tools with a low deposition rate. That's what we achieve. So nothing really special there.
Okay, good. Another question from me. How do you expect these devices to compete with silicon carbide devices on cost?
So I do believe that the fact that GaN can be grown on large area silicon substrates. I'm not talking about vertical device, but lateral device. That's a major advantage. So if you the fact that you can now have 8-inch, 12-inch GaN on silicon, and you can process that in the same batch, is a major advantage. So I don't think cost is going to be an issue compared to silicon carbide.
Oh, that's great. Meanwhile, there is another question from Dr. Rupesh Kumar Chaube. What about charge trap at fin gate due to the large surface area?
Yeah, so this is what is shown here. So, for example, if we take typical so here's the tri-gate device. We're comparing after passivation, so it's an LPCVD silicon nitride passivation. Here you do have the traps on the sides of this structure, and what we see is that if you have a single channel device, actually, if you do see a degradation in dynamic iron, and the degradation goes high as you increase the number of sidewalls, which is by reducing their width. But on the multi-channel, it's quite amazing because it's completely independent on the sidewalls. And the reason for this is that now we have carrier densities that are much larger than in a single channel, but the trap density is basically the same. So the relative ratio is much more favorable now. So
thank you.
It can be solved.
Yeah, thank you very much. Alison, we are running out of time. Otherwise, there were other questions also. We'll contact you, separately. Thank you very much.
Sure. Thank you very much. Thank you. Bye-bye.
Bye-bye. So the next talk is from by Ms. Jaya Lohni from Solid State Physics Laboratory, Delhi. And she will be, because we have now left with 2 oral presentations. The first presentation is from by Ms. Jaya Lohni, and she will be talking on unintentional gallium incorporation in indium aluminum nitride gallium nitride heterostructures. Ms. Lohni, you may kindly start your presentation.
Thank you so much, sir. Good afternoon, everyone. Myself, Jaya Lohni. I'm a scientist from Solid State Physics Lab and working with the MOCVD team for the growth of 3-nitride material for electronic application. And I thank the organizers of Icee for giving me this opportunity to present my work on unintentional gallium incorporation in InGaN-GaN heterostructures during the MOVEP growth in this conference. So, talking about the indium gallium aluminum nitride and indium aluminum nitride GaN heterostructure. This is a very interesting material for applications like fabrication of devices for UV light emission, LEDs and laser diodes, and also HEMS for high frequency and high power application for radar, satellites and communication. Also a reliable device operation at high temperature for military ambience. As compared to conventional GaN heterostructure, indium aluminum nitride GaN heterostructure offers certain inherent advantages because the 17% indium aluminum nitride alloy is lattice matched to GaN, and therefore one can actually design a strain-free structure which ensures a very good device operation reliability. Also, this heterostructure has very strong spontaneous polarization, which ensures high carrier concentration, even with very thin barrier layers with low indium composition, hence reducing the thermal losses because of resistive heating. So if one has to grow such a device quality material using a technique like MOVEP, there are certain constraints which originate because of the contrasting physical characteristics of aluminum nitride and indium nitride. And as indium aluminum nitride is a binary alloy of aluminum nitride and indium nitride, because of huge difference in the lattice constant of the two, difference in the bond length, thermal stability, and very different surface diffusion characteristics, where the indium nitride gets decomposed at temperatures above 800, 900 degrees centigrade. Aluminum atoms do not have good surface diffusion over this temperature range. Therefore, growing a good indium aluminum nitride layer by epitaxial method becomes quite challenging, and one has to acquire a very stringent control on growth conditions, because any deviation can result in issues like indium segregation, diffusion of indium from one layer to another, resulting in the formation of undesired quaternary alloys, phase separation, and non-uniform composition, posing issues of deviated emission in light emitting devices and device reliability related issues. So while growing this kind of heterostructure in our lab, initially in some of the structures we observed a very peculiar spherical morphology on the top surface with spherical features of diameter around 40 to 50 nanometer in size, which could not be attributed to conventional hillock like features which are observed in MOCVD grown nitrides, because the size was much smaller than those. These HELOC, commonly reported HELOC features have an average size of around 100 nanometer. Further, these can also not be attributed to spiral HELOCs centered around screw dislocations, because the density of the features we observed in our samples were 2 to 3 orders higher than those of the screw dislocations. Also, these spherical features almost covered more than 90% of the top surface and necessitated a further investigation. So, we recorded a phase contrast AFM image of the sample, and we observed that these spherical features were darker as compared to the underlying layer, and the phase contrast was as high as 8 degrees, indicating a different chemical composition or phase of these spherical features from that of the underlying layer. So we further investigated the surface by XPS analysis, and we recorded a fast scan where, in addition to indium 3D photo emission of electron from indium 3D shells and nitrogen 1s and aluminium 2p, we also observed a peak from the gallium 3D. So we collected the signals of these elements at slower scan rate, and for the aluminium 2p32 emission, we observed a broad peak around 74 electron volt with a multi-peak features like a very weak shoulder around the higher binding energy. So we fitted this peak using a pseudo-void multi-peak function accounting for 95% Gaussian and 5% void function, which took care of this asymmetry of the peak, and we resolved the peak corresponding to emission of electrons from aluminium nitride and aluminium oxide 2p shells of these two material systems. And we found from the intensity ratio of these individual peaks that the oxidation, the total oxidation, the percentage of the aluminum, the fraction of the aluminium atoms which has undergone oxidation was less than 3%. There was only mild oxidation that has taken place, which was quite surprising because, as you can see, we have not used any passivating layer or a cap layer over the topmost indium aluminium nitride, and aluminium is very prone to oxidation. So such a weak oxidation is a surprising estimation. And further, there was no photo emission intensity around 73 to 72 electron volt of binding energy, that confirmed that these spherical features were not because of the aluminium precipitates or segregation. So similarly, we recorded the photo emission of the electron from the 3D 5 to 5x2 shell of indium. And again, we saw a broad peak around 445 electron volt with a broad shoulder towards the higher binding energy, indicating a signal from the indium oxide. And we again we fitted this multi-peak using the pseudo-void function and resolved the two peaks. And from the intensity ratio, we found that again the oxidation was almost negligible. And again, toward the lower binding energy, there was no photo emission of the electron. Therefore, indium-indium precipitation or segregation was also ruled out. The surprising observation was that despite that we have not used any cap layer or passivation scheme, the topmost indium aluminium nitride layer had undergone a very weak aerial oxidation. So when we collected the photo signal of the photo emitted electrons for the gallium to around 20 electron volt, we observed contrary signature. The peak was broad, having multi-peak features, but the intensity was towards the higher binding energy, and we observed broad shoulder towards the lower binding energy, which indicated that there is a gallium accumulation actually on the surface, and this gallium has undergone significant oxidation. So we studied this, we further analyzed this photo emission characteristics, and conducted a theoretical depth analysis by assuming these spherical features as made up of a gallium core comprising a shell of oxide, and using the expression where the intensity of the photo emitted electron was represented as a function as an exponential function of depth of the sample and the escape depth of the material. We converted this expression into a spherical polar coordinates using suitable limits using a function fr theta. And then we set up this mathematical expression where we equated the experimentally determined intensity ratio corresponding to photo emission of electron from the 3D shell of gallium oxide to that of the 3D shell of gallium in zero oxidation state in the underlying gallium, and equated it to the theoretically estimated ratio using this expression in spherical polar coordinates, and using the different radius of the core and the total radius of the spherical particle. We solved this expression, and from the best fit values, we estimated a shell thickness of around 1.8 nanometer, which confirmed that a part of the surface of the gallium that has accumulated over the surface of indium aluminium nitride has undergone environmental oxidation. This oxidation is self-limiting in nature and is generally of 1 to 2 nanometer of thickness. And it is interesting to mention here that despite of such a poor morphology and spherical features on the top surface of the indium aluminium nitride GaN heterostructure that we had initially grown, the heterostructure showed very reasonably good electrical characteristics with mobility as high as 1400 centimeters square per volts per second and 2-day concentration more than 2e13 per centimeter square. So it made us think that this kind of spherical pattern, which was undesired during the growth, has resulted in a kind of passivation of the indium aluminium nitride GaN heterostructure that we had grown, and has not deteriorated the material characteristics. So it is not only protecting the underlying indium and aluminium atoms from aerial oxidation, it is also passivating the donor states on the surface, and therefore preserving the 2-day concentration and 2-day characteristics. However, such a spherical feature on the surface is undesirable from device fabrication point of view, because it leads to leakage currents and high contact resistance, as well as it raises several issues related to device operation reliability. So we investigated that from where this unintentional gallium is coming over our heterostructure, because we switched off the gallium source during the MOCVD growth. Once the GaN layer the growth of GaN layer was completed. So we searched literature and we found there are several sources mentioned for this kind of unintentional gallium incorporation. A few of them is like you get this gallium residues from the previous growth, which you can actually avoid by using good growth practices like cleaning the reactor parts, especially the shower head cleaning before every growth, and conducting the baking of the entire reactor at high temperature. And using these good growth practices, we also ensured further. We put a blank substrate and annealed it in hydrogen ambience at 1100 degrees centigrade, and we found that over this sample, there was no such spherical feature and no traces of gallium present by XPS analysis. The second source, which has been reported in literature, is the decomposition of GaN layer at high temperature and diffusion of gallium add atoms from the underlying GaN layer to the indium aluminium nitride layers, resulting in the formation of quaternary alloys and gallium accumulation on the surface. So this gallium is coming from the bottom of the GaN layer. So, and it is reported that this kind of diffusion can be controlled by putting an aluminium nitride spacer layer. And so, as I've already shown that in our structure, we were already using this aluminium nitride spacer layer. So this could also not be the source of gallium in our samples. Further striking a balance between the growth conditions, strikingly different growth conditions for the aluminium nitride and indium nitride, we were already using a very low temperature where this kind of gallium nitride decomposition we had cannot actually take place. So we finally, related more to this kind of a source which is reported in literature, that is the composition of gallium particles on the reactor parts in the presence of indium. So what has been proposed in one of the report is that when you grow gallium nitride, while growing a heterostructure, you grow a 2-micron gallium nitride for a hemmed heterostructure. So when you are growing this gallium nitride, some of the gallium particles are also getting deposited over the reactor parts. And even if you switch off the gallium source, once the GaN growth is over, and you switch on the indium source for the growth of indium aluminium nitride, some of the indium also gets deposited over these particles, and it results in the formation of low melting indium gallium alloy, which results in a gallium rich gas ambience that can lead to unintentional gallium incorporation, not only in the indium aluminium nitride layer, but also once the entire growth is complete and you switch off all the sources, this gallium from the walls of the reactor can also get accumulated as droplets on the surface of the heterostructure during the cool down process, because it's slow melting. And once you take out the sample from the reactor into the ambience, such a gallium metallic layer can undergo environmental oxidation and result in the formation of gallium oxide. So this we further confirmed by fitting the photo emission of 1s electron from the nitrogen in aluminium nitride and indium nitride. We obtained again a broad peak with multi-peak features, and when we try to fit this peak using only the literature reported binding energy of nitrogen in aluminium nitride and nitrogen in indium nitride, we ended up estimating indium composition of 37%, which was much more than the intended 17%. So, however, when we fitted this peak using the binding energies of aluminium nitride, indium nitride, and gallium nitride, we got closer to the realistic figures, and we found that indium and combined with gallium, total composition was 20%, and aluminium was around 80%. We further confirmed the presence of gallium not only on the surface but also.
Ms. Lohani, you will have to conclude your talk now.
Yeah, sir. I think this is my last slide, sir.
Oh.
So we also confirmed the presence of gallium not only on the surface but also in the indium aluminium nitride layer by conducting the Engel resolved depth analysis. And we recorded the indium photo emission of electron from 3D shells of indium and gallium and plotted the ratio points here. And we observed 3 distinct regions. The topmost part accounting for the gallium accumulation as spherical particles. And then there was this region where the indium to gallium ratio kind of, having a very weak, variation, degradation with the positive slope. And there the indium composition is gradually decreasing and the gallium is increasing. And there we have got clear evidence that gallium is not only present on the surface, it is also present in the indium aluminium nitride layer. And the first few monolayers of indium aluminium nitride is free of gallium, and there we have seen an improved ratio of indium to gallium atomic ratio. So this kind of incorporation of gallium on the top surface and the intended indium aluminium nitride layer is undesired and has very adverse implication because it results in undesired ternary alloys, leading to composition variation throughout the layer. It can result in strain in the structure, so poses issues to device reliability. And apart from poor surface finish, in light emitting devices, this kind of incorporation can result in deviation in emission wavelength and energy. So we adopted, to avoid this kind of incorporation, we adopted a template growth approach where we started growing our heterostructure in basically three steps. In the first step, we used to grow a GAN template of almost 80% of the GAN of a thickness, and then in the second step, used to grow the indium aluminium nitride layer, and just before that, a small thickness of the GAN was grown, so there is no significant deposition of gallium on the reactor walls. And then we also used an intended passivation scheme using a cap layer of GAN. And in these structures now we do not observe any kind of spherical features. In fact, we are obtaining on regular basis the typical step flow morphology and reproducible electrical characteristics. And this is how, on the basis of the studies, we have improved our structures, and very small measures, very small alterations and measures taken during the growth, we could improve the material quality of the indium aluminium nitride device structures. Thank you.
Oh, thank you, Ms. Loni, for an excellent work presented here. I think we have already run out of time. So I thank you for participating and making your presentations. So the next oral presentation is by Mr. Bhuvnesh Kushwaha from IIT Madras, and he will be talking on ultra-thin native oxide by barrier layer oxidation at gate dielectric for aluminum, indium nitride, gallium nitride mishems. Mr. Kushwaha, please.
Okay. Thank you, sir. Are you able to see my screen?
Yes, yes.
Okay. Okay, so good afternoon, everyone. I am Bhuvnesh Kushwaha from Department of Electrical Engineering, IIT Madras. And first of all, I would like to thanks to Icee 2020 conference, which will provide me the platform to present my work. So my oral presentations is based on the ultra-thin native oxide by barrier layer oxidations, which is basically a thermal oxidations, which can be used as a gate dielectric for aluminum nitride, gallium nitride mishems. So so first of all, I just want to quickly go over the basic properties of the gallium nitride and what are the basic structures for the aluminum indium nitride mishems in which the gate dielectric has inserted between the gate contact and barrier layer in order to reduce the gate leakage current in the hemmed transistors. Then various method which is adopted to realize the AL2O3, and then I will conclude it to the approach which is a high pressure oxidations to realize the aluminum oxide for the mishem. And I will explain all the results and process flow which I followed to fabricate the mishem devices using barrier layer oxidations.
Mr. Kushwaha, for saving on time, I suggest that you can avoid talking about crystal structure and properties, as the whole audience, quite aware of that, and
okay,
directly
sure.
going on to your mishemed structure. Is that right?
Yeah, sure. Okay,
okay,
sure.
Thank you.
No issue.
Thank
Yeah,
you.
yeah,
Thank
sure.
you.
Yeah, so as we know the basic structure of the HAMT, which is in which to control the gate channels, the Schottky contacts can be used as a gate contact, and as we have seen in this figure. So due to this gate contact, there is a huge gate leakage current is there in the hand transistors, which can provide the various reliabilities, which can affect the various reliabilities in the HAMT structure. So to avoid this gate leakage, to suppress this gate leakage current, the gate dielectric has been inserted between the barrier layers and the gate contact, so which can reduce the gate leakage current. And as we know that various materials has been used as a gate dielectric. Some of them are aluminum oxide, hafnium oxide, ZrO2, etc. has been reported as a gate dielectric for the mishem, in which Al2O3 is the widely used because of its high band gap and the dielectric structures. So yeah. So to realize the gate dielectrics, so where various to grow the aluminum oxide, various methods like depositions and oxidations has been carried out. Some of them are the ALDs, MOCVDs, reactive ion sputtering, thermal oxidations of aluminum layer. Various methods has been adopted to grow the aluminum oxide as a gate dielectric. but due to the introduce the insulating layer can reduce the gate leakage current, but it can also move the gate contact away from the channel, which can reduce the peak trans conductance of the devices. So there is a trade-off between the gate leakage current separations and the peak trans conductance of the devices. To overcome these dependencies, the native oxide grown by the thermal oxidations of the barrier layers has been used as an alternative. So, but as we have seen in the thermal oxidations of the barrier layer, which is required a very high temperature. So, because of this high temperature, some of the oxygen atoms can diffuse inside the barrier layer, and which can deplete the 2dg charges, which can deplete the 2dg charges inside the 2D charges, which is due to the deeper propagations of the oxygen atom inside the barrier layer. So, in order to avoid these diffusions, the high pressure oxidation process has been adopted, in which we have decreased that oxidation temperatures by increasing the pressures of the oxide of the oxygen gas inside the chambers, which can give our margin to reduce the temperature, which can avoid the diffusions of the oxygen. So, in order to carry out the high pressure oxidation, we have in our department we have make one system called high pressure oxidation setup, which is schematic whose schematic diagram is shown is here. Basically, this systems has made up of the stainless steel, which is closely packed after the sample loading, and inside this systems we have an internal furnace where the silicon carbide heating rods has been used as a heating element. Then after the sample loading, so this is the basic process flow for carry out the oxidation. So first we will load the samples, then we will ramp up the temperatures in the nitrogen ambient. Then once the oxidation temperature has been reached, we will suddenly increase the pressure of the oxidation inside the chamber, such that we will make the inflow and outflow of the gas as equal. So the pressure should be maintained throughout the process. Once the oxidations has been completed, we will create the post-oxidation annealing in N2 ambient after in N2 ambient at the oxidation temperature, and then slowly we will ramp down the temperature in the N2 ambient. So this is the basic process flow to fabricate the MISM devices for the barrier layer oxidized MISMs. So first we will take the standard wafer, which is aluminum indium nitride gallium nitride HAMT wafer, and then we will make the gate contact by the titanium aluminum nickel gold metal stacks, which is followed by the rapid thermal annealing and for the contact activations. Now, to facilitate the barrier layer oxidations, we will first remove this GAN cap layer by the ICPRI plasma using BCl3 as a process gas for the barrier layer oxidations. So then the high pressure oxidations has been carried out as shown in the previously. So after this high pressure oxidation, the aluminum indium nitride, some part of the aluminum indium nitride barrier layer will consume, and it will make the aluminum oxide. Then the gate contact has been made by the nickel gold metal stacks. Then after this gate contacts, the forming gas annealing has been carried out for the multiple time for the annealing time optimization at 400 degrees Celsius. So this is the first IBCB characteristics of the devices, which is high pressure, which is oxidized in high pressure oxidation at the 400 and 500 degrees Celsius for the 15-minute in 3 atm pressures. And we have found that there is only one order reductions in the current, and the threshold voltage shift of the MISD with respect to SBD is very less, means minus 3 volt to minus 0.3 volt. Now, as I mentioned earlier, we have done the post metal annealing also in the forming gas at the 400 degrees Celsius for the different time of 15 minutes, 10 minutes, 15 minutes, and the 20 minutes. And we have seen this, there is a reduction in the gate leakage is up to the 15 minutes of the annealing. Since this okay. In the barrier layer oxidation, during barrier layer oxidations, the oxygen atoms can be penetrate inside the barrier layers, and which can make the oxygen vacancies. Now, these oxidation vacancies will make the conductive path, and it will increase the gate leakage current. So during the forming gas annealing, these oxygen vacancies can be passivated by the hydrogen, and we will get the some more reductions in the gate leakage current. But as we have seen at the annealing after the further annealing after the 15 minute, we have seen some more, again, the increment in the gate leakage current, which is due to the metal diffusion inside the gate metal diffusion inside the dielectric. So as we know, we in the previous case, we just got the one order reductions in the gate leakage current. So that is because of the thinner layer. So to increase the thickness of the oxide layer, we have carried out the temperature for the longer period by keeping the temperature constant at the which is a 500 degrees Celsius, and we have increased the oxidation time to 30 minutes and the 60 minutes. Now, in both of the cases, we have found that the gate leakage current is around the 5 order reductions in the reverse bias, and more than 3 order reductions we have found in the forward bias, and we will get the more VG swing also for the cases of MISD. And in the CV, we have found that after 2.5 volt, we have electron spillover also, where the charge can swept over the barrier layer and deposited within the gate dielectric. And these devices will show the very less hysteresis voltage also, which is 0.08 in the 30-minute oxidation case and 0.07 in the 60-minute oxidation case. Right. So the thickness of the devices, see the oxidations is happening by the consuming the barrier layer itself and making the gate dielectric. So the thickness of the grown oxide can be extracted using these equations, where 12 nanometer is the barrier layer thickness, initial thickness. The delta VTH is the shift of the threshold voltage of the MISD with reference to SBD, and VTH is the threshold voltage of the SBD devices. So the extracted oxide thickness for the MISDs has been summarized in this figure, where we can see that the thickness will range from the 1.68 nanometer to 2.42 nanometer. In this, in the cases of 2.4 nanometer, we are getting the 5 order reduction of the leakage current also. Now, for the cases of 500 degrees Celsius, this the square of this thickness has been plotted with the time, and we found that there is a linear fit in the square of the thickness, which can show the parabolic law of the Deal group model, which is there for the oxidation of the silicon. So we have concluded that this oxidation is carried out by the diffusion of the oxygen atom inside the barrier layer. So in the high pressure, the main purpose of the high pressure oxidation is to reduce the temperature in order to avoid the diffusion of the oxygen inside the barrier layer. The another approach is that we have carried out is the rapid thermal oxidations, where we have take the oxidation temperature as a 600 degrees Celsius, but we have carried out the oxidation for a less time, which is a 60 second and 120 second. So in this case also, we have found that so for the cases of 60 seconds and 120 seconds, we have found the gate leakage current reduced by around 1 order reductions in the gate leakage for the both MISD. And the extracted thickness we have found is 0.83 nanometer for the 60 seconds case, and for the 120 second case, we got the thickness of the 1.70 nanometer, which is very less. The same rapid thermal oxidation, the same post-gate annealing we have also carried out for these samples, and the same conclusion we got, that like after the 15-minute annealings, again the current has been rise up. So the annealing has been optimized for the 15 minutes in the forming gas ambient. In order to increase the oxide thickness, we have increased the temperature also, like we have tried out at the 700 degrees Celsius for the 120 seconds oxidations, but we have again get the reduction in the gate leakage for the 1 order only, and the extracted thickness is 1.80 nanometer. So this reduction of the gate leakage current is just due to the less thickness of the gate oxide dielectrics, and which requires some more temperature or a time for the oxidations, which is not good for the devices and for the ohmic contacts also. So that is a summary. Like we have carried out the variolar oxidations by the two method, which is high pressure oxidations and the rapid thermal oxidations, in which the high pressure oxidation provide the better controllability over the oxide thickness, because we are having a very less growth rate growth rate, and we can grow a very denser native oxide also, where as we have seen we are getting a 5 order reductions in the gate leakage for the case of 2.42 nanometer oxide thickness. So high pressure high pressure oxidation of barrier layer is effective for the reducing the gate leakage current, and we can found the very higher voltage swing also in the forward bias. So thank you for this.
Oh, excellent results presented, Mr. Kushwa. All the best for your future endeavors. I think with this, we come to the end of this session. And this, because we have already late by about 18 minutes, I think everybody is waiting to leave for the lunch. I'm sorry that I could not take present questions from Dr. Krishnamurthy and Mr. Vishal Sharma. Due to the want of time, I request them to contact directly the speakers whose emails would be available from the conference. Okay, thank you very much, and I am thankful to Icee organizers to giving me this opportunity to sit through this excellent session. It was very, very interesting and very illuminating for me as well. Thank you. I hope you all enjoyed this session. Thank you very much. Bye-bye.
Rawal, am I on?
Namaskar,
Hello.
Rawal Sahab.
Namaskar, sir. Namaskar. End कर देते हैं because in my session the oral presenter is not coming, so we can have a little bit longer break, and maybe we join for the post lunch session at 1:45.
Yes, sir. We can join at 1:45. This is the volunteer, Dr. Manikanta Babu.
Okay. Thank you.
Yeah, we can join at 1:45. Thank you.
1:45. Okay. तुम्हें कुछ नहीं, बस अब चुप रहना है. Hello, am I audible?
Yes, Dr. Rawal.
So, shall we start?
Yeah,
How many participants have already joined? 15 are already there. Okay. So, Dr. Manikantha, are you there? Good afternoon, Dr. Digvijay. How are you?
I'm doing fine. How are you, Dr. Rawal?
Fine. So, I think for proper management of time, I think we should start now, and people will join in the due course. So, I welcome session and this session is having three invited talks. The first talk is going to be delivered by Professor Digvijay Nath, and the title of talk is 3-nitrate HAMT on silicon for RF electronics. So let me briefly introduce Dr. Digvijay, assistant professor at Indian Institute of Science, and he has done his PhD from Ohio State University and BE from BITS Pilani. And his current research interests include growth and study of optical properties of beta gallium oxide, gallium nitride HAMS on silicon for RF, GaN-based HAMS for high voltage application, 2D materials-based synaptic devices. So I now formally invite Dr. Digvijay to present his talk.
Thank you, Dr. Rawal. Thank you for the kind introduction. So I'll just share my slide. Hope it's visible. Kindly let me know if it is visible. Okay.
It's visible.
Okay. And okay. Good afternoon, everyone. Thank you to the organizers for having me here. My name is Digvijay from Center for Nanoscience and Engineering, Icee, Bangalore. And today I'll be talking about some of our work on 3-nitrate HAMS on silicon for RF. Much of the work is unpublished and it's still ongoing. So some of the things will need more investigation, as we will see when we talk about. So I thank Vasu and Dr. Muralidharan, who are our close collaborators, and our students, particularly Sai and Niranjan, who have done most of the work I'll show. And the work is funded by primarily ISRO through its SCL arm and SERB imprint. The facilities at Cleanroom, the picture of which is shown here, are supported by MHRD, MAITI, and DST, and acknowledge funding from time.
So, Dr. Digvijay, sorry for interrupting. I would request that you finish your talk in 25 minutes and then we'll take 5 minutes for the questions.
Right. Sure. Okay.
Go ahead, please.
Sure. Yeah. So the talk is divided into motivation, and then we'll speak about some work on indium aluminum nitride GaN on silicon HAMS, and finally on our work on gold-free contact to alkane GaN on silicon HAMS. So I don't have to explain about the promises of GaN HAMS. The audience knows it very well, but I'd like to particularly say that going ahead in the near future, there is a lot of push towards working towards higher and higher frequencies, even millimeter wave and going all the way up to 100 gigahertz. The upcoming 5G communication, for example, is looking at both sub-6 gigahertz as well as carbon, which is starting from 28 gigahertz. The reason is there's a lot of congestion at lower networks, lower frequency ranges. So we are looking at very high-speed frequency ranges, coming short range, indoor communication links, line of sight communication, and things like that. Automotive radar, for example. So all these commercial applications necessitate looking at devices that can deliver high power at millimeter wave or carbon at least. So this is the day when we are looking at gallium nitride on silicon also, because traditionally, although gallium nitride and silicon carbide have been excellent in performance, in thermal and RF performance, but now people are looking at cost also, because if you want to expand to 5G base stations all over the world, the cost is a big issue. So silicon, GaN silicon platform, it's suitable for low cost and the large manufacturability, scalability, advantages, because in silicon CMOS foundry you can go up to 12-inch wafers. And so the devices need to be, CMOS integrable or compatible in some ways. And also the performance of GaN on silicon for RF has to be evaluated and, investigated to make it at par or at least as close as possible to GaN on silicon carbide. So that's the primary motivation. So there are challenges unique to GaN on silicon for RF, this is not for power device necessarily, but for RF. So one of the issues is that when you grow on silicon and not silicon carbide, the dislocation density is typically around 10 times higher, even more. This is a big issue for GaN amps on silicon for RF, even for power devices. But one particular issue that needs to be highlighted is that there is a parasitic channel that often forms at the ALN and silicon interface. The ALN is the nucleation layer that is necessary for growing the rest of the layers. So there are many theories for why this parasitic channel might form. But nevertheless, this is a major source of loss for RF. So this has to be taken into account, and in epitaxial stack has to be engineered to minimize this loss. The substrate itself, even if you use high resistive substrate at high temperatures of operation in RF, what happens is that your silicon will start having more intrinsic area concentration. So it will become mildly doped material or mildly conducting material, sorry. And substrate loss becomes an issue. Besides, compared to silicon carbide, silicon has a poorer thermal conductivity. So thermal issues are also prominent for GaN on silicon. The elegant transition layers, they are grown to manage the strain and the bow. This is also a major issue that doesn't exist in GaN on silicon carbide. The wafer bow, especially for 6 and 8 inch and even more, is a very big issue that needs to be addressed if you want to make large-scale manufacturable GaN on silicon RF devices. The buffer needs to be very insulating, and so people typically use iron doping as an acceptor, and this iron doping also leads to buffer-induced collapse and traps that are also many challenges. And then contact resistance, of course, it exists also in GaN on silicon carbide, but people have not investigated as much on contact resistance studies for GaN on silicon amps based on the literature, but it's an interesting aspect. Passivation. Passivation is also an important aspect to look into, which is similar to silicon carbide, GaN on silicon carbide, but nevertheless, there's a lot of study that remains to be done. And more importantly, for deeply scaled devices, if you want to go to carbon and millimeter wave, the barrier has to be really thin so that the gate has better control on these ultra scale devices. So the parasitic channel formation, which is a major issue, of course, my talk is not centered on that, but I'd like to highlight is nevertheless, this is from a paper from Harish Chandrasekhar. There could be aluminum and gallium diffusion from the growing layers, or there could be an inversion at the interface of aluminum nitride silicon due to polarization. This parasitic channel layer is a major source of loss for RF devices. So there are many techniques people have adopted to engineer, the low temperature ALN growth, for example, that can act as a diffusion barrier, or people even remove the silicon substrate partially or fully below the device so that the parasitic loss can be minimized. So here on the figure on the right, if I may start the pointer, figure on the right bottom actually shows you the loss that is measured for GaN on silicon devices optimized with optimized epitaxial stack or even trench etching. It shows very low, loss up to 100 gigahertz. It shows loss less than 1 dB per mm. So that's pretty good, promising results that people have published already. What is the status of GaN HAMT on silicon? Typically, Algan GaN HAMT is the most widely studied stack on silicon. People have shown discrete devices to power amplifiers, MMICs, LNAs, all the way from 2 gigahertz to almost 90 gigahertz, going up to W-band. So there's a lot of reports, a lot of demonstrations, although reliability is thoroughly, yet to be investigated on these devices, long-term reliability. And output power densities in watt per mm for GaN on silicon is yet to reach, that of GaN on silicon carbide. It's much lower than what you can achieve on GaN on silicon carbide. For example, in GaN on silicon carbide, the record power at C-band is up to 40 watt per millimeter, which is ridiculously high power. GaN on silicon probably would be around 4 to 5 watt per millimeter on average. So there's a lot of work that remains to be done on this front. On a commercial aspect, OMIC has a foundry in Europe, and they have already released GaN on silicon 100 nanometer process. It's like a foundry service that they offer. 60 nanometer, 40 nanometer nodes are also there. They have already demonstrated carbon, PA and V-band going up to 50, 60 gigahertz downlink. So there's a lot of work activity going on GaN on silicon devices, especially for cost issues, and people are trying to push the performance, but there's a lot of work that needs to be done to make it, as at par with silicon carbide. This is what I'm trying to emphasize in my talk here. So one particular thing that needs to be, I would like to highlight is essentially the indium aluminum nitride barrier, GaN on HAMT. This has been studied, but not as much widely. The promise of indium aluminum nitride is that it can give much higher 2DG density and hence a higher output current. It is very thin barrier. It's lattice matched also. It can be really aggressively scaled. The gate to channel distance can be as low as 5 nanometer, which is not possible without researching LGAN, for example. So very high GM and FT can be expected in the ultra thin barriers indium aluminum nitride devices. So these two figures show indium aluminum nitride on silicon carbide long back. These two are more recent results on indium aluminum nitride on silicon. People are trying to look at it. The record high cutoff frequency till now is around 300 gigahertz from NTU Singapore. And this plot shows how over the years, the cutoff frequency has been improving on indium aluminum nitride GaN on silicon. So, indium aluminum nitride GaN on silicon or even silicon carbide shows some of the highest FTs in general, even compared to LGAN GaN. So this is because of the ultra thin nature and high charge density of these HAMs. So now I'll come to the part of my talk. So I'll show some work that we have been doing on indium aluminum nitride GaN on silicon. There are two primary parts. One is I will show you results for aggressively scale HAMT for millimeter wave that we are doing. And one is our work on introducing a novel metallization scheme using scandium contact for lower contact resistance and lower surface roughness. So this is a typical stack of indium aluminum nitride. It's a wafer from NTT, Japan. We have fabricated devices of different gate lengths going from 60 nanometer to 200 nanometer, but primarily focused on 80 to 200 nanometer. Source to drain spacing was around 2 micron, and the width of the device 2 into 50 micron. These are SCM images that shows the schematic of the device, not schematic, the actual fabricated device. And this is a zoomed SCM to show 60 nanometer gate length in the source and the drain. These are the steps that we followed. Tri-al nickel gold. This is gold-based contact, by the way. And gate contact was 10 and 17 nanometer. GSG pads were Ti gold, 200, 400 nanometer. We got counter resistance typically around 0.20 millimeter, which is very good, 0.2, 0.23. 230 ohm per square sheet resistance that indicates extremely high charge density in these wafers. The gate leakage was reasonably okay, less than microamp per millimeter, minus 5 volt. The output current density was fairly high, 1.7, 1.8 amp per millimeter. The transconductance was around 400, 450 millisiemens per millimeter on these devices. This is a typical representation, but there are a bunch of measurements we have done on a lot of different devices. So this is a plot, for example, we show the transfer characteristics for different gate lengths. We should see that, at 200 nanometer, the threshold voltage is slightly lower. But with shorter and shorter gate lengths, we see more short channel effects. So the threshold voltage shifts more to the negative. And these are some results that show, if the gate length is 60 nanometer and the source drain spacing is 1 micron, we can exceed about 2 amp per millimeter on the output current, which is very high current. And the GM doesn't improve a lot, but nevertheless, we can get very high FT on these devices. So these 4 plots show for 4 different device geometries, for the gate length, 70, 80, 100, and 200 nanometer. What is the threshold voltage variation? So this is basically to highlight the increasing nature of the short channel effects as we go down the gate lengths. So at 200 nanometer, you can see the threshold voltage variation is very minimal. Go to 100 and then 80 and then 70 nanometer, the threshold voltage variation changes a lot. That indicates the short channel effects coming into play because this epitaxial stack does not have a back barrier to confine the carriers. Similarly, the subthreshold slopes also degrades and also becomes different at different gate drain voltages. So if you have different drain, this is again for 4 different devices for different drain voltages, VD going from 1 volt to 5 volt, for example, how the subthreshold slope changes. So you can see at 200 nanometer, it's minimal. But if you come to 70 nanometer gate length devices, which are very deeply scaled, then the short channel effects become very pronounced. We can see that subthreshold slope is changing a lot with the drain voltage, indicating that the drain is having a much more control on short channel devices now. So this is a summary, of this short channel effects. So threshold voltage changes with respect to gate length, as expected, as I have shown. And the drain-induced barrier lowering dribble, which is a figure of merit kind of thing for short channel, also becomes more pronounced and important as we go down to 17 nanometer. You can see the steep increase in dribble. So this means that we need to suppress the the short channel effects, and we need to have a contextual stack with an inherent back barrier like an InGaN back barrier or LGaN back barrier. And unfortunately, not much studies have been done on back barrier indium aluminum nitride GaN HAMs. Very few studies are there. So this is an area that we are trying to investigate, right now. So RF measurements were done, small signal measurements in VNA. But the as measured characteristics for a 200 nanometer gate length device was around 70 gigahertz on FT, 46 on FMAX. If we de-embed using open and short structures, we get up to 90 gigahertz FT. The FTLG product for this is around 18 gigahertz micron, which is one of the highest, or probably the highest, for GaN on silicon HAMs, as we know till date. So this is one of the highest FTLG products that we got. Then using cold FET and hot FET measurements, we try to extract out various parameters like the resistances, the parasitic resistances, and the GM values, using which we try to simulate the FT. And for example, 200 nanometer gate length, it gives an FT of around 86 gigahertz, which is close to 90 gigahertz, but we need to get further calibrations done to match it even better. For even shorter channel length, for example, 80 nanometer gate length, we are able to measure or extract out an FT of around 196 gigahertz, which is one of the highest in the world. We believe the highest is 300. I think this is the third highest FT in the world. We need to do a lot of work on this front also. But nevertheless, the plot here shows the FT where we are in respect to world, and this figure shows you FTLG product. These top three dots are actually GaN on silicon carbide. So, of course, silicon carbide will definitely have much superior FT and FTLG product. So we cannot compare with them. But all other FTLG product work based on, GaN on silicon are here. And so we believe our work with FTLG of 18 gigahertz micron is probably one of the, this here is one of the highest, or probably the highest in the world. So that it's not yet published result. We got it more recently here. Then I'll switch gears from our deeply scaled indium aluminum nitride devices, and I'll focus on our work on ohmic contacts to this indium aluminum nitride GaN HAMs. So typically people use regrowth to make very low contact resistance, less than 0.1 ohm millimeter, but it's a more complicated process. You need to have regrowth, and that's a more expensive, more complicated process. So people typically use alloyed contacts, and in alloyed contacts, you can get very low contact resistance with extreme, optimization, but then there are issues like the edge equity and the surface roughness of the metal itself, which comes into play if your device, is really, really low. If the source drain spacing is less than 1 micron, for example, then the roughness of the the metal contact when you anneal at high temperature becomes very important. So for all these reasons, there's always a, people have been always looking for metals and metal schemes in which alloying can be done at moderate temperature, for example, without, roughening the surface, for example. Typical metal contact, as we all know, is Ti-Al nickel gold, which people use widely. It's a gold-based contact. And the idea is that the titanium nitride that forms at the interface, it scavenges nitrogen, creating nitrogen vacancies in GaN, makes it n-type dope. The low work function of titanium nitride is there. Some people also say Ti-Al, an alloy forms there and spikes down in the form of an inclusion. It forms this ohmic contact with low work function and things like that. So this is a very widely studied contact, and people have shown going down to less than 0.1 ohm millimeter. Professor Dipankar Saha from IIT Bombay has shown very low contact resistance. But then, the problem is the metal contact might have some rough surface morphology, for example, and that may not be suitable for really, really scaled devices. So we are thinking, can we explore a new metal scheme? And scandium has a very low work function, so around 3.5 eV. So we realized that scandium has never been explored for indium aluminum nitride HAMT, and so we tried to investigate metal stack that consists of scandium, aluminum, nickel, gold on this indium aluminum nitride HAMT stacks. And the idea behind is that scandium, if it diffuses into the barrier, scandium can form alloy with 3 nitrides, and scandium-based alloys are known to be semiconducting and also have very high polarization, as we can witness by growing volume of work on scandium gallium nitride-based HAMTs that are reported increasingly. So that putting a scandium contact might actually be interesting, and total barrier we have is around 11 nanometer, the HAMT stack. We had also a control sample of Ti-Al nickel gold, and under process under similar conditions, we showed that scandium-based contact would offer somewhat lower contact resistance, around 0.39 ohm millimeter as opposed to 0.48 ohm millimeter. But again, this is not to say that our titanium-based contact is worse, because we can go up to even sometimes 0.2. It depends on the exact surface preparation and annealing conditions. But this is an alternative metal stack that we are trying to explore and optimize for lower contact resistance, at the same time lower surface morphology, smoother surface morphology. So for example, the bottom AFM here shows a typical titanium-based contact. After annealing, the surface roughness is 73 nanometer, whereas scandium-based contact after annealing is 23 nanometer. So this significant difference in surface roughness of the metal stack is a very promising aspect of scandium-based contact, and we need to optimize it further to make it even lower contact resistance at the same time to have smoother surfaces. So to understand how it's forming an ohmic contact, we tried to do some TEM imaging. We found that scandium diffuses preferentially along the steering dislocations line. And we also found out that the scandium forms inclusions below the metal. And we did these colorful maps that I show here are actually EDS elemental maps. And we see that, and this is, I think, this is along this direction here. And we see that there is nickel. Of course, nickel alloy is forming an, the metal contact over top. And this indium, the purple line here shows that indium aluminum nitride barrier is there. There is gallium deficiency here, which means gallium has gone away to form alloy with scandium. Scandium, you can see, the scandium has come up here. So there's a scandium gallium nitride inclusion in below the metal. That is one thing that we observe from here. And the width of the inclusion can be up to half a micron also. The depth is around 60 nanometers, 60, 70 nanometers. Then we did an EDS line map, along this direction. Along this direction, we showed the atomic profile of the different elements, aluminum, gallium, and scandium. We can see that gallium rises here at this interface sharply, and also the scandium. The scandium has a peak along this, that tells you that scandium is actually going inside. And scandium actually acts as a lower function metal contact at this interface. And there's a graded interface. I'll show you a better TM image in the next slide. There's a graded interface which is also observable from here. From this profile here, the gallium is rising gradually at the at the scandium gallium nitride interface. Gallium is rising gradually, scandium is falling gradually. That indicates that there is a graded interface at scandium gallium nitride interface over here. This is scandium gallium nitride over here. So this is a HRTM image that shows the interface between scandium gallium nitride and gallium nitride. That shows that the barrier is more graded, which indicates also that there's a diffusion happening along this point. And we also did a selected area electron diffraction imaging of this sample at this interface, and we found out there is a splitting of these diffraction spots in all directions, indicating the crystallinity of the layer and also the lattice mismatch between scandium gallium nitride, which has a lower lattice constant than gallium nitride. The oriental relationship between these two, scandium gallium nitride and gallium nitride, was also obvious from this SAED pattern. So the crystallinity was also confirmed from these images. Then we also had studied the barrier, the indium aluminum nitride barrier close to the metal. We found out the barrier was slightly modified with the scandium indium aluminum nitride. Around a couple of nanometers has been modified around that point. And we also did FFT, fast Fourier transform, as well as XRD analysis. XRD is not shown here, but that indicated that we have a crystalline layer over here. And the FFT pattern also shows that scandium aluminum indium nitride that we form here is also quite crystalline. So the crystalline nature makes us possible to conjecture that the scandium that is going in probably would also retain its polarization or crystalline nature that can lead to lower that can lead to a lower work function, and maybe polarization induced effects might come into play in reducing the contact resistance. So there could be many possible mechanisms, and this needs further investigation. We are trying to study it still. But what could be a mechanism for forming a lower ohmic contact? One could be that, of course, scandium, when you form scandium gallium nitride, it's a polar material also. So in the this at the interface of scandium gallium nitride and gallium nitride, there could be a channel that forms, but this will not be connected to the 2DG that is there in the sample. So maybe they can somehow go through a punctured barrier, scandium gallium nitride, but this is a speculation or hypothesis that we have to the trading dislocation, for example. Another hypothesis is that the scandium indium aluminum nitride interface might also have a charge because of the polarization. But then this charge also is not connected to the 2DG that we have. So maybe that indium aluminum nitride, through that, the charge can move through either some thermal assisted tunneling or trap assisted tunneling, and that can also lead to a lower contact resistance. So this work needs a little bit more study, but these are some of the speculations, or at least hypotheses that we have to believe how our scandium-based contact is making lower, giving a good ohmic contact or ohmic work function, ohmic contact to these devices that we have. So we also annealed this stack at different temperatures, but the temperature variation I'm not showing in details. I'm just capturing the contact resistance. We see that if you anneal at a temperature lower than 775, for example, the contact resistance can be really high. But if you anneal at very high temperatures like 825 and above, then the roughness of the surface becomes very high. So we have to find a sweet spot around 775 to 790. And that spot where the contact resistance also is low, at the same time the surface roughness of the metal stack is also low. So those two conditions have to be traded off, and 780 degrees Celsius is our sweet spot in the study here. So the last part of the talk, and I believe I'm on time, I have probably a few minutes more, is on trying to understand our work on gold-free contact to Elgin-Hampton silicon. The reason we want to do gold-free, as we all know, is because it is one of the important ingredients for making it CMOS compatible. There are many aspects of CMOS compatibility like planarization, MESA, no MESA etching, and things like that. But gold-free is a very important aspect, as CMOS foundries do not entertain gold. So in gold-free contact, and there has been a lot of work, of course, and a lot of processes are there that have studied. But nevertheless, we are trying to study some of the specific etch chemistries and metallization schemes that I'll show you here. In gold-free contact, one of the important things is to have a well-engineered metal stack. Okay? That can be high temperature anneal, but then that's again not good. So idea is to do a low temperature anneal or a moderate anneal, but for that we might want to etch away partially or fully the ohmic barrier, the top barrier of the algam. So that's called recess-based ohmic contact. And the surface treatment, the plasma treatment, and other things are extremely crucial to determining the optimal condition for having a good ohmic contact. The problem with recess etching is that we need an extremely high repeatable process where the barrier thickness and other things that we etch can be really, really consistent and repeatable. Okay? And everything needs to be very precise, otherwise there'll be wafer to wafer or device to device variability that we might also show here. So if you want to talk about recess etch ohmic contact, okay, then typical recess etch chemistries that people use for recessing the barrier are BCl3Cl2, BCl3O2, and chlorine-based chemistries and so on. Here we will focus on BCl3Cl2 and BCl3O2 chemistries that people widely report. And the stack, for gold-free stack, there's a lot of metal schemes that people use based on all this molybdenum, nickel, platinum, and so on and so forth. But here we shall try to focus on titanium, aluminum, titanium, tungsten stack, which is known to give a lower contact resistance. So coming to etch chemistry, this sample was, of course, what's thank our collaborators from Cambridge, Colin Humphreys, Professor Colin Humphreys, and Ira Guinea. This is a conventional Elgin stack on silicon. We use two recipes. One is BCl3O2 and one is BCl3Cl2 recipes.
Dr. Vijay, I request you to conclude 2-3 minutes.
Sure. So the details are given here. I'll not go here. We use the digital etching cycle. One step would be BCl3, one step would be O2, and so on. The O2 recipe was found to be much better because the oxygen plasma also treats as a etching mechanism that removes the sidewall polymerization. BCl3Cl2 etch recipe was found to be not so optimal actually because it was a lot of sidewall polymerization when we do the etching. So that in here I'm showing you the contact resistance for BCl3O2 and over BCl3Cl2. We see that BCl3Cl2 has a wide range of contact resistance. That's because the recess etch non-uniformity is very high. As I told, this is most likely because of a non-optimal, removal of the sidewall polymerization. The etch residues will fall on the sidewall, and that cannot be removed by chlorine, but oxygen does remove it. So BCl3O2 recipe is a more uniform and suitable recipe. And we had done more studies on BCl3O2. Therefore, we tried to do different etch schemes. One for 18 nanometer partial removal of the barrier, 130 nanometer full removal of the barrier. We found that if you remove the barrier almost fully, then the contact resistance becomes really low, almost 0.5 ohm millimeter, which is one of the lowest contact resistances reported for this metal stack. The metal stack uses Ti-L titanium gold. And if you use partial research, then the contact resistance was found to be higher as well as non-uniform. Okay. So this was the the conclusion we got. And if we overetch the barrier, then the contact resistance again becomes worse because the reason is we have used a soft mask as a photoresist as a mask. We have to use a hard mask and do a slant profile in order to have a sideways contact for overetched barrier. So that's something we had not done. So then the different metal stacks were studied. One was Ti-L titanium tungsten and Ti-aluminum. We again found that the average roughness as well as the contact resistance was much better when we used titanium aluminum titanium tungsten contact with a lower specific contact resistivity also. In the interest of time, I'll skip that. And finally, we did temperature dependent measurements on both these type of stacks to find out what is the transport mechanism. And we found out that for the optimal contact that we have, the fitting was best for field emission. So we believe the dominant carrier transport mechanism is a field emission with a lower barrier of around 0.42 eV. And there's a localized doping that happens at around 90 to 10 to the power 18 per centimeter cube. So this is temperature dependent measurements that was done to confirm the same. So with that, we'll conclude the talk, I hope in time. This is my group. Many of the RF folks actually are missing from the group. I'd like to thank all the students, MNCF and NFC staff, and in particular, Dr. Muralidharan and Vasu for this collaboration. This is a sample that we processed recently, and this is an SM image of the device that I've shown. So thank you again, everyone, for your time, and I'll be glad to take any questions. I hope
Dr. Digvijay, for an excellent talk and sticking to the time. We have time for one or two quick questions, if there are any.
Okay.
Rupesh, ask one question in the chat box.
Sure, I'm not able to see it actually.
Question is, have you also tried T-gate HAMT? This is the question.
No, actually, we are going to try, or we are in the process of trying, because our Fmax is low. So we need to do mushroom as well as T-gates to bring our Fmax up. So good question. Thank you.
Question is that what is the effect of aspect ratio to DIBL performance, so to DIBL phenomena?
Yeah, we have not investigated that as much because our indium aluminum nitride is around 10 nanometer thick, and our gate is around 60 nanometer minimum, or 70-80 nanometer. So the aspect ratio is around 7 or 8:1, and that's fairly good actually. But the DIBL is degrading because we don't have a back barrier, so we need to confine the carrier. That's the primary reason. If we do an AlGaN-GaN HAMT at 60 nanometer gate length, then we can study the aspect ratio better because we can etch the AlGaN and then do it. But in indium aluminum nitride, the barrier is already very thin, so we have not done that.
But to completely eliminate these short channel effects, you need to have gate length by barrier ratio greater than 14 or
10.
so. So
Yes,
7 looks
10.
like a little bit lower side.
Yeah, I mean, we have indium aluminum nitride HAMS with also 6-7 nanometer barrier. Maybe we should try that. Then it will probably be okay. But that's we have purchased some of the wafers. Yeah.
Okay. Thank you once again. Thank you very much.
Thank you. Thank you very much.
Okay. Then now, second talk of the session, I invite Professor Tian Li Wu.
Yes.
Am I audible to you?
So I hope everyone can hear my.
Yes.
So
the title of the talk is Reliability Challenges in GaN Powered Devices. And let me briefly introduce Professor Dr. Tian Li Wu. He is currently serving as an assistant professor at the International College of Semiconductor Technology. Before joining NCTU, he was working on power and mixed signal technologies at IMEC Belgium from 2011 to 2017, where he focused on research development of CMOS compatible 200 millimeter GaN on silicon platform for power switching applications. And his research interest on GaN, silicon carbide power semiconductor and electronics, advanced semiconductor materials and devices for sub 5 nanometer logic, industrial relevant reliability evaluation and degradation mechanism analysis, and aluminum assisted device. So now I invite Professor Wu for I request you to stick to the timings and try to finish your talk in 25 minutes, and we'll have then 5 minutes for the question answer session.
Okay, no problem. So first of all, I hope everyone can see my screen, see my slide. Okay, good. So my name is Tianli Wu. I come from the NCTU, and in this talk I will summarize reliability challenge in the GaN power device. So I summarize the literature, some part from my previous study and current study, and some part from the current literature, available literature. So first, just give an overview of the material that's suitable for the power semiconductor device. Then for sure, the first one is silicon. So silicon-based power semiconductor has been developed for a long time ago, and then there's many targets for the like for example silicon BJT, MOS, and IGBT here. And in this talk, we are actually more focused on the gallium nitride-based semiconductor. So the gallium nitride for the power device application since 2010. Since 2010, it has become a very promising material that we can use for the power switching application. And compare the material property with the other silicon and silicon carbide. So basically, gallium nitride is a wide band gap, and we have a large breakdown electric field. We have high electron saturation velocity and high electron mobility, which is due to the hand structure here. And in terms of every different aspect of the property compared with a different material. So in general, we can see that the gallium nitride can offer for high voltage application, high temperature, and the most interesting, attracting is very low on resistance due to the two-dimensional electron gap, and that's enabled for the very fast switching applications. So if you look at for the basic equation for power semiconductor device, if you look at the ideal case, consider like an anode, cathode, the diode, and once you apply the bias, then you start to have a drift region here. So the drift region can be calculated from the resistance here. And by consider breakdown voltage, which is the area of this triangular, then in the end, you can get the formula as this one, the ideal on resistance versus the breakdown voltage. And this is a very famous called the bodyguard figure of merit here. So consider the bodyguard figure of merit, you can see that this is theoretical limitation that shows that the gallium nitride can show a very superior property compared to silicon, and even better than silicon carbide. That's why the gallium nitride is very promising in terms of very lots of application, like the previous speaker has mentioned. That's good for RF, but for power is sure as well. So here, just a brief summary for how the gallium nitride high electron mobility transistor look like. So first of all, usually gallium nitride is grown on the foreign substrate. In case of silicon carbide, sulfide, and gallium nitride. And because of due to the different electronegativity compared to the gallium and then the nitrogen here, so there's already what we call the spontaneous polarization charge formation just when we grow the gallium nitride. And once we have another layer called aluminum gallium nitride, you have to consider the spontaneous polarization charge. And also in the meantime, if you put this material together, due to the lattice mismatch, so you will actually have what we call the piezoelectric polarization charge. So due to the charge, polarization charge difference between L GaN and GaN, therefore, we will start to have what we call the two-dimensional electron gap formation at the interface. And that's leading to a very high electron mobility up to like 1,500. And typically we deposit as a source strain gate metal, and then we can have the current go through. And however, the gallium nitride usually is a normally on device, so we need to have the negative bias to deplete the channel. And this is just a typical TN structure picture for the real alkaline GaN hand epi state here. In reality, however, we actually more prefer for EMO technology for the natural GaN hand, because for the integrate with power electronic system, then if we use a depletion mode device, once the gate driver fails, then we have a huge current go through, and then therefore there's a really huge damage in terms of a whole power electronic system. However, in the case of the electron EMO technology, that can be offered that to avoid the issue that I mentioned about. And so far, there's several different possibilities to have the EMO technology. So the one most popular one, which is gate reset. So reset the channel, and then we can reduce the two deck in the channel. And also we can possibly to have a flow treatment, or we can have the p-type gallium nitride, or even use some very special like piezo neutralization layer or the most hand structure. But however, so far the most popular option right now will be the gate recess, and also the using the p-GaN gap, which is a commercialized product now for gallium nitride power device. So this is the first paper that who has the first demonstrated p-GaN hand that's happened in the 2000 years. It's a p-GaN on top of L-GaN, so they can demonstrate for more than 3 volt of the threshold voltage here. And as I say here, right now the most popular the structure for the gallium nitride, which is the first one, p-GaN. So we have a p-type gallium nitride on top of L-GaN, and there's two different approach. One is blanket p-GaN, so you grow the complete blanket p-type gallium nitride, and then you etch away this one. Or we can do the regrowth of the gallium nitride only in the gate region as well. So there are several different issues as I list here. And most difficult part for the p-GaN hand is to control the magnesium diffusion, and also once we do the etching, and usually the selectivity between the gallium nitride and L-GaN is very poor. So it needs to be very carefully to determine the precise etching in this region as well. And this is the approach that right now for the commercialized product like EPC, TSMC, even for research institute like IMEC, is also we are actually working on this one. And barrier regrowth is also another very promising approach, like for the Panasonic, Infineon, IMEC also do it. And in terms of recess gate, that's more straightforward. That once we recess the gate channel, then we reduce the two deck under the gate and can realize the EMO characteristic. And so far, still many research and developed in the university level. So here, just a brief overview for the gallium nitride technology here. Then we'll move for the more main topic that we like to address today is the gallium nitride reliability. So in terms of a typical traditional gallium nitride, that's the right-hand side is a conventional gallium nitride hand. And then if you consider like the typical operation for the power device, then we will switch the device from off to on. That's usually this is curve we call the hot switching. So you have the hot switching curve like in this way. And then if you look at for the typical case with considering either mishang and peak hand, this is device structure here. So under the off state, this is a case where you have a high voltage, but you have a very low leakage current. Assuming ideally you have very low leakage current. That's easily to induce like a trapping in the buffer, or even for the trapping in the gate edge, because you have a gate edge have a very high electric field, then you have a gate edge degradation. Also the trapping in the preservation region as well. That's one of the most critical issues under the off-state situation. And then once you come to on-state, then you have the hot electron trap generations. And this is semi-on-state, so you have the hot electron trap generation, but at the meantime, you also have the possibility to have the trapping in the preservation region as well. And once you go to on-state, mainly determine your gate size stability. So in terms of a mishang or peak hand, due to the different characteristic of the gate size, so that's also leading to a different kind of the on-state instability here. So in sum, for typical Schottky gate ham, the sensitive region will be the gate to drain access region and also in the buffer from this side, because we mainly apply high drain bias from here. So this region that's sensitive to leading to some instability in gallium nitride hand. But in terms of right now, we have a new technology that's enabled for EMO power gallium nitride, especially for the mishang and peak hand here. So this one actually will lead to some extra instability that we need to worry about. Okay, so this is a summary paper that published in 2017 to summarize the reliability in terms of a different bias region of state, semi-on and on-state. And in the next shot that we can conclude this as a three different kind of the reliability challenges in the different bias region. So in terms of off-state, actually this is when we apply very high drain bias. And usually that's leading to the very famous issue in the gallium nitride is what we call the dynamic resistance, or sometimes we call it current collapse. And that's leading to the unresistant increase due to the trapping in the buffer and service. At the meantime, actually, this off-state will also leading to the threshold voltage shift. And this threshold voltage shift is due to the trapping under the gate side. So this is an issue that during the off-state. And also when we try to stress the device under the high drain bias for a while, then you have a time-dependent breakdown characteristic that need to be worried about. And this will lead into the, like for example, higher buffer leakage current and also the breakdown voltage decrease as well. And then in terms of the on-state region, the most difficult, the most challenging issue is first one is what we call the threshold voltage instability. And that's related to that you have the either positive or negative bias. So in general, we call it positive or negative bias temperature instability. Also have to consider the time-dependent breakdown characteristic, TDB here. And that's related to under the forward gate bias, you have start to have to deal with the gate current, and that's will lead into a time-dependent dielectric breakdown phenomenon as well. At the meantime, for the semi-on, actually just a combined effect that could happen both for the on-state and off-state here. So this will lead into what we call the hard carrier effect, and sometimes in the circuit level, especially during the switch transient in this region, then we will have the hard switching stress as well. So in the later slide that we will briefly introduce each of the reliability issues. So the first one is off state. And under the off state, the first one is what we call the dynamic arm. So usually call the current collapse effect. So this is typical, the curve when you do have the fresh IDVD curve here. But after the one times of the high voltage or several times of high voltage, then you can see that the current start to decrease, and which means that your resistance increase as well. And this is experimental data that the 0, 0 is a case of a fresh. But after then you stress at the minus 8 volt for 100 or minus 8 volt for 600 volt, you can see the current is highly decreased here. And this decrease is because of due to the resistance increase, which is highly dependent on your bias, your temperature, and even your stress time. And then the time between your stress and recovery. So it's very dynamic. That's why we call it dynamic arm here. So in general, the dynamic on resistance is a recoverable decrease or increase for the resistance. And then that's happens when the device switches from off state to on state. And dynamic on resistance is mainly due to the first one is service trap, and second one is buffer trap, and also the preservation effect here. So dynamic on depends on how long device is keeping off state, how fast the device is measuring on state, and temperature, and also electric field distribution in the device. So the first one trying to explain the dynamic arm that was proposed by 2010 by the Raman Venturi here, that is first proposed to explain the dynamic arm in the Schottky gate hand, which is what he called the virtual gate concept. So in general, it's just once you give the net bias, so this negative bias will inject electron and then can be actually jump to these surfaces. And once you have some surface state, and this surface state will capture your electron here, and therefore you are leading to the extra depletion of your two-day because there's formation of the virtual gate here. And this is the first proposal model to explain the dynamic arm in Schottky gate hand. So at the moment that when people realize this model, the first way trying to reduce the dynamic arm is trying to reduce the service state here. So you put the preservation, and then or improve the process and improve epitaxy, trying to reduce the service state here. And as I say that this current collapse of dynamic arm also is possibly caused by the threshold voltage shift, as shown here. This is the result that during the different of state, you can see the threshold voltage shift in the right-hand side, which means that you have a partially trapping in phase below the gate that's leading to your threshold voltage shift as well. Okay, and then this is current collapse, so trapping in the SS region. So, and then usually when we consider the under the off state, you have the trapping in the this region, and that will leading to resistance increase as shown here. So that's also one of the results that leading to the during the high voltage off state. And in order to solve this issue, there are so many papers trying to explain how to improve the dynamic arm. So the first way people try to deal with is find the best way to have the good preservation to reduce the interface state here. So in this case, you can see that the people propose use the in situ silicon nitride, and they can have the very stable resistance increase in the room temperature and high temperature as well. Or you can have some other dielectric here, like aluminum nitride, which is a case that can also reduce your resistance, dynamic resistance as well. But I have to remind that so far there's still not reached the consensus of which dielectric is the best, because of the this also depends on your process and the accuracy quality as well. And but the one most useful way try to improve dynamic arm is for sure to have the field plate. So as you see that in this paper they compare with dual field plate and single field plate here. So they can see that dual field plate can have the very small resistance increase up to 300 volt compared to single field plate here. And this is more recently the paper that was published, and they have the more sophisticated field plate design with gate and soft field plate 1 and soft field plate 2. And the end, they can get different field plate design. They can always get a low dynamic arm. So the field plate for sure is very important to optimize the electric field that can reduce the dynamic arc here. And then also dynamic arc might be due to the buck trap here. So buck trap, which is, as we know that usually in the power device, we need to make the buffer as a semi-insulating, then we need to have the carbon doping. And then carbon doping actually will affect the dynamic arc as well. So usually the result is leading that we have higher carbon doping for the high breakdown, but also bad for dynamic arc. So this is a nice study, shows that as you increase of your carbon doping, and then actually you can start to see that your breakdown strength can increase, but at the meantime your arm resistance increase as well. Is anyone still following? Because my computer is kind of like have the slow down the transit.
It's okay, you're fine.
Yes, just wait a moment. Okay, so another effect is the time-dependent breakdowns. I say that during the stress for a long time, that you will start to see the leak current will be increased, as shown in the middle graph here, and then therefore that's will lead into that you have the TDB effect as well. So that not only happen in the case of the DRAM side. Actually, when you see a stress device for a longer time, that's also in the case for the buffer also will be able to show that the TD effect as well. So the high voltage stress also leading to a very high buffer leakage as shown here. So you can see this is clearly the TD effect here. So you need to make the device very robust. We also need to consider the buffer TDB in order to make sure that the buffer can sustain at enough voltage that you want. So in this case, they stress the device at the 800 volt, and they can prove that this device for the 600 volt can still guarantee for more than 20 years of lifetime. And that's also related to the one of the important qualification, which is what we call the high temperature reverse bias here. So high temperature reverse bias is another way to evaluate the TDDB and also the long-term stability. So this is some accompanying data that they want to show that when they do the high temperature reverse bias, in this case they stress at the VDS 520 volt at 150 Celsius degree, which like 1,000 hours, they can show the very stable characteristic in terms of the threshold voltage and the ID, and this is data set for the Panasonic as well. Okay, then we move for the threshold voltage, the unstable reliability issue. So unstable is that the most famous one is that we have what we call the BTI in the mishap here. So BTI is when we have the sweep the device from forward to reverse, you can see that apparently there's a hysteresis here. And this hysteresis is highly related to your bias and temperature. And that's why we call this as a bias temperature instability. And this is recoverable, and this is due to a trap at the dielectric or 3-5 interface. So this is an example that we compare with two different dielectric, one is silicon nitride, one is aluminum oxide, and we can try to extrapolate the effective charge density, then can lead into these gamma factors. As you can see, that the silicon nitride is more easy to get the trapping compared to the aluminum oxide. And then based on this paper, we propose a model to explain like the reason why that the silicon nitride is more trapping. This is mainly because of the low gamma, which indicate that you have the wide defect distribution, and this is very close to your conduction band. But for the high gamma, it means that you have a narrow trap defect distribution, but it's far away from your Fermi level. So then in terms of the bias temperature instability in pig and hen is relatively complicated here, because in here we can see that this is experimental data. When we do the stress, you see the negative shift, but at the meantime, you start to see the positive shift here. And this indicates that they both have what we call electron trapping here. But at meantime, because of you have the pecan, so you have the full of a hole in this region as well. And that will have the 2D hole gas accumulation, and this also leading to the hole trapping effect as well. So the combination of the electron trapping and hole trapping will lead into sometimes you have a negative shift and sometimes you have a positive shift in the p-type gallium nitride hand. And we can see that this paper that also proposed, this is another paper that proposed using the same way that first you have the hole trapping and you have electron trapping as well. So in this paper, they study the different aging of cyborg. They say that in the end they can reach the stable of the hysteresis as long as they improve the sideward aging. And consider the forward gate bias TDB in this hand here, then we have the series of experiments in here. We compare with different recessed depths in the TDB, and then we can start to have this TDB graph here. And in terms of this TDB graph, we analyze the TDB result, and actually we found out that in the case of the fully recessed, you have the actually much close of your sidewall in the edge compared to the center here. And that's leading to this could be the possible easy to form the population path, and therefore this is something need to be worried for the recessed gate in his hand. And in terms of the pecan hand, the breakdown mechanism, then first we look out for the positive temperature dependency, so we can find out that the device, once we switch to the different voltage with a different temperature, we have how we have the, as long as the temperature increases, there's a higher breakdown voltage. And we'll propose a average breakdown under the forward gate bias to explain this one. So once we apply the positive gate bias, then we will have the extension of the pecan hand, and then this leading to the electron injection in this depletion region, and thus can be leading to the impermeabilization, and that's why we have a positive temperature dependency here. So this is a more recent study show that in the case of pecan hand, if you compare different magnesium concentration, then high magnesium concentration is always leading to the high leach current, and that's because of in the high magnesium you can actually have this very narrow depletion width between your gate diameter and pecan hand, and that's why it's become a challenge for the pecan device to reduce gate leach current, and this for sure that will influence. This is for sure will influence your TDDB result here. So due to the time limit, so I will
conclude in 2-3 minutes.
Okay, so no problem. So I will conclude that this is the last one. I will show the hard switching and hard carrier effect here. So I will quickly look at this one. So in terms of trying to validate the gallium nitride power device, so researchers start to work on to really like hard switching stress on the device to see that how the device actually can have the different stability here. So this is comparison between the typical pulse IV, and by considering the hard switching, you can find out that hard switching is always has a higher dynamic arm increase compared to typical pulse IV, and therefore this leading to a different industry trying to propose a different testing vehicle, trying to in order to testing the hard switching effect in the gallium nitride power device here. Okay, so due to the time limit, my presentation will be stopped here, and I will be like to acknowledgement for all the research in my group is supported by the MOST and then in Taiwan and MOE in Taiwan, and this is a collaboration we have with a different group in the world. Especially, I want to highlight that we have already collaboration with IIT Delhi, IIT Bombay, and IIT Kanpur. From the NCTU, we have many Indian students working with us, also in my group as well. So we all welcome to have a further deep collaboration with the Indian friends here. Thank you for your attention.
Thank you, Dr. Wu, for an excellent talk and sticking to the timings. We can quickly have 1 or 2 questions.
Before I open my talk, I forgot to say the namaste in the beginning.
let us move to the third talk of the session, and that is to be delivered by Professor S. Raghavan. And title of the talk is Growth, Microstructure, Device Performance Correlations for 3-nitride Optoelectronic and Power Devices on Sapphire and Silicon. I'll just briefly, Professor Raghavan, although he's well known in the 3-nitride fraternity, Professor Raghavan, metallurgist and materials engineer by training who enjoys working at the interface between the world of materials and that of systems. Professor Raghavan, over to you.
Thank you, Dr. Raval. Can you see my screen?
Yes, it is visible.
Okay. And I have, you said 25 minutes, right?
In 5 minutes for the discussion.
Excellent. Thank you. So I thank the organizers and particularly Dr. Rajendra Singh from IIT Delhi for the invitation. And I also commend them for conducting this conference in spite of the current situation. My name is Vasu. As Dr. Raval just pointed out, thank you for that kind introduction. And while a lot of the talks prior to this one have been predominantly device heavy, apart from the first one where Dr. Seema Vinayak from SSPL discussed the importance of growth, it is my duty to move the focus to the growth aspect of these 3-nitride applications. And as I mentioned in the tutorial yesterday, it is so difficult and it is so important in having enabled this technology that it for all practical purposes got the Nobel Prize. So a big fraction of what Akasaki, Amano, and Nakamura did was in the growth domain. So acknowledgements to MITI, the Department of Science and Technology, and MHRD for the funding. And we work as a group here in IISc along with all the students, Professor Digvijay Nath, who gave the first talk in this session, Dr. Muralidharan, and myself. And so a lot of the work I'll be presenting is the outcome of a collaborative effort. What I would definitely like to tell you is that if it had not been for this collaborative effort, I was basically developing material in the blind. And unless and until you look at how the material performs at the device end of things, it for the most part is useless, right? So we've all heard of GaN HEMTs. So I'm going to jump into the fray right away. I won't tell you why GaN HEMTs are important, power, RF applications, and so on and so forth. And while GaN for RF is done on silicon carbide, GaN for power, because of cost considerations, is done on silicon. And let me just get rid of this video here. Yeah. So if you take this paper that was published in the Japanese Journal of Applied Physics in 2019, it's a fantastic paper. It is from onsemi, and it gives you a feel for the state of the art in this field. So if you would take a typical GaN stack on silicon, so this is what I'm showing you here in the right-hand corner of your screen, or the right-hand part of your screen. So you have a GaN stack. Of course, the AlGaN-GaN interface at which the 2-deck forms is right up there, and this is where all the action happens as far as lateral devices are concerned. It is grown on a silicon stack, silicon substrate, typically about 2 millimeters thick these days. And on top of this silicon stack, you grow a GaN stack that is of the order of about anywhere from 4 to 6 microns. Okay. And as you can see, between the silicon stack and the point at the top where a lot of action happens, there are many, many, many things in between. And very often when especially you're a device engineer and you take these stacks, you just see one gray rectangle and you treat that as a black box and you move on. But trust me, that there is a zoo in there. And what I'm going to tell you as part of my talk is that we discovered, and in rather the hard way, that there are all kinds of defects that are hidden all over this stack, and not just your threading dislocations that GaN is known for, including VPITs, point defects, and so on, that impact the device interface that is always the top part of this whole stack. Okay. And to give you a feel for the fact that, and most of these things, actually all of these things you can only control during growth. Once you're done growing and you're cooling down to room temperature, you can't do anything about it. You have the wafer, you run with it. And what you see on the left-hand side is what happens when you're monitoring the curvature or bow of this wafer as this stack is being grown. As you can see, it's a rather complicated graph where on the y-axis they have plotted curvature, on the x-axis they have plotted time. Ideally, it should be stress thickness versus thickness. And since this is a paper from industry, they have intentionally kept it as curvature versus time so that a lot of the information that you could have otherwise gleaned if it had been a stress thickness versus a thickness plot cannot be done. But regardless of that, what it shows you is that from the time the wafer starts growing all the way at this bottom till it's completed, there are many, many things that are happening in there which are causing this change in curvature. Why is the wafer curving? Because there's a film that's growing on top of it that is stressed. Okay, and because there is stress, the wafer is bowing, and this stress is changing. Why is this stress changing? The stress is changing because there's a microstructure in there that is evolving, and you have to understand. And this microstructure is what is constituted by the defects I was telling you, which in turn impacts your device performance. All the way from leakage, current collapse, what have you, the sheet resistance at the top, that all the folks who work, reliability, which the previous speaker spoke about, it impacts all of those. And after, you have to understand how all of these contribute to the way the wafer curvature is changing, such that when you cool back to room temperature, if you see at this point, the curvature has come close to zero, which means you have to present the person who's making the device with a flat wafer. As mundane as it may seem to everybody, oh, a flat wafer, fact remains that unless and until you understand the science behind all the processes that are happening during growth, and unless you're able to control it in real time, you will neither be able to achieve your technological requirement of a flat wafer on which you can put devices in the first place, nor will you be able to meet your technological requirements of reliability or how the device is going to perform. Okay, so if you're a device engineer and you're thinking that this is a black box with nothing in there, think so at your own peril, because if you take a cross section of what I showed you in the previous slide and look at it in a TEM, you will see there are all kinds of defects in there. I'll show more during the course of my presentation, a lot of which starts at this interface at the very bottom there with the substrate. So here the substrate is there. This is the silicon, and growth has happened in this direction. And this is unfortunately the way things are. I mean, nature is what it is. Silicon is what it is. Gallium nitride is what it is. And technology demands that you grow gallium nitride on silicon. Well, there are certain interfacial energies that you can't do away with. So gallium nitride will start growing on silicon with a certain set of defects that are nucleated at that interface, which then have to be brought down to manageable levels at the top so that your device will work. So for example, if you were to measure the stress I was showing you in the previous graph, the stress thickness, the curvature versus time plot, and if you converted that into a stress versus thickness plot, and that is what helps us understand the physics of growth that is happening, you can see from my animation there that in each one of those layers, the stress is changing significantly. I mean, if you look at the initial layers here, which are aluminum nitride or algan, the stress is heavily tensile, 1 gigapascals. At times it goes up to 2 gigapascals, and it's changing. In these algan layers that are there subsequently, the stress is heavily compressive. It goes all the way down to minus 2 gigapascals, and even there it is changing. Why is the stress changing? Because the microstructure is evolving. So in this fashion, by understanding how stress is changing, you can understand how microstructure evolves. If you can correlate that microstructure with the way your device performs, you can go back to growth to change conditions to get the microstructure that you want. And that's essentially what we do in our group. Okay. So in order to tell you the complete story, I don't have a choice but to, and we have been working on this for many, many years now, start right from the beginning, which is the interface with the silicon substrate. Even though I have presented it at previous conferences, it's important enough that I just spend one slide on it. So a long time back, we used to try growing these wafers on silicon, and this is actually a rather old paper that was published in 2013, and everything being the same. Everything absolutely being the same. One day the wafer would come out looking like the one on the left. Fantastic, nice, shiny, smooth wafer on which you can put down nice devices. Mobility 2200, or not 2200, close to 2000, somewhere between 1500 and 2000. But on other days, the wafer would come looking out as if, it's the surface of the moon. That's the wafer on the right. So when we had dug into it back then, we had found out that a lot of importance needs to be paid into the way the silicon wafer is cleaned. So as we know, all silicon wafers have an amorphous oxide layer on top. So of course you have to clean the amorphous oxide layer, because if you didn't clean it enough, the gallium nitride that has to grow on top of it epitaxially will not grow epitaxially, and therefore you get a polycrystalline gallium nitride and the surface is rough. However, what we found out, much to our dismay, was that even if you clean the wafer out very well, which is what you see at the top there, even then it would come looking out rather, rough. So you had to clean the wafer just enough such that you remove the silicon oxide layer that is there on top. At the same time, not over clean it. In over cleaning it, we would introduce pits. Now, if you have a good PhD student who does the exact same thing day in and day out, it is fantastic, right? You just have to dip the silicon wafer into your etching solution exactly for 5 seconds and take it out. Well, that's not how engineering works. So luckily, what we then found out was that if you measure the stress and the stress in the aluminum nitride at the very bottom, and for a aluminum nitride that would grow well, that in turn would result in the subsequent 2 microns of growth, such that you would get a smooth wafer. The optimum amount of cleaning would result in an aluminum nitride with very large values of stress. Okay, so here I have different dots here. Each one is for a different type of cleaning. Of course, we have that optimized now. It's a highly empirical process. But the point is that within the first 50 nanometers of growth, you had a signature of whether or not your subsequent 5 hours of growth is going to happen well or not, just by looking at the stress signature. The stress was very large. You would grow very good quality aluminum nitride, on top of which you would be able to grow your hem structure. If the stress was low, you wouldn't be able to do it. So you can look up this APL paper to understand why a high value of stress can be correlated to a good quality of aluminum nitride. Okay, so like I told you, it starts with that interface. Okay, then we had optimized that. Everything was nice and fine. We would start getting nice shiny wafers. Till one day, a student of mine decided that he had enough with GaN algan. You see, the problem with GaN is, especially on silicon, that you grow a lot of aluminum nitride algan and you grow a very thick layer of GaN on top. Very often, a lot of healing of defects happens in that GaN layer. And therefore, your top looks nice and smooth, and you put your devices and you forget, and you don't think about what might be there a few microns below, what defects might be there that is contributing to your background, a breakdown and stuff like that. By the way, I used to think that this is a problem only in silicon and silicon carbide for folks who worked on silicon carbide, along the lines of, for example, what Dr. Renu Tyagi and team have put together in SSPL. Life was easier, right? It's much easier to grow GaN and silicon carbide. But recently, there's a company called Swigan that has come out with growing very good layers on silicon carbide, and they show that even the quality on silicon carbide can be further improved if you pay attention to this very thin layer right at the beginning of growth. It's a very nice piece of work, and if those of you who are working on GaN on silicon carbide, If you've not looked up their work, I urge you to look it up. In any case, everybody was working on GAN, so nobody thought twice about it until a student of mine, Abhi, decided that he wanted to look at algan hems. He said, forget GAN algan, I want to study algan hems. So now what we had to do was we had to stop growth at algan. We didn't have the luxury of growing a few microns of GAN, in which, as I was telling you, a lot of this defect healing would happen. So what Avik found out was, even though if you clean the substrate the way I just showed you very nicely, very well, very large stresses, the way Harish, one of the former students, had done, if you grow this aluminum nitride layer at a single temperature, which is 1050 degrees C, then its surface, all said and done, was rough, like I'm showing you there. So if you looked at the surface of this aluminum nitride film, it would look like the one below here, where the surface roughness, as you can see, is much larger. And then if you grew thick layers of algan on it, mind you, not GAN, and the problem with growing algan is that the surface diffusivities in algan are not as high as they are in GAN, relatively speaking. So in general, alloys that are rich in aluminum nitride or algan-rich alloys, grow better at higher temperatures. What do I mean by higher temperatures? GAN itself grows at 1000. And you must have heard of sputtered algan being made by annealing it at 1800, sorry. So while GAN prefers 1000, aluminum nitride probably prefers something closer to 1400 if you had a reactor that could go up to those temperatures. And as you go up in higher aluminum contents, you have to go that much higher in temperature. So what Abhik found out was that, okay, if I want to grow to a higher temperature to grow aluminum nitride on silicon right away, so if I take my wafer whose surface is silicon to 1150 right away to grow aluminum nitride, I have a problem. The surface of silicon gets damaged. But if I now have a lower temperature, the problem is the aluminum nitride surface is rough. So what do I do? So then he came up with this method of what we now call, it's uncannily similar to growth on sapphire, LT, aluminum nitride on silicon. By the way, there are others also who have reported it. We are not the only ones. But through this work, as a crystal grower, I managed to get some insight into what is really happening there. So if you now use this combination of a thin 1050C layer, that will ensure that the silicon surface gets covered before it can get damaged. And then you raise the temperature to 1150. You then ensure that you grow aluminum nitride that is relatively smooth, okay, which now has a much lower surface roughness, as you can see, of 0.71 nanometers versus 5.11. And if you actually look at the cross section in a TEM, yes? Hello? Hello, is there a question? Hello? Okay. Can everybody hear me?
No, go ahead.
Okay. So indeed, if you now grew your aluminum nitride or this algan layer, hello, am I audible?
Yes.
Okay.
Very
For
much
some
audible.
reason, I'm getting an alarm at my end. I'm getting this ping, and it's not coming from my computer. Okay. Is everybody hearing that music, or is it just me? Okay, that's gone away now. Thanks. So as I was saying, that if you now grew a algan layer, mind you, I'm not growing GAN on top of it. And this is also what you need for growing UV structures, okay? UVA, B, C, and so on and so forth. That when you now grow it on a aluminum nitride layer that is grown at a single temperature, At the very bottom below, there is surface roughness. And this surface roughness doesn't get removed, it gets accentuated as you go to your algan. Okay. Okay, the music is back. I don't think it is from my end. Dr. Rawal, do you hear that music?
No, there is no music.
Okay. I hear that as if somebody is trying to connect to the web.
No, it is somebody is muting, unmuting their mic. It is because of that. You please go ahead.
Okay. So what we then found out was that, on the other hand, if you now grow this algan layer on a 1T plus 2T aluminum nitride buffer, where the aluminum nitride at the bottom is smooth, then the algan that grows on top of it is also smooth. Now, what do these roughness constitute? They constitute actually what are also called as VPITs. Okay, and these VPITs are sources of leakage in power devices. Now, even though people were aware that VPITs are sources of leakage in power devices, and we always had this question of where they arise from, and still the debate rages in the literature as to what their sources are. But it appears that one such source is the roughness in the aluminum nitride layer, which is grown at low temperatures. Now, of course, if you grow GAN on top of this algan to grow your hem structure, these VPITs might get smoothened out at the very top. But mind you, they are in the algan, buried below the surface, and below each one of these pits, there are defects or dislocations that could act as leakage paths, or there could be local concentration of oxygen, as I will tell you, that could also result in an increase in the local background carrier concentration. So when one of the students who was working on UV, along with Professor Digvijay Nath, we had these students Shashwat and Anisha who were looking at UV detectors. They said, okay, you have this nice algan on silicon, so why don't I put some back-to-back Schottky diodes on it using this interdigitated structure and start looking for leakage. So they put it on this AL25, and those of you who work on HEMTs on silicon will realize that this kind of a graded structure is very common in even GaN HEMTs on silicon. So before doing the UV measurements, when they looked at the surface of this algan in an AFM, they saw the ones that were grown on just the low temperature aluminum nitride, no 1T plus 2T, had a lot of pits on the surface. That which was grown on the LT plus HT aluminum nitride, the one that is there, did not have these pits on the surface. While I will not go through the details of the dark current photo response and so on and so forth, the details of which you can find in that paper there, from the point of view of characterizing as a UV device, what we did see was in going from sample A, which had just this one temperature aluminum nitride, which in turn resulted in rough surfaces and these pits, to sample B, which was now grown on this smooth aluminum nitride, there is a sharp drop. Sorry, this is the dark current. There is a sharp drop in the dark current as a function of applied bias. So this was done, of course, for UV applications. Now, in the case of UV, you look upon it as dark current. Now, the same phenomena can constitute leakage paths when you're looking at it for power applications in HEMTs. And they, of course, also looked at it using a conductive AFM. And indeed, when you use a conductive AFM, you find out that close to these pits are where your leakage paths are. So the image at the top here is the topographic image. The image at the bottom is the current image. And around where the pits are, you can see the current is higher. I should have probably put the scale there, but it's probably about 10 to 20 times higher than the background current. Okay. Now, mind you, we had earlier published a paper in which the same group, which was looking at UV devices, had shown that if you grow GaN on sapphire, now this is GaN on sapphire, okay, this is, or AlGaN on sapphire, not AlGaN on silicon. So far I was talking of AlGaN on silicon, and I'm kind of flipping back and forth because as a grower, I see them all in a holistic way as opposed to being very separate entities. So when they were doing AlGaN on sapphire for UV applications, the same group had seen that when you decrease the full width half maximum as we know it of the symmetric 002 peak, which in turn results in a order of magnitude reduction in screw dislocations, there is a big reduction in the dark current. This is for UV again. So the question was that this phenomena that we were seeing on silicon, is it again due to screw dislocations or is it something else? So we did, of course, look at the screw dislocation density. And we came to the conclusion that this drop in leakage that you're seeing on silicon cannot be completely attributed to a screw dislocation density alone. We didn't have as much of a difference between these two samples in terms of your full width half maximum of the symmetric scan. Okay. I'm assuming that I'm speaking to an audience that is well versed in gallium nitride technology, and therefore I'm going into the basics of what a 002 full width half maximum is versus what a 102 full width half maximum is. So then we thought, okay, if these things are contributing to dark current in UV on silicon, they're probably going to also contribute to leakage in HEMTs. So this is when then we did a series of runs where we took a silicon substrate. We grew this 1T plus 2T aluminum nitride, 1T and 2T aluminum nitride. 1T stands for 1 temperature, that is 1050. 2T stands for 2 temperatures, 1050 and 1150. Remember, 1T gives you a rough surface and pits that are embedded in this stack at various depths, even though the top will look very smooth. And 2T results in a reduction in pits throughout. Okay. The whole reason why we went all the way to the HEMT was to make sure that we are measuring leakage also through ohmic contacts and not only through Schottky contacts. This is a busy slide here, but what you indeed see, the top row is for growth that was done on the 2T stack. The bottom row is for growth that was done on the 1T stack. Now, across all these figures, so in this case, this is just the plain aluminum nitride. You see the stack that has grown using a 2 temperature has less surface roughness, less defects at that point versus a 1T stack that is very rough and has a lot of defects. You go all the way to GaN, the one that has grown on the 2T stack has none of these deep pits, as you can see from this AFM image. The stack that has grown on the 1T stack, you start seeing these deep pits. You stop at various points in the AlGaN.
Request to in 2-3 minutes.
Oh, wow. Okay. AL75, AL50, or AL25. You see the degree or number of pits goes on decreasing. Okay, when you go from 1T to 2T. Indeed, if you look at it a little more closely, you will see the same again. So what we therefore see is that when you grow the HEMT stack on 1T, the leakage is much larger as opposed to when you grow it on 2T. So that is a mantra. Even though at the top the stacks look very similar, buried within the stack are many defects, and these defects contribute to leakage, which is lower in the stacks that were grown on 1T plus 2T. So why does this happen, among other things? So it is well known in the literature that these V pits actually have facets on which it's easier for oxygen from the growth surface to absorb. And indeed, when we do a SIMS, we see that in stacks which are grown on the 1T stack, especially in the AlGaN, the oxygen concentration is higher than in stacks that are grown on 2T. And remember, this is average oxygen concentration. So if you then divide it by the number of possible pits and the concentration around there, we get oxygen concentrations of the order of 10 power 18 per centimeter cube or so. Now it doesn't stop there. So if Dr. Rawal, I might have just another minute. So I told you that I told you that we engineered the silicon surface. Then we engineered the aluminum nitride and then grew the whole stack on top. It doesn't stop there. After that, we now have started engineering the AlGaN, and this requires a lot of painstaking growth work. And this is from the work of Naina Ramesh that's not unpublished. By changing the temperature of growth and the extent of carbon incorporation, the problem is that there is a give and take there. Higher the temperature you go to, smoother is the surface, especially for AlGaN, but lower is the carbon incorporation. You go to lower temperatures, the surface roughens, but the carbon incorporation is more, and carbon is incorporated, as you know, to take care of the background oxygen in GaN. So by using a combination of all of these in the recipe, recently we have managed to now vertical leakage, I'll come to it later, on hemmed stacks. We have managed to go significantly up in the voltage that our stacks are able to withstand. And among the thinnest of stacks, we have been able to demonstrate breakdown fields, vertical breakdown fields of the order of 2 megavolt per centimeter, which is probably state of the art. As you know, breakdown fields in GaN is about 3 megavolt per centimeter, and state of the art in the world is around 1.5 to 2. And we have managed to do that in among the thinnest of stacks. I'm going to skip this. This is work done on Sapphire that I was going to do. Why is this important? The reason all of this is important is that silicon, the substrate on which you grow, as you raise the temperature to 1000 degrees or so, its yield strength drops precipitously. It's about 3 megapascals at 1000 degrees, which is the temperature at which we grow our samples. Now, if you ask now when your wafer bends or curves, you can then calculate the curvature, because when the wafer curves, it puts a stress on the silicon, and then the silicon can buckle and we actually see it. So when I'm growing all this stack on top of the silicon, and I have to grow it to also manage the defects in there, at the same time, I have to ensure that the curvature of the stack, which is due to the combination of the stress and the thickness that is there, is not so large that the substrate will buckle, and we do indeed see it happening. And yet to deliver a wafer to the device person such that leakage is low, and then once you take care of leakage, they will say, give me low sheet resistance, you give them that, then they will say, give me low current collapse, and of course the result is endless. So the summary of my story is that to enable good device performance at the top, which is what the average device person sees, it depends on many embedded defects in the stack. It's below the surface. And especially if you're a device engineer, you should keep that in mind. These in turn have their origins at the bottom and all the way to the interface with the substrate. So thank you for your time, and I hope I have given you an overview of the perspective from the grower. Thank you, Ravalji.
Thank you, Professor Vasu, for an excellent talk. Now we have time for one or two questions, if there are any.
I can't see the hand, so if you have any questions, I need you to interpret it for me.
Yeah, even no question. You can ask your questions in chat box. So if questions, let us thank again Professor Vasu for an excellent and illuminating talk. Thank you very much.
Sure, you're welcome.
And by ending this third talk, now we close this session, and maybe we will rejoin for the poster session after tea break. Thank you very much.
Thank you.
बोल सकते हैं बोल सकते हैं क्वेश्चन पूछ सकते हैं कि आपने जो कराई थी ना कल सर, आपकी वाली सही कर दी, उसमें जान आ गई। कल का आप लाने को आ जाएगा। Hello, Mr. Avinash. Can you please stop sharing the screen right now?
Okay. Yeah, I stopped it.
Okay, thank you. Dear all, please be ready with your posters. And when the examiners will come and ask for the posters to display, then at the time you can display the required posters. The examiners will ask specific questions if they have, and at the same time you can display. Please be waiting. Hey, Madan, are you able to hear me? Can you please share your poster now?
Yes, sir. Yes, sir. So I have to share.
No, we have shared already. Can you speak something
Okay.
for 2 minutes about your poster now?
Okay. So this is about the layer transfer of silicon carbide samples. So we all know that silicon carbide is a very promising material for power electronics, but the problem is the cost of silicon carbide, and that cost is because of the silicon carbide substrates are very costly. So there is a one way, that is smart cut technology, by which we can reduce the cost of silicon carbide substrate by the transferring silicon carbide from one substrate to another substrate. So this is the complete process in which first hydrogen atoms ions are implanted in the sample, sorry, in the wafer, and then another wafer is bonded with that implanted wafer, and that this complete stack is annealed at higher temperature, and we can exfoliate this desired thickness of the sample. So but for this complete technology, we have to optimize parameters like implantation parameters and annealing parameters. So here we have optimized annealing parameters for large area exfoliation. So this is the as implanted sample in which hydrogen atoms ions are implanted by 5 into 10 to the power 16 with fluence and 70 kV hydrogen ions. Sir, I am getting some noise.
तो मेरी मेरी बारी बारी है अंदर शोर हो इसलिए डॉक्टर ने अच्छे कहाँ गए हुए मैंने देखा है सही है
Sir, I am getting some noise.
Can you please other participants please mute your voice?
Okay, so just I am telling about this smart cut technology by which we can reduce the cost of any substrate. So for this layer transfer, we have to optimize lots of parameters like implantation parameters and annealing parameters. So here we have optimized annealing parameters for large area exfoliation. So this is as implanted sample, and this sample is annealed in the two-step process. The first at 500 degrees Celsius for a long time period of 50 hours, and then we anneal the sample at 1100 degrees Celsius for 30 minutes. So by which we can optimize that we get the 500 micron exfoliation. So this is the formation of blisters, and this is the AFM image of blisters and exfoliated region. And this is the STM image of the damaged region. So actually when we implant the hydrogen atoms inside the material, so it creates some kind of damage inside that. So this is the region where this damaged region is created because of the defects. Because of these defects, some stress is produced inside the material. So from this HRXRD, you can see that this different circular peaks or Gaussian peaks shows the strain profile, and this maximum peak, this is around, this is near to the this zero strain peak. This shows the maximum strain, and from this second image, you can see that this maximum stress is around 395 nanometer. So that 395 nanometer is thickness is in this that lies in this damaged region. It means you can see that this in this damaged region the maximum strain is produced. So this is some conclusion that this large area exfoliation can be achieved by this two-step annealing process, or we have also studied this strain profile using the HRXRD. So this process can be used to for the smart cut process of silicon carbide on insulators. So this is
Thank you,
SiC
Madan.
technology.
Thank you.
Okay, sir.
Thank you. All the other parts we will share from our side, just in the serial number. Now poster 3, they can display. We will display. They can speak for 2 minutes about their poster. Please be strict to the time. Poster 3, Dr. Monu Mishra. Okay, if he is not there, Dr. Monu Sharma, if he is not there, next is Miss Minal Rajesh Gupta, optical properties of wide band gap material, lanthanum substituted CO2. Can you please talk for your a poster for 2 minutes. Miss Minal Rajesh Gupta, are you there? If you are not there, we are proceeding for the next poster P5. Mrs. Barnali Patak, Studies on Chemical Synthesis and Characterization of ZNO PBO by ZNO core shell. We are sharing from our side. Please speak about your poster for a couple of minutes. If Ms. Barnali Patak is not there, we are proceeding for the P6. Mr. Palwal Avinash is reacting ion etching optimization for laser diode facet fabrication. We are displaying it. Please speak for a couple of minutes.
Should I share my poster, sir?
We are sharing from our end. You don't need to do anything.
Okay. So in this work, we have carried out reactive ion etching experiments for optimizing the surface roughness and the etch rate of in order to fabricate the laser diode facets. So in case of laser diodes, it is the epitaxy is grown on the sapphire substrate. It is required to obtain the smooth facets. So it is not possible by cleaving it in sapphire substrate, because there is a it could not be cleaved on sapphire substrate. So we have carried out reactive ion etching experiments for this fabricating the facets. So initially the mask was transferred on the hard mask. SiO2 was used as the hard mask, and this SiO2 hard mask was first etched with the CF4 and oxygen plasma, and then this hard mask is used for gallium nitride reactive ion etching. And in gallium nitride reactive ion etching, we used chlorine VCl3 chemistry, and the flow of chlorine is set as 7 SCCM, and VCl3 flow was set as 3 SCCM. And we have varied the argon flow, and by varying the argon flow from 0 SCCM to 12 SCCM, we obtained optimum results at 8 SCCM of argon. So this AFM images are these step height was measured with the DECTEC surface profiler, and from that the H rate was estimated, and the RMS roughness was obtained from the AFM AFM. This RMS roughness, surface roughness, was obtained from the AFM microscopy. So in conclusion, the optimum results are obtained for 8 SCCM of argon, and now we are optimizing it for the we are studying the effect of variation in chlorine and BCl3 plasma on the surface roughness and this H rate. So that's it, sir.
Okay, thank you. Now we are proceeding to 7th Miss Damanpreet Kaur, effect of swift heavy ion irradiation on gallium oxide thin films and photodetectors thereof. Please speak for
Hello everyone. Yeah, am I audible? Hello.
Yes,
Hello?
you are audible to everyone.
Okay,
Please speak for
fine.
2 minutes.
Okay. Good afternoon, everyone. My name is Damanpreet Kaur, and the title of my poster is Effect of Swift Heavy Ion Irradiation on Gallium Oxide Thin Films and Photodetectors thereof. Here we have studied the effect which the SHI, which are massive ions, has on semiconductor gallium oxide, which is a wide bandgap semiconductor, and it is intrinsically solar blind, and hence it can be used for fabricating solar blind photodetectors. Why we chose SHI is because SHI is shown to cause material modifications such as defect annealing in SiC, which is another wide band gap semiconductor. So what we did was we deposited gallium oxide thin films, both amorphous as well as polycrystalline, and then we irradiated it with swift heavy ions of Ag7 plus with 100 MeV energy. And what we found out was that both the amorphous as well as the polycrystalline thin films and their photodetectors showed structural modifications in their thin film morphology. There was a sort of nanoporous structure which was formed in amorphous thin films, while the polycrystalline film showed a destruction of visible larger crystallites. We found that that the photodetector performance it degraded with the incidence of irradiation, the SHI irradiation, and we could attribute it to the thermal spike model of swift heavy ions, and it was found that the major energy loss in the thin film was because of electronic energy losses, and we carried out the photoluminescence studies to find out that there was a reduction in optical defect density, and thus it showed that there is annealing of pre-existing defects, due to which the performance degraded, and the performance could be recovered by annealing at moderate temperatures of about 250 degrees Celsius. So this study, it provides the guidelines to develop gallium oxide based solar blind photodetectors, which showed excellent radiation hardness against the swift heavy ions, and thus they can be used for extreme environment applications, and it paves the way for using the swift heavy ions as a tool for defect engineering. That will be all from my side, sir.
Thank you. We're moving to the poster 8, Mr. Ram Shankar L. Performance enhancement of cerium oxide thin film based oxygen sensors via TiO2 doping.
Oh, hi, excuse me. Is someone moderating this session? Hello. Am I audible?
Yes,
No, Dr.
you
Ashito.
are. I'm Dr. D.S. Rawal. We both are, I think, supposed to rate 1 to 15 posters.
Yeah, actually, yeah, sorry, I'm a bit late.
Mail
So
from the organizers that we have to evaluate the posters on the basis of the PDF files have been sent to us, and
yeah,
we have
so
to rate them out of 20.
yeah, so the PDF files I have right now. So what is like, so as per the evaluation, they are briefly explaining the work they are doing, right? And at the end of the their explanation,
If
we
you
can
feel like
ask one or
asking, you
two
can
questions
ask
if we
questions.
want.
Otherwise,
Yeah. Okay, I understood. Okay, so this Ram Shankar, please go on.
If Ramshankar N is not available, we are proceeding for the next one.
Yep.
Miss Shubhagi, atomic layer deposition of titanium oxide thin films at an ultra low temperature of 50 to 120 degrees Celsius using titanium oxide as precursor.
Good evening, all. Am I audible?
Yes.
Okay. So in the work which we are presenting here today is over atomic layer deposition of TiO2 at ultra low temperature using tert butoxide as one of the precursor. The challenges, why am I going forward with this is that we know that perovskite solar cells is one of the emerging technologies where perovskite tends to degrade at higher deposition temperature. So if and we use TiO2 as one of the electron transport layer in solar cells, perovskite solar cells. So if we deposit, so the issue one here highlighted as shown in the poster is that if we deposit ETL at high temperature, that is TiO2, which is commonly deposited at temperatures higher than 250 degrees Celsius or so, we cannot deposit them on flexible substrates. They will degrade. Another issue is that perovskite tends to degrade at high temperature. So if we go for PIN architecture, we cannot deposit TiO2 over perovskites. In order to address these challenges, we have tried to go for low temperature deposition technique, of ETL using ALD. The precursors which we have used is titanium tetrodoxide and water. We can see the chemical reaction which will proceed in the given manner in the poster. The recipe which we have tried to optimize here and come up with requires the optimization of the dosage time of tert butoxide and water, which are being alternatively fed in, along with nitrogen as for purging. These times needs to be optimized. The figure here shows how we have placed the samples inside the ALD chamber, and we will be focusing on the centermost samples as TTB is not one of the ideal ALD precursors. So starting with the optimization of TTB purge time and purge time, we saw that at longer soak times, we are able to provide enough precursor to get chemisorbed and come into a self-limiting manner. Same observation was seen in water soak time. So here we have measured the thicknesses and refractive indexes with ellipsometry technique. After optimizing TTB and water dosage time, we went with the nitrogen purge time. And at longer purge times, it was observed that deposition rate tends to be uniform for our centermost samples with a refractive index about 2.2, which is near to the bulk value of TiO2. And lastly, we went with the optimization of substrate temperature, because in ALD, what is important is to find out an ALD window. So for our recipe, we find out an ALD window from between 50 degrees Celsius to 120 degrees Celsius, with the most uniform samples being deposited at 90 degrees Celsius. So these are the optimized parameters which I have highlighted in the table. With the substrate temperature being minimum as 90 degrees Celsius for TiO2 deposition as of now. And in order to also cross-check that what we have deposited is TiO2 in its elemental composition, we went for XPS, and the two peaks at binding energy of 464.97 and 459.22 EV is evident and corresponds to Ti 2pi 1 by 2 and Ti 2p 3 by 2 peaks, which shows that titanium present in the film is in Ti plus 4 oxidation state. And oxygen also shows the same oxidation of 2 minus 2. And hence, we can conclude that TiO2, what we have deposited is TiO2 at a ultra low deposition temperature of 90 degrees Celsius. Yeah.
Thank you.
Thank you.
We are just moving to the next poster, Mr. Pawan Kumar. Optimization of ohmic contact for dips grown MgZNO, CdZNO, HFET on silicon. Go ahead for 2 minutes.
Am I audible?
Yes,
Hello,
you
sir.
are.
Yes, you are audible. Go ahead.
Okay, thank you, sir. In this work, we have described the optimization of the ohmic contact for DIBS grown MG Jordano, CD Jordano, HFAT on silicon. And we know that Jordano as a wideband material, they have the high saturation velocity around of 10 power 7 order, and they have a higher breakdown voltage. For that, it is suitable for the DC application. So in our work, we have tried to formation a heterostructure field effect transistor. For that source and drain contact formation, we need to optimize the ohmic contact. So first we grow the heterostructure by using the dual ion beam scattering, and with different conditions that like mentioned in the table, beam voltage and acceleration voltage like 160 and ratio of the gases argon and oxygen 2:3 SCM, and the growth temperature of the both material is same is 300 centigrade. And we have make the TLM mask at CSCR Sri Pilani, and we use the three different metal combination like titanium, aluminum, nickel, gold, and titanium, aluminum, gold, and titanium, gold with different thickness of the metal. And in right side we have so that with the different distance with the metal we have observed the total resistance, and inside we show the with, distance between the metal 0, and we calculate the total resistance. And for that the instant we use to calculate the resistivity.
Mr. Pawan,
Yes,
can
sir?
you quickly wind up because many of the
Okay, sir.
participants are
1
waiting. We
minute.
are just
Okay.
1 minute. Just
In this work, we have looked that we have achieved the lower resistivity in the combination of the titanium, aluminum, nickel, gold. The reason behind is that the nickel is prevent to diffuse the gold through the aluminum and titanium, and it will help to degrade the ohmic contact. That's why the titanium, aluminum, nickel, gold combination is the best combination for the ohmic contact for the source drain contact in the transistor, or it is comparable to already available in the industry like gain based transistor. So it's that means our work is useful to try to make the power transistor. Thank you, sir.
Nice presentation, Pawan.
Thank you, Pawan. Next, we are going to Kapil Narang. Growth of device quality in gallium nitride based GaN HAMT structure on silicon carbide. You have only 2 minutes. Please go ahead.
I'm audible. Please confirm.
Pawan?
I'm audible.
Hi,
Please
Kapil, you are
confirm.
audible.
Okay, thanks a lot. First of all, good. It's for 11.
Okay.
Okay. First of all, good evening to each and everyone here. In this work, we report the growth of AlGaN GaN HAMT structure on a very thin GaN layer, about 200 nanometer on a silicon carbide substrate by metal organic vapor phase epitaxial technique. As we know very well, in conventional HAMT structure, about 2 micron thick GaN layer has been used. And so we are successfully able to grow thin GaN HAMT structure. There are several advantages here I have listed, just like improvement in the heat dissipation, reduction in material consumption, and so on. If we all remember the last lecture given by the Professor S. Raghavan sir from the IFC Bangalore, he has clearly mentioned about the group named Swegan in Sweden, and the recent work about their thin GaN HAMT structure on a silicon carbide substrate. And he has also mentioned that the group which are working on a silicon carbide substrate must look into that. So on the same thing, we are also working on toward this, in which the aluminum nitride nucleation layer quality has a big role to achieve thin GaN based HAMT structure. This is a system. This is a picture of the system that we have used to grow the structure. The growth challenges, the main two growth challenges are the dislocation density in the GaN epi layer and the interface quality near the 2DG. So for that, the different experiment runs have been done by varying different growth conditions for the aluminum nitride nucleation layer and for the GaN about 200 nanometer layer. And we are successfully able to grow similar structural surface morphology as well as electrical 2DG properties of thin GaN HAMT structure. As you can see on the HRXRD, we are getting a similar structural property. Regarding the FWHM values for the 002 plane and 102 plane, we are getting a similar FWHM value, means a similar threading dislocation density has been achieved in a thin GaN HAMT structure as in conventional GaN HAMT structure. As far as the AFM result, we are getting a similar surface morphology on a 5 micron by 5 micron scan area with a RMS roughness of less than 1 nanometer in both the structure. As for the 2DG properties, we are getting a similar 2DG properties of sheet resistance, concentration, mobility, and the device fabrication has been started on. Yes, I'm winding up in that, and we are getting an improvement in the buffer leakage. Finally, optimized thin GaN ham structure has been grown. Surface morphology, structural 2DG properties comparable. Buffer leakage has been reduced significantly. Thanks a lot.
So hi, I have one query, Kapil. Ashutosh here.
Yes, Dr. Ashutosh.
So like, what is the TDD in that thin GaN hams, like threading dislocation density? From the XRD, have you measured it? Like, what's the order?
From the XRD, there is a one basically formula given by the M. Moron. In that, the threading dislocation density we have calculated. It is in the screw dislocation density is about low 10⁸, and for the edge dislocation density is about little higher 10⁸, and they are similar as in conventional GaN ham structure.
Okay. Thanks, Kapil.
Okay, thank you.
Thank you. We are moving to the post number 12, Muthumayi Nayak. Just go ahead for 2 minutes.
Hello. Audible?
Yes, you are. Please go ahead.
Just
You have only 2 minutes.
magnify your poster.
Oh.
Yeah. Okay.
Algan ham mobility concentration the threshold. Important to know to applied voltage induced stress. This is the start of the device. So here with increase negative due to the enhancement stress. With increase in the gate length, in the threshold voltage becomes maximum. And the third figure.
Dr. Muthumayi, please wind up.
It is stability.
Thank you. Next, we are moving to the post number 13. Ms. Sonika Singh, please go ahead for 2 minutes. If she is not there, we are moving to the next P14, Ms. Shraddha Gupta.
Am I audible?
Yes, you are. Go ahead.
Okay. I have modeled the on-state leakage current in AlGaN HAMT. For that, the total modeling has been done as using a combination of trap-assisted tunneling current and the phonon-assisted tunneling current, using the concept of change in the phonon energy. In the experimental details, the measurement has been performed on the Nitronics device, that is AlGaN HAMT. Here we can see the leakage current, change in the leakage current. As we increase the temperature, there is a reduction in the leakage current. And it is because of the change in the phonon energy. As we increase the temperature, there is a reduction in the phonon energy. On the other hand, as we increase the drain voltage, there is an increase in the phonon energy. So here is the result in the discussion, in which we can see it can be explained by the capture rate and the emission rate. As we increase the temperature, there is a reduction in the capture rate. On the other hand, as we increase the temperature, there is an increase in the emission rate. This increase in the emission rate resulted into the reduction in the virtual gate length. So at the higher temperature, drain current collapse is less pronounced. So the total leakage current over here now being modeled as a combination of phonon assisted tunneling current and trap assisted tunneling current. This TAT component has been explained by considering the two parallel conduction path from the gate edge towards the Elgin barrier, one the direct tunneling part and the other via the traps. So the other component is the PAT component, which has been explained using the phonon energy. So here we can see that as we increase the temperature, there is a increase in the TAT component. But on the other hand, as we increase the temperature, there is a reduction in the PAT component. So this PAT component is being dominated because of the change in the phonon energy. So the total leakage current now being more governed by the PAT component.
Shraddha Gupta, please wind up.
Okay, the total leakage current now being modeled mainly because of the change in the phonon energy as a PAT component. Thank you.
Okay, thank you. We are moving to the next one. P15. Post number P15, Mr. Vishnu Agarwal.
Yes, sir. Am I audible?
Yes, you are audible. Please go ahead. Just 2 minutes only, please.
Okay. Sir, we have grown GAN on by laser assisted MB and on A-planes fire and used in photo detector applications. We know the GAN is wide band gap material with band gap 3.4 electron volt, and it is tunable by alloying with indium and aluminum from 0.7 to 6.2 electron volt. Whereas work has been done on different substrate due to unavailability of a single crystalline GAN bulk target. So we most of the work has been done on C-planes fire, but due to the lattice mismatch, which is greater than 14%, there is various threading dislocations in the grown GAN. So we use here A-plane fire and grow this by laser MB. And this is actually in silicon, in comparison to silicon, this is a direct band gap, and the photodetector have application because silicon photodetector aging didn't have harsh environment like in strong radiations field and high temperature and pressure. So we have grown gallium nitride by laser MB. This is the schematic diagram of this laser MB. This is the growth process of sequence of growth process. First, we have nitrated the sphere, and then growth proceed at 700 degrees Celsius. We also introduce their buffer layer, low temperature buffer layer at 500 degrees Celsius, and then we gain the nanostructure of gallium nitride. This is the spectrum morphology shown by FESM images. We got GAN film and nano column and nano structure of the gallium nitride by
Vishnu, can you wind up, please?
Yes, sir. And gallium nitride nanostructure have a very high height due to the vertical growth due to the porousness. And then for crystalline quality, we do HRXRD. There is clearly shown the single crystalline growth along the 00 C-axis, that is growth along Woodgile structure.
Thank you. We are moving to the next one because many people are there.
Sir,
Thank you.
One minute more, sir. Sir, 1 minute.
It's already 2 minutes over, please.
Sir, please. Sir, in Brahman, we have seen that the nanostructure have very good quality, very less in plane biaxial stress. And in photoresponse, nanoporous GaN has very high responsivity due to porousness. The light trapping is high and carrier generation is very high. So responsivity is, of nanoporous GaN is very high. This is shown table also. The XRC value and
thank you.
Okay, thank you, sir.
Thank you. We're moving to the next one, Miss Ruchi Singh, poster number 16. Please go ahead for 2 minutes. You are audible.
Good evening, sir. I'm going to give presentation on the topic of structural study of antimony doped ZNO thin film for optical application. In this work, we have grown antimony doped ZNO film over NSI, medium resistive NSI and sapphire. The growth conditions are mentioned in the poster. We have done a post annealing, in situ post annealing after the growth inside the DIBS chamber only. The basic band structure of the structure grown is indicated in the poster. Also, we have drawn the contact IV analysis, and in characterization we have done FESAM, through which we have visualized that the grown structure is very smooth, and if other layer would be grown over this layer, then the epitaxy and other structure will be it provides a better film to grow other structure over it. In a spectral ellipsometry analysis, we have done verified the refractive index, excitonic coefficient, band gap, and transmission intensity, transmission spectra of the grown film. Also, we have analyzed the thickness of the film and roughness of the film. From the transmission spectra, from the ellipsometry analysis, we can get the band gap, which is about 3.92 electron volt of the grown film. After that, we have also done the IV analysis using the solar simulator, in which we have obtained a rectification ratio of approximately 16 at plus minus 4 volts. From this analysis, we can conclude that antimony doped ZNO is weakly p-type, and it can be used for the applications where wide band gap and semiconductor is useful.
Thank you. Thank you. Next, we are moving to the post number 17, Mr. Vijay Kumar Vishwakarma. Please go ahead for 2 minutes. You are.
Hello.
Mr. Ajay Kumar?
Am I audible?
Yes, you are. Please go ahead for 2 minutes.
Yes, in this work we are presenting the effect of inhomogeneities on Schottky height and Richardson constant. We have fabricated in-house the Schottky diodes with various area and carried out IVT measurement. Thereafter, we calculated the Schottky height and identity factor based on the IV characteristics and plotted against the temperature. We can see that there is a variation in the Schottky height and identity factor with temperature. And again, we extracted. This graph shows there is a inhomogeneities in the interface at the interface. So again, we calculated Richardson constant using standard Richardson plot, which resulted in a very low value of Richardson constant. And again, we incorporated the effect of barrier inhomogeneities as a function of Gaussian function. We considered a Gaussian function which states that the barrier height inhomogeneities are distributed as a Gaussian function, and then we incorporated it in the standard model and extracted the new value of Richardson constant, which is around 33. And again, this value is in good agreement with the experimental data published. People also uses very people uses the Richardson constant value in between 26 and 40, because for AlGaN the exact value of Richardson constant is dependent on aluminum fraction. Therefore, it is important to extract the Richardson constant value for our sample is important to extract the exact Schottky parameters. So we have carried out this whole work. Thanks.
We are just moving to the post number 18.
This is Rajesh Sharma. I just wanted to ask a question. Can you put it back? Yeah. You have not mentioned the composition of Elgan, Mr. Vishwakarma. Has he left?
Mr. Vishwakarma?
Hello?
Yeah,
Yes, I'm on.
it appears that you have not mentioned the composition of Elgan.
It is around 24.
What do you mean by 24?
24 mole, aluminum mole fraction is 24. That is 24% of aluminum, and the 76 is of gallium in the Elgan.
So what is the conclusion that whether this is perfectly all right or some improvement can be done?
It is I think it is around 32, standard value is 32.4, and we are getting a 33.4. So there is an error of around 1 ampere per centimeter
Okay.
square per Kelvin gap.
So the purpose here is to get the correct No, I wanted to know whether the kind of inhomogeneities you have observed have some repercussion on device characteristics.
We are also doing in this area.
Okay. Fine. No issues.
And
no, it's okay. Okay. Thank you. Go to the next, please.
Okay, thanks.
Mr. Manu Shaji?
Yes, hello. Am I audible?
Yes, you are. Please go.
Okay, good evening to all. In this work, we have done a direct comparison of ionic liquid gated and conventional SiO2 gated zinc tin oxide thin film transistors. Ionic liquid gated thin film transistors have attracted attention because of their ease of processing, low voltage operation, and high electric fields at low bias voltages resulted from the formation of electric double layer in the ionic liquid semiconductor interface. Coming to the experimental and device fabrication part, we fabricated a SFT of TFT, the bottom gated TFT structure in a SiO2 substrate with a channel layer thickness of 50 nanometer. And titanium gold was used as drain source electrodes, and ionic liquid of EMIM TFSI used as a top gate because of its wide electrochemical window and large specific capacitance. In the device characterization, by comparing the TFT parameters of SiO2 gated and ionic liquid gated TFT, we obtain a improved mobility in the case of top ionic liquid gated TFT compared to the SiO2 gated TFTs. The mobility improved from 0.65 centimeter square per volt per second to 5.4 centimeter square per volt per second, and this improvement is seen in the case of subthreshold swing and threshold voltage
Mr. Manu
also.
Shaji, can
Yes.
you please wind up?
Yes. So the ionic liquid gated TFT show improved performance compared to the bottom SiO2 gated device at low operating voltages, because and this IL gated TFT can be used as for flexible devices and low operating voltages and for neuromorphic memory applications. Thank you.
We're moving to the next poster, P19, Miss Devashrita Mahana. You're
Yes, sir,
audible.
may I
Please go
audible?
ahead.
Okay, sir. Good afternoon, everyone. Myself Devashrita, and my topic is synthesis and CO gas sensing characteristics of CO nutrients prepared by the vacuum evaporation method. Now the question is why I have chosen this topic, because in recent society, air pollution become a serious problem of our society, and the main source of our air pollution are industry, power plants, automobiles, stubble burning, and storm dust, etc. Due to this air pollution, various diseases are occur in human body. So every year, 800 people are die due to air pollutions. Hello.
You please go ahead.
So
Yashpal Singh Khatriya, please mute yourself.
to detect, so it is necessary to detect that air pollution. We are trying to develop the portable gas sensor to detect that pollutant airs. So in our research work, we have tried to develop copper oxide thin film by vacuum evaporation method, and here we have chosen thermal evaporation method and deposit and copper thin film on glass substrate. After deposition of copper thin film, we oxidize it by tubular furnace in atmospheric air. And then resultant samples are copper oxide. We examine this sample by various characterization method, and in XRD we found that in 400 degrees centigrade temperature for 5 hours we got the copper oxide thin film. And
Can you please wind up, because we have to move to main session at 5 o'clock, so much time is not left.
Surface structure also we are characterized here, and sensing properties we are found by device measuring.
I think I suggest you directly go to the conclusion, and I suggest to the organizers also to request people to talk about mostly the conclusions. What is the conclusion of the study? Best we can understand.
Yes, sir.
Okay, sir. So in this, in our work, we found that copper oxide thin film is good for CO sensing work, and we found at 375 degrees measuring temperature, we got the highest sensitivity, and 400 degrees centigrade, that response and recovery time is very fast. So this is our best result of our.
Thank you. Thank you. One question. How do you assure the selectivity for carbon monoxide? Can it not, it may be sensitive to other gases as well?
Yes, sir. Next study is our other gas also. Now we are trying only CO gas. CO gas is most harmful.
Thanks. Okay.
Just we are moving to post number 20 now. Ms. Manisha Kumari.
स्क्रीन नहीं दिख रही
Wait, we are just arranging.
Okay. Good evening, everyone. My name is Manisha Kumari. हमें नहीं करना. In the present study.
Go to your conclusions.
Okay, so in the present study, the conclusion of my work is that I have grown a secondary phase of a BiCO03 at room temperature, which is found to be a wide bandgap semiconductor of bandgap 4.43 electron volts. This material is grown at 700 degrees Celsius to be crystalline along 310 plane, and I have grown using a thin film of this material using pulse laser deposition technique, and characterize those films. And this is the UV of these thin films, which is after top plot, the band gap is found to be 4.43 electron volts. Thank you.
Thank you, Manisha
Thank you.
Kumari.
Welcome, sir.
We are moving to post number 21. Ms. Gunjan Yadav. Ms. Manisha Kumari, please mute yourself. Okay, please go ahead, Gunjan Yadav.
Hello. Good afternoon, everyone. I have done the fabrication of Indian GaN multi-quantum wells based PIN laser emitting diode on sapphire substrate using laser molecular beam epitaxy technique. In the left side, you have seen the self-esteemed system of the laser MB, and these are the read parameters which I have measured from the read technique at room temperature, thermally clean substrate, nitridation, and the growth of the film. On the right side, you have seen the laser grown blue LED.
Go to your results. Go to your conclusions, please.
Okay, sir. In the conclusion, the Indian quantum well were deposited optimized growth temperature using laser molecular beam epitaxy system. The read images indicate the n-phased growth of the GAN thin films. On the top of the poster, you have seen the XRD of the individual GAN and InGAN thin films. And now the PL structure shows the emission at 361 nanometer, and the EL spectra for without LED and the without quantum and with quantum are shown. And the EL spectra of LED at varying injection current is characterized by single emission peak in the UV region centered at an emission wavelength of around 370 nanometer. It may be noted that the EL emission of the LED device was relatively redshifted as compared to the PL emission, that is 361 nanometer, obtained for individual GAN layers by the laser
Thank you.
molecular
Thank
beam
you. We are just
epitaxy
moving to the next one. Please, thank you. Post number 22, Ms. Chanchal. Ms. Gunjan Yadav, please mute yourself. Please, Ms. Chanchal, please. Okay, we are moving to
anybody else like Rupesh Chaube is there? If he can speak about it, that's also okay. If not, then we can move to the next.
We are moving to 23, Ms. Jagori Raichu. Please go ahead for 1 minute.
Good evening, sir. Here we have taken two different layer structures of gallium nitride HEMT. The first one has a GaN buffer layer, which is 2 micrometer thick and heavily doped with carbon atoms. The second one has that GaN buffer, but along with that, it has a 200 nanometer thick gallium nitride layer, which has high crystalline quality and less doped with carbon. Now, the traps can be characterized from the peak frequency of the device by measuring the S parameters. And when we do this measurement over a wide range of temperature, we can calculate the activation energy of the trap and the cross section of trap. So here we have taken two different layer structures and we have done low frequency S parameter measurements. From there, we have converted the Y parameters.
Conclusions, please. Conclusions.
And
Conclusion, please, quickly.
Yes, sir. And from this experiment, we have calculated the activation energy and cross section of the traps, and we can see that the device A having thick GaN buffer is severely affected with deep level traps. And since the second one, okay, sir. Thank you.
Thank you. Please unmute yourself. We are moving to the post number 24. Mr. Jayjeet Mukherjee, please go ahead for 1 minute. Please go to your conclusions.
So am I audible? Hello, am I audible?
You are audible, please go.
So over here that we are, what I'm presenting is a pulsed IV and drain current transient study of unpassivated and passivated HEMTs, which are grown in SSPL on in-house MOCVD epi structure. So the we have conducted pulsed IV characteristics with gate turn-on pulse as well as gate turn-off pulse. We can see that the gate turn-on pulse has heavily high degrading effects for the unpassivated HEMTs, which are directly due to the effect of surface traps present in the on the AlGaN surface, whereas the passivated one are mitigated due to the passivation. The surface trap effects are mitigated, and the only kink that is evident in both the devices are resultant due to the epi structure traps, which are which can be also due to the bulk traps. And apart from that, I have also conducted the transient analysis for a temperature range of 25 to 150 degrees Celsius, from which we can calculate the trap energies as 0.43 electron volt and 0.52 for the unpassivated one, and for the passivated one it is 0.68 electron volt, which are correlated to the for the passivated one, it is correlated to the gallium vacancies and oxygen complexes or the nitrogen interstitials within the epitaxial layers, and these are contributing to the kink effect.
Thank you.
Which is around 0.58 electron volt. Thank you.
Thank you. We are moving to the post number 25. Dr. Sonali Kapoor, you're audible. Please go ahead for one. Dr. Sonali Kapoor, do you have from your end the poster? Please upload it.
I have already sent the poster. अब upload कैसे होगा? Sir, I'm on the phone actually. Will not be able to upload right now.
We don't have with us your poster number 25.
But we have sent it through the DRDO mail. Can you upload it from your side? Oh,
now it's not. We don't have now.
So I can briefly tell you.
No issue. You please send it to us, and we will send it to the evaluators. Please.
I can briefly just tell about the poster. Hello.
Just your conclusion, Sonali. Just what you found out in your study. Just in 2 lines.
Just in 2 lines. Okay, I was basically working on Elgan-GaN HEMS. Presently, we are fabricating ohmic contacts based on ti-aluminum nickel-gold metal scheme, and we are obtaining FOM of the order of 0.3 to 0.6 ohm. So basic idea is to reduce this contact resistance down to 0.1 ohm. So we are working on tantalum-based ohmic contacts. These are gold-free ohmic contacts. As you are aware, they offer low contact resistances with smooth surface morphology, and they also
Sonali,
offer.
that's great. What have you achieved? What is the specific resistance you could achieve?
So basically, through the design of experiments, we have tried different tantalum aluminum ratios of 1:30, 1:28, and 1:35, and 1:14 based on literature survey. And what we have found out that with 1:30 ratio, an yield at 575 degrees centigrade for around 3 minutes is giving us very good IDSS values as compared to the normal metal scheme.
Oh, that's okay, but you didn't answer. Okay, no problem. Go ahead.
Thank you. We are going
next पे जाइए.
to
Next
the
पे जाइए.
26. Dr. Samriddhi Prabhakar Rao, please go to your conclusion.
Excuse me.
Good afternoon. So in this work, we have investigated the electrical performance of buffer-free GaN and silicon carbide HEMT. As observed, the figure 4 shows the electrical concentration. The buffer-free HEMT proves an edge by in the absence of the buffer layer. It gives a smaller area for the plasma to generate, and a faster removal or the saturation is achieved in the buffer-free HEMT. While the transient diagrams, you can see that the impact is more severe in case of epi-buffer doped HEMT because in presence of buffer, there will be a greater plasma generation rate, a greater charge, and so a greater transient action. Also, there will be a significant negative charge as observed from the figure. This is because of the induced back channel effect and the bipolar effects. The electrical field shows a much greater degradation in case of epi-buffer layer than the buffer-free head, while the charge generation plot shows that more charge can be collected in case of the buffer in absence of buffer. In presence of buffer, which shows a greater robustness of buffer-free head.
Thank you.
Thank you, sir.
Okay, next we are moving to next post number 27.
Yes, sir. I am audible, sir.
Yes, you are. Please.
So this is Sharda Sharma. The conclusion of my work is basically we have fabricated doped TiO2 nanotubes using silver nanoparticle, using silver, and then we have characterized it using Tox plot, XRD, and SEM. With Tox plot, we can identify that the band gap was reduced from 3.2 to 3, identifying that which can be used for enhancing the electrochemical sensing performance. Here, as using glucose sensing as an example, we have used various concentration in order to show the electrochemical sensing performance. By using Nyquist plot, we have understood the effect that by reducing the charge transfer resistance, we have improved the conductivity, and thus the performance was improved. In the further conclusion, what I can say is, if we have added some catalyst and if we have done further modification on the doped nanostructure, we will be able to enhance the sensitivity as well as performance of electrochemical sensors. by for one more thing I must add is for in order to see the anti-interference ability, we have checked with various analytes such as ascorbic acid, uric acid, dopamine, and where we can see in the inset that the performance for glucose sensing was much more showing the selective property of my electrochemical
Thank you.
sensor.
Thank you. Thank you.
Thank you so much, sir.
Last for this session, we cannot go further because the 5 o'clock talk is going to start now. So
Yes,
we are going to take one more. Last, Dr. Rupesh K. Chaubey. You
Okay.
have.
Hello, am I audible?
Yes, sir. Yes, sir.
Am I audible?
Yes, sir.
Hello, am I audible?
Yes, you are audible.
Yes, sir.
Yeah, good evening all. This is Rupesh from SSPL. I'm presenting my work on challenges of dye simulation in aluminum gallium nitride HEM technology. So dye simulation.
Please go for the.
Yeah, I'm going for. So dicing is a process in semiconductor manufacturing where individual dies are separated. So in this work, we are working on silicon carbide substrate, and we know that this is the third hardest material in the world. So I have mentioned here the challenges associated with the silicon carbide dicing, means hem to dicing on silicon carbide, and we have developed an in-house process of dicing process for high frequency, high power gallium nitride, aluminum gallium nitride on silicon carbide devices. That's it.
Thank you very much. All the other participants' posters will be evaluated by the examiners. And for time being, we have to move to the main session, which is going to be started at 5 o'clock. Please join.
Hi, is there any moderator? I'm Ashutosh actually. I just have one request. Like I have to evaluate poster 1 to 15, but I don't have poster number 3, 5, and 13. So may you kindly send them? I left a message in the chat section also. So
yes, we will get back to you.
Yes. Okay, thanks.
Dr. Manikand Babu, just is checking for you.
You're audible and visible also.
Okay, fine. So I can just wait for.
Yes, we'll wait for your turn.
And okay, so just 1 minute. Can you just see whether I'm able to share my video? So
yes, your video is visible. Yes, it is fine.
now, and also you can see my slide now. Correct? I am just now shared mine.
You're sharing. Yes, it is coming now. Yes,
okay,
yes, yes.
Fine. That's what I wanted
fine,
to.
Thank you.
Thank you. You can remove from me. Okay.
Yes, yes.
हेलो नवीन, इसका 2 ईयर अभी मेल भेजी हुई है, उसमें डिटेल लिखा हुआ है, डिटेल लिखा हुआ मेल भेजी हुई है इसको परचेज। हाँ दूसरी है वही है, कटेगा इसमें एलडी फाइनल डिलीवरेबल 3 साल के बाद है यार, बीच में डिसाइड हुआ है। दी हुई है ना जो डिस्कशन हुआ था, क्योंकि जो लॉन्ग टर्म प्रोजेक्ट्स होते हैं। अच्छा तो फिर अभी तो कोविड की सिचुएशन में ले लो यार थोड़ा बड़े भाई। हाँ,
Dr. Huda, you are wishing
हाँ,
morning to everybody.
जस्ट होल्ड ऑन, मेरा एक मीटिंग चल रही है बड़ी मत। ठीक है, थैंक यू। हेलो हेलो
Hello.
हेलो
Hello. Dr. Manish Huda?
या मनीष here sir, how are you?
Sir, please go ahead for the session. Please share this.
Okay, sorry for the delay, actually I got a late response from the link. I welcome you all in the last session of the day, and in this session we are having 2 invited lectures. One from Dr. Kumund Ranjan from NTU Singapore, and the title of the lecture is Algan GAN HAMT on CVD diamond. I think this is one of the new area where the people are now most looking forward to provide the solutions for high power and high frequency application of the devices. And this is the area where people are looking for solution for deep space as well as for the commercial application. And of course, 5G is giving a next inch towards the technology nodes where we can have pole-to-pole communication for giving better communication and setup for the all. Now I request Dr. Kumund Ranjan from NTU Singapore to give the talk. Thank you, sir. It's over to you, sir.
Thank you, Dr. Manish. Just give me 1 second. Hello. Hello, Dr. Manish.
Yes, sir. Yes, sir. We can see your screen, sir. Yes, sir.
That's
you are
fine.
out.
And my presentation is, can you see my presentation?
Yes. Yeah, we can see your presentations.
Okay. Okay. So good evening, everyone. I'll, as Dr. Manish already mentioned that it's a GAN HAMT on CVD diamond. First of all, I would like to thank this committee, and in a very short notice, actually, I just prepared all these things. For this emerging electronics, what I understood from this conference for the emerging electronics is, so GAN technology, already we know that for last 2 decades almost, we are developing GAN devices and replacing most of the gallium arsenide based devices and all. So I would like to start first to give introduction and gallium nitride. Why gallium nitride? It's a technology and applications, and then GAN on diamond, and what are the advantages of the GAN on diamond, and what are the challenges? Because recently,
Sorry for the interruption. Can you please go for the full screen, please?
Us. Okay, sorry. Yeah, is it okay? Okay. And finally, I will conclude with the advantages and challenges in the GAN on diamond. So first, as we all know, the why gallium nitride. From the material point of view, the gallium is a figure of merit or material figure of merits. We can see from this, it's a graph. It's like for on left half of the side, we can see from the power perspective, high power, and the right side we can see is the high frequency application. So here there are 3 color we can see is the one is the this gray, then green, and the blue. So it's representing gallium nitride. Here is gallium arsenide, and the gray one is for silicon. So here in this presentation, I will be mostly focusing on the RF side. So I will be highlighting how it is better than GaN from the gallium arsenide or silicon perspective. So for the high speed and the high power, GaN has very clear advantage over from the material perspective. So wherever we talk about its mobility or the high speed, or it's like the handling the power, or wide band gap like handling the temperature, means high temperature operation. So then gallium nitride has a very clearly has well developed devices on a different substrates. Then we can see the applications, the GaN applications. As we mentioned, that a lot of applications of the GaN semiconductor from the LED perspective, laser, power electronics, and the microsystems, Li-Fi, and other solar cells and all. So, but here we'll focus in the RF communication and the how it is advantage in the RF side and what in the power. Has 200 gigahertz or even sub 6 gigahertz frequency also gallium nitride has already emerged. But for like high frequency applications with the high power, we have we already know that it's for satellite communication, automotive radar, military systems and all. It's required very compact device and very high power RF amplifier from small band, or we can say it's S band, even L band to W band. So we can see just a very conventional spectrum, RF power spectrum for from the low frequency to high frequency. Even I didn't cover even higher frequencies. But in all these applications, we can see increasing the frequency, and same time we need for radar and avionics system, even the high power. So how gallium nitride is fulfilling the requirement, and what is the advantage? Like we can see the small form factor, like the smaller size, and the reliability, the voltage operations. These are the requirements, basically high voltage operations and the high temperature. So we have to understand the gallium nitride technology and the reliability point of view. It's what happens when we increase the voltage to get the more power, RF power, and what happens when we go for the higher temperature operation. This is a typical diagram of any transmitter receiver system. This is just for the conventional. I just show the radar RF front end system. In this major part is the power amplifier and the low noise amplifier in the receiver side. This is in the transmitter side, power amplifier, and the switch. So here in the conventionally, we see in the front end, most is fabricated like even PA, LNA, and switch. So here we will see some of the, like how the gallium nitride, like previously, okay, TWT based amplifier, and now GaN based power amplifier is replacing partially. It's not completely, but TWT amplifiers. For moderate and low power, solid state power amplifier, even gallium arsenide and silicon based amplifiers are available. But in this, from market's perspective, we can see the RF power amplifier, even the maximum share. We see here it's just like one future market. It's a companies they have presented. It's around 40% is the share of the RF power amplifier. So more is focusing on the power side. So here in this conversation, in this discussion, we'll highlight what is the requirement of the power amplifier and how gallium nitride is fulfilling these requirements. So just take one development steps. Like as we know that for the radar and electronic warfare and even communication applications, the GaN technology for military applications and all. So like this module is required in any system. So this module needs the packaged chip. Previously the gallium arsenide based chips were larger and larger. So these chips needs basically a fabricated ICs. Here is just a symbolic representation of the device. This is not complete IC. This is just one multi-finger transistors and how it is fabricated on wafer, and then what is the structure. So if there is a requirement of example 100 watt power amplifier, CW power amplifier, any frequency, then how we design the epi structure and for the different substrates. So this is a conventional approach from the requirement of the system, from military applications, for defense, for space applications, or even for commercial applications. So then we come to the device structure. This is in general because device structure gives the current requirement, voltage requirement, breakdown voltage, cutoff frequencies, and all. So from this, this is a conventional approach. So previously, we used to have a silicon and silicon carbide, even long back it's a sapphire substrates. But now we'll see the problem with the silicon or silicon carbide. So in this one, just I can show you all like the gallium arsenide. Even if you take the 2-decade advancement in the MICs, size reduction. So gallium arsenide based for the same power, if it is gallium nitride, almost we see that around 80 to 82% of size reduction in size. So further, what happens if you go beyond size reduction? Because sometimes it's a requirement of the size reduction of the ICs, complete MICs. So gallium arsenide, we see just for an example, 4-watt gallium arsenide power amplifier. So it's like, okay, this from the single devices or even the MICs, and after combining few MICs and then combining, we get 4-watt at C band. Somewhere is a 4 to 8 gigahertz. And then it's replacing equivalent GaN PA. It's just replacing the entire gallium arsenide based power amplifier. So as we already discussed, advantage with GaN technology, small form factor, high power density, and lower cooling management. This cooling management is a requirement also. So what are the challenges? Because now previously the requirement was around 10 volt drain voltage, because gallium arsenide has a lower breakdown voltage. Then increase the voltage, like currently it's a 24 volt, or even now it's going 48 volts and beyond that. So once we increase the voltage, drain voltage in the device, so self-heating in the device, this is one of the key parameters, like what happens when the self-heating happens in the device itself during the operation. So it degrades output power and trapping effects. This is also a very important parameter, because without having understanding of the device trapping effects, because this directly relates to the RF performance, it degrades the RF power of the complete device and ICs. So for this, we have one example, like what is the self-heating and how it goes when we increase the voltage. Okay, just I took one example for the silicon carbide, GaN on silicon carbide. So we see the current reduction after certain ID max, at few voltage around 5 volt or something. So current reduction, it's intrinsically the mobility drops down because of the increasing the temperature. I can present in the few next slides. Then this, due to this self-heating, we can see, probably I can't see here. Yeah. So it's a GaN on silicon carbide. Sorry, the red one is the GaN on silicon. So we see after few voltage, like 60 volt here, the power, this is around 5 gigahertz, and 5 gigahertz RF power drops down. So there is always challenge, like it should minimum self-heating or minimum power degradation at the higher voltages. So silicon carbide is showing better performances. So what happens when self-heating occurs? The channel temperature rises. It degrades 2dg electron mobility by increasing phonon scattering, and the resulting is the current reduction, and power output and the power added efficiency degradation happens. So what we have to do for high performance GaN HEMT, we have to minimize the self-heating effect. That's the first. Second is that, so for this, what do we need? We need a large thermal conductive substrate. So now we can see is the thermal conductivity of the substrates. This is just a symbolic representation. It's not exactly scaled down here, but we can see here is the sapphire, silicon, gallium nitride substrate, silicon carbide, and the CVD diamond. And that one temperature, still it is not a very quantified in exact values, but it's in general, it's showing the 10x higher thermal conductivity than conventional silicon substrate, silicon material, and around 4 times higher than the silicon carbide. So because we can see here in this, like most of the self-heating, most of the heat dissipation from the channel, it happens through the bottom, through the substrate. We have seen some of the like heat dissipation from the top also, but we have done a few experiments also, like what is the values, like how much it heat dissipates from the substrate. And then we see the Hempt form factor in GaN on diamond can be reduced because of the we can increase the voltage because when channel temperature is increasing. Sometimes we are, as a developer, we have to restrict ourselves. Channel temperature should not go beyond 150 degrees C at certain voltage, like around 25 volt or 30 volts or something. So channel temperature goes very high when the substrate is silicon. Then we cannot go beyond certain voltage in some current density, particular current density. So here in the diamond, we have options. We can increase the voltage. This is one simulation studies we have already presented in one paper, that at certain 20 volt is in the same configuration device, same density, same 2 dg concentration of both the devices, identical devices in terms. The channel temperature is around 150 to 160 degrees C, whereas in the diamond it's just 65 to 70 degrees C. But this can be changed based on the device topology. Basically, is the source drain gate configuration also. But this is a simple representation that what is the effect of the substrate when diamond comes, then how the channel temperature goes down, or its heat dissipation is faster and faster. So people have already presented GaN on silicon carbide also. There's a previously GaN on silicon carbide. So GaN on silicon carbide, example is the 4 watt power density. Is the temperature is around 200 degrees C, 202 degrees C. Whereas in at the diamond, where the base plate even was the same base plate temperature, is around 12 watt dissipation RF power. Also, it's 195 degrees C. Here, it's a 12 watt. So they have observed that it's the 3 times higher power dissipation in the diamond, and thermal conductivity almost 3.8 times lower thermal conductivity in GaN on diamond compared to the GaN on silicon carbide even. Yeah. Even in diamond, it's like there are different type of crystalline structure, like the 1B or 2A. It's basically a different crystalline quality, and it also have a different thermal conductivity. So it's reported, Irama group has already reported with the 1B single crystalline structure when the substrate is 1B side, and thus when it is 2A, then they have observed that it's 5 times lower thermal conductivity in terms of the thermal resistance, sorry, in terms of 1Bs. So now have some challenges. So how it is GaN on diamond is recently. There are a couple of methods, like it's a substrate transfer and all, but this is general representation that this is conventional GaN on silicon. It's a device, it's a transition layer and the silicon substrate. And here, this entire substrate is removed, is a GaN transition layer is removed, and then it's the diamond is basically bonded, or sometimes the diamond is grown also. So I will present in the next slide that how people have like grown their diamond, or is bonding is there. So question is also the reliability. Apart from this DC and RF performances, it's a reliability side. So as we have seen that how the form factor reduced the GaN on silicon carbide to GaN on diamond, even multiple finger, because the source drain area, or we call like gate to gate pitch, is we can reduce because the junction temperature increases. So in the diamond, when the temperature is low, even so we can further reduce the source drain gap. So in terms of, we can increase the temperature, but still the power is maintained. It's no power degradation occurs. So they have observed, researcher has already observed, there's a 3x reduction in thermal resistance, and almost 3.87 times is the areal power density, increased areal power density in GaN on diamond. So why we call it areal power density here? Because the total area is almost reduced, even in the giving the same power for the small form factor. So if the same area is there, so from the GaN on diamond, we can take almost 3 times or even more than high power density in GaN on diamond. So now reliability side, GaN on silicon is 3000 hours. After that, the reduction in the current, almost 80% IDS degradation has observed in that at 350 degrees C. Whereas GaN on dia, it's almost only 10% ID reduction. So reliability is basically the same temperature, but this reliability is not very, as of now, it's not very clear that whether in terms of the material or is it degradation because of the gate degradation and all. So people are doing a lot of research on this reliability side in the GaN on diamond. So one one device I also fabricated around a couple of years, 2-3 years back, in the GaN on silicon and the GaN on diamond. So we compared the GaN on silicon because the devices Epi structure were identical. So GaN on silicon is the fast current degradation we have seen previously also. It's a fast degradation once we increasing the drain voltage, whereas the diamond even up to 60 volt we went through. But there was no burn even the devices, but silicon devices were burning. So we can reduce this burnout by increasing the source drain spacing. But for the similar structure, this is the clear advantage. So now designer can take, depends on their requirement, where they want to design the devices, even higher voltage and like high current density is required. So diamond can give the very high current density as so they can achieve the high power. So high DC power density, they can achieve even high RF powers. One result from S parameter, FTF max point of view, because it's identical current density. So we have seen some gain advantage in the diamond also. And from the S parameter, FT and F max calculation over the dissipated power density, because increase the voltage and maintaining the current density. You see that we have seen the degradation in the GaN on silicon is much faster. So this is ultimately related to the mobility reduction also, because mobility is directly the transconductance, and we know that cutoff frequency is just like GM upon 2 pi, 2 pi CG. So from the GM and from the sum capacitance, but the mobility directly affects the transconductance of the devices, and FT and same way F max also degrades. So if we have to go for high FT and high F max, and example, the wide voltage operations, like from 10 volt to suppose 30 volt operations. So in case of the silicon, what happens, or gallium arsenide based devices, or even GaN on silicon based devices, we cannot design the same devices for low voltage or even for high voltage. For high voltage, maybe we have to increase the device's dimension, source drain spacing, and the gate length, okay, it is required for the frequency. But in the GaN on diamond, the single design can give the low voltage, okay, that's fine, but even high voltage, because there is no degradation, almost it's a very flat. It's just, I can show in the sum here. Yeah, it's just 1 dB degradation. Almost is a 10 volt to 40 volt, 1 dB degradation in diamond, whereas in the silicon, around 7 dB. So this 7 dB is not acceptable in for any design perspective. So GaN on diamond can be well used for the large wide voltage. Already this slide we mentioned that why we go for the GaN on diamond RF power, because GaN on silicon suppose gives a 3 watt per mm at 10 gigahertz, whereas silicon carbides 4 to 5 watt. Again, it depends on the gate technology. So this is just one example, 4 to 5 watt at 10 gigahertz per mm. So whereas the diamond can give the higher power density. So researchers have already used the more than 3 times higher power density than GaN on silicon carbide and GaN on silicon even. In this series, here is the one example, like how it is GaN on diamond is more than 3.6 times areal power density increased. Maybe the heat dissipation or the temperature increases by, so power is saturated and further power goes down. But here in the diamond have bandwidth, increase the input power also, and we can achieve the high power. So it also relates to the current density. So this is the normalized current density is the diamond. It's not degraded with the time scale also, and whereas the silicon carbide current degradation can be observed. So one that we used for our research sometime like is how the GaN on silicon and the GaN on. So there are some challenges here. So like silicon is available, readily available silicon substrates, even the silicon carbide, and we go with we have a very well established technology to grow the epi structure on silicon and silicon carbide. Diamond is still it's not readily, like it's a very high performance crystalline structure availability for the AlGaN GaN layer development. So people have tried, one group has tried the single crystal diamond and then growth of this one, but the performance is not good. So this technology is that whether it's remove the substrate and the transition layer and then the bond or grow the diamond. So for this is the challenging here. So many groups are trying, and they have presented results also. I can show some of the results. Yeah, in one group, PC Chow, yeah, they used both the methods, like the growth of the diamond after removal of the substrate growth, and the same time it's the bonding techniques. So with the low temperature bonding techniques, because growth normally the diamond needs more than 800 degrees C for the growth side, and the mobility and the thermal conductivity is in between around somewhere it's 1200 to 1400 watt per meter Kelvin, whereas in the low bonded less than 150 degrees C. So this they have claimed that 2100 watt per meter Kelvin. So this one, with this, the thermal conductivity is improved. But the challenge is, another challenge is, because this diamond substrate is grown or is bonded, so we have to study a deep research we have to do with the trapping effects, like what happens, because every process induces some of the traps that probably it's after the device fabrication, we have to go for the analysis. What happens with the current collapse? So very few papers are available on the current collapse study or even the different traps on the GaN on diamond substrates. But in GaN on silicon carbide and GaN on silicon, it's few papers are already available. So this side researches are going on. So in the summary, I can say that it's like 5 times enhanced DC and RF performances we have observed in the GaN on diamond in comparison to the GaN on silicon. But the GaN on silicon carbide, it's around 3.4 times higher RF performances. The challenges is substrate transfer and the diamond bonding. This is still under development process. Basically, I can say from the reliability perspective, the more research on the reliability is required on the GaN on diamond. However, the few ICs are available, but it's not commercially available. It's just in the research it is available, and reliability studies, like the most important is the trapping studies, and over the time period how the degradation occurs. But the thermal conductivity is well proven that improved power performances, improved device DC performances, and once the reliability, if the more reliability data is available, then we can claim this like, okay, the maturity of this technology. So I can acknowledge, I just wish to acknowledge our microsystem department, MTDC, and there are a couple of characterization center is there. One is the Silicon COE. This is for high power, high voltage DC and DC characterizations. And in Thales group in the same another department, it's for the load pull system for RF power measurements and all. So after fabrication of the few devices GaN on diamond, we have already characterized, and we have presented few papers on this one. And thank you everyone. I hope I just finished early, but if you have any questions, you please ask.
Yeah, thank you, Dr. Ranjan, for the nice talk. And if any questions, you can write down onto the chat box, or we can directly ask. Any questions, please?
Yeah, so Dr. Manish Huda, I am Dr. Rajendra Singh from IIT Delhi.
Yes, sir.
I just want to ask, what is the material of this adhesion layer and how much is its thickness?
Yeah, because this material is, we cannot, because this is a proprietary material from the element 6, because we didn't use this adhesion layer, we didn't grow deposit the adhesion layer in our lab. But normally after the TM, we can see that it's a silicon nitride, but we cannot give the 100% composition of that material. But it's around 10 to 15 nanometer to 50 nanometer additional layer thickness is there. So with this thickness, people are also doing the research on the thermal conductivity, because heat dissipation, thermal resistance, overall thermal resistance. So based on the thickness, there are a few data available, like how it improves the heat dissipation.
How to improve. Okay, thank you.
Yeah, welcome, sir.
Yeah, Dr. Rajan, I have some questions in the box, and the question is, what is the thickness of diamond that you have used?
Yeah, diamond thickness 100 micron. We have used 100 micron, but people have also used 50 micron diamond substrate thickness because it's the most important is the handling of the substrate. But still, because we cannot directly process Ganon diamond 100 because 100 micron thick, either 4-inch or even 1-inch, we cannot directly process. So we bonded it on just it's bonded on a different like silicon or something. But generally, we are using from 50 micron to around 150. So standard is 100 micron diamond substrate thickness.
Okay, sir. There is another question. Can we have diamond-like features instead of diamond as a substrate?
Diamond-like features?
In some substrate by adding. I think that is the question from Dr. Gaurav.
I didn't understand clearly.
Okay,
Like,
then
yeah.
we can leave it. And the another question is predominantly cooling effect improves RF performances.
Yes.
Are there any scalable cooling technology you foresee?
Okay, maybe
To achieve similar RF performances. I think I can repeat the question. I think the writing is not predominantly cooling effect improves RF performances. Okay. Are there any scalable cooling technology you foresee to achieve the similar RF performances? This is the question, sir.
Yeah. So see, there are two cooling. Normally, the cooling technologies we understand in different conventional substrates, like external cooling technologies. After the material, we just thin down the substrate to 100 micron, or depends on what we can do maximum. So thinning down the substrate is the conventional, and after that, adding the additional parts like some liquid cooling system or some heat sink and all. So here in the diamond, I can say that this is the inherent cooling system. So beyond that also we can use. So even further want to reduce the temperature, junction temperature, so that can be used the conventional, whatever the conventional like system, cooling system is used. So, but the substrate inherently reducing the temperature. So there are two parts always cooling, inherent and then external part. So maybe external, yeah, they can use whatever the conventional approach is there.
There is another question from Dr. Satish.
Yeah.
Recently, microfluidics based cooling is also proposed to improve the performances. Is that has been adopted in this?
Yes, yes. That's why same thing I mentioned in the previous things. So the cooling system, the microfluid and all. So that later can be used. But the question is comes like, can you etch the diamond or the backside? How we can this one? This currently in the diamond is not being used, or I can say that it is not used so far. But can be used depends on the etching technologies and all. Because the diamond etching itself is a very challenging, because people are trying to reduce the temperature in two ways, from the top and from the bottom. I mentioned in the few earlier slides, from the top, like in place of the silicon nitride passivation. So people also use the diamond, CVD diamond deposition. But what happens in the high temperature CVD diamond deposition around 800 degrees C, it degrades the 2DG performance of the device. So what we can, because performance is degraded, so we cannot go for this one directly. Or in case somehow it is protected, then etching the diamond and putting the gate or this technology itself like degrades the device performances. So there are a couple of cooling, even in microfluids, they can use it, but currently it's not used so far in the diamond, as I know. Yeah.
Okay, sir. Thank you. Thank you very much, sir, for your nice talk. Yeah.
Dr. Manish, I am Ashok Kapoor from IIT Delhi.
Yes, sir.
Yes, sir.
My question is that what is the growth temperature for this CVD grown diamond, and what are the effects of this growth on the already grown hem structure?
Yes. So conventionally, it is 800 degrees C, because now a few technologies are coming in the low temperature growth. But when we use the 800 degrees C, then we observe that the 2DG degradations. Directly when we grown from the like on the GAN structure from the top, it's 800 degrees C. Then in the blanket, and there is no device process, once we grow, after growing, we observe that the mobility degradation is there. So this is one. Second, when the device was fabricated, then like ohmic already fabricated, gate was there, and then diamond was deposited. Then it's completely degraded because the ohmic contact couldn't sustain that the high temperature. Then the third steps, like even the very thin layer of the silicon nitride, first device was protected, very thin layer. And then after that, the CVD diamond deposition was done. Then, okay, then also it was degraded, but it's not like that. So there are a couple of stages, but still this is a research is going on. Means we cannot say very clearly that because optimization is going on currently in even NTU. Like
yeah, that's what I was thinking.
Yes,
so, but
yeah.
why I asked this question is that I did not see any degradation when you compare your diamond devices with the silicon devices.
That was bonded actually. That's not grown. That's a complete diamond. It's a CVD diamond. Yeah, it's a lap down, the silicon substrate, and then after that, it's bonded with the adhesion layer. So there is no deposition at that time. So that's that's why there is no degradation.
Okay. Thank you very much.
Yeah, welcome.
Doctor, more question, last question, I think. Thickness of the diamond cap when used as a passivation. What is the thickness of the diamond cap?
See, it depends on, because for the silicon nitride, okay, we use even 40 nanometer to even 120 nanometer. This is conventionally. For the diamond, because the grain size and all, it was not optimized. So initially, okay, we thought it's a 200 nanometer, but we didn't see the uniformity over the across the entire wafer, even in the entire 1 inch by 1 inch. But conventionally, we can say that, okay, once you increase the thickness, of course, the heat dissipation will be better. So, but the second thing is the degradation of the device. So it's optimization. So, silicon nitride is is good enough even for the 20 nanometer, but in the diamond, it's the optimization part actually. So we can say it's a 50 nanometer or even 60 or even 100 nanometer, but it's not so far. It's because that technique we couldn't achieve the results. That's why we couldn't publish or anything. We couldn't present the results of that.
Thank you, sir. I think we are running out of time. I really want to thank you to enlighten us on the different, comparison of the different GaN HAMT devices for the RF, L, C, and S band and W band kind of application, where you have clearly, mentioned about the GaN HAMT technology for RF application is much suited on the diamond or silicon carbide. This is a very good presentation and enlightening one, sir. Thank you very much.
Thanks.
I'm sorry that I am not able to, read your bio because of the paucity of the time initially. Let me briefly introduce our speaker. Dr. Ranjan has done his PhD from NTU Singapore, and he is basically an electronic engineer and having a research experience of 15 plus years in the microelectronics on GaN and based HAMT SBD devices and devices for RF millimeter wave MMIC subsystem for space and defense application. He has a work experience of more than 15 years, and he worked as a research scientist at TEMSEC laboratory, NTU Singapore, from 2012 to 2020. He worked on the process integration of GaN HAMT, silicon carbide CVD diamonds for 150 nanometer and 250 nanometer technology and HAMT project, developed via hole etching technology on GaN HAMT on silicon carbide substrate, device parameter extraction, etc. Prior to that, he has worked as a senior research fellow at IIT Kharagpur in India. He has received various recognition and award, with the Best Application Award for the year of 2014 for High Johnson and Figure of Merit of terahertz worth in 0.15 micrometer conventional T-gate L-GaN GaN HAMT on silicon, and reported in GaN RF market analysis article on Semiconductor Today's. He has several publications on his back, and he has a very wide experience in this. He has worked as a scientist and at DRDO SSPL from 2004 to 2008. Thank you, Ranjan sir, for enlightening us on this topic. Thank you very much.
Thanks, sir. Thank you very much.
Now we have in this session another talk from Dr. D. Krishnamurthy on substrate technology, epitaxial technology, and device processing. Dr. Krishnamurthy is one of my closest friends and known to me also. And Dr. Krishnamurthy has PhD at Crystal Growth Center, Anna University, and learned the bulk growth of oxide crystal. He has more than 17 years of research experience in Japan, working on Shizuoka University, Furukawa Electric Company, Osaka Gas Company, Osaka University, and NICT. He has a process hands-on experience in bulk growth, epitaxial growth, device fabrication, characterization, and speaking and packaging. He is a member of pioneering group of gallium oxide power devices and NICT Japan. At present, owns a company of Shan Innovotech Venture and serves as the scientific consultant for 5 Japanese companies: Novel Crystal Technology, Inclusive, Ulvec, Hiba, Entity 80, and ECO. Act as a bridging between India research and Japanese companies, catering to the research need of Indian research. Yes, over to you, sir, Dr. Krishnamurthy.
Thank you, sir. Thank you.
Yes, sir, you are audible. Your screen is also, yeah. Can you switch it to the full mode, sir?
What about now?
It is okay, sir. It is okay, sir.
Okay. I really thank the chairman of this session, Dr. Huda, for introducing me, and also Professor Rajendra Singh for giving me this opportunity to present this conference. I think Professor Kare and Rajendra Singh have opened a Pandora box of successfully organizing this virtual conference, and it's so successful it is. Probably slowly, we all will be very encouraged to attend this kind of conferences so that our time and also our cost is also very much premiumly available. Okay, at that, I would like to also see that wideband semiconductor symposiums are getting more and more prominence in India. And I'm happy that a combination of silicon carbide, gallium nitride, gallium oxide has been put forth by Professor Rajendra Singh. And it was heartening to note that Dr. Digvijay, who presented the results on the NTT Advanced Technologies wafers, based using the GaN M2 wafers, he could get very good results. So I'm hopeful that Professor Vasu's efforts and other efforts will lead us to some kind of foundry so that we are again trying all our push towards the wideband semiconductor harnessing the effect of them. Okay, with that, I would like to introduce this gallium oxide material for the August audience here. And I would like to give a briefing about the activities at Novel Crystal Technology Company, the pioneering company for this beta gallium oxide technology. And the outline of my talk is, I would like to give us starting with the proprietary properties and applications of the beta gallium oxide material, followed by the status of the development of this material, what kind of a substrate technology is being done, epitaxial technology and device processing. And I would like to show some of the results carried out by this company in the device sector, and I would like to summarize followed by that. Actually, as most of the people who are working in the gallium oxide would know, this is a very surprising and happy to work with material, which is having a 5 poly types, alpha, beta, gamma, and epsilon. In that, the beta gallium oxide is the most stable one, and it has extremely large band gap. So we can usually, instead of telling it as a wideband material, we can even say as ultra wideband material, which have between 4.5 to 4.9 electron volt is the band gap for that. And well, the advantage of this material seems to be that the entire conductivity can be controlled in a wide range, and more importantly, there is easy method of growth of this single crystal by melt growth. So frankly speaking, until and otherwise people get this beta gallium oxide substrate or bulk crystal, the research on that was not that much effective. but slowly it has picked up. The main reason for that is the properties. As you can see, as you compare let me just take my pen. So here we can see that as compared to silicon, what are the features of the beta gallium oxide as regards the power device? Here we can see the figure of merit, which is supposed to be the, of course, the Baligas figure of merit, giant Baligas, India's person's figure of merit, which explains the suitability of any material over the power devices. And we can see it is very high due to the higher band gap and electrical field strength. Though the mobility is low, still these two higher values gives you higher figure of merit. And also, as this figure is very familiar to the people here, you can see it is better than the gallium nitride to silicon carbide. So frankly, the point of interest for the people working on gallium oxide is this. It can be used as a MOSFET, a Schottky diode, HEMT structures, of course, in the optical devices also, finding applications in railway types, renewable energy, smart grids, and even in the extreme environment devices like gas turbines, nuclear reactors, space applications. And so when you compare with the gallium nitride and silicon carbide technology, this beta gallium oxide is good at the medium frequency range, but more importantly, at the higher voltage, there is no competition at all for this. Though it can do this, perform similar to silicon carbide, but in the higher voltage side, this application is incomparable. And also, you can see in coming slides, you can see the cost effectiveness of beta gallium oxide because of the comparatively cheaper substrate price gives is much more advantage. As we all know, as compared to silicon, all the other three materials are competing with silicon. But still, silicon is doing very well because of the low cost effectiveness. So, in order to compete with silicon carbide has to outperform, and it is outperforming, unfortunately, with a premium cost. And you will be seeing inherently the growth method gives us an advantage for the beta gallium oxide. Actually, what is the advantage of this beta gallium oxide in overall perspective? Let us forget about we are a scientist, but we are thinking about human being. You can see that basically this gallium oxide, development of this beta gallium oxide in the power sector will lead to low power consumption, which will the energy saving, which will be estimated kind of 10 million kilowatt by the year of 2015, which is equivalent to that produced by 10 nuclear power plants. And of course, this is the catchiness. The low power consumption of beta gallium oxide is the driving force behind any research. And it has already started up a very good industry in the power electronics industries, and people are expecting in the medical field, in space business and electrification of aircraft, this can play a major role. And so now I will keep on telling that this is a cheaper, this is an easier method. What is that? Basically, any growth method, any crystal which is grown by melt growth is supposed to be the easier one and also cost effective. And luckily, yes, this material we can grow by melt growth by 4 different types of melt growth, like the float zone, vertical bridgman, Zugralski, and age-defined film bed growth. And as you can see, the comparison of these 4, in that 4, age-defined film bed growth is much more advantageous, mainly because of this growth rate. As you can see, it is comparable only with the float zone. BB and Zugralski, still the growth rate is low, but as you can see, the growth rate is comparable or 3 times than the floating zone. But more importantly, we have 1 inch maximum. See, in India, already we have people working in various laboratories having successfully grown zone, grown the gallium oxide by the floating zone technology. But unfortunately, the size has been restricted and maximum has been reported to be 1 inch only. But here, 6 inch has been reported by this method, and mainly because of this higher growth rate, the cost will be reduced, as we can see lower. Okay, so all this thing was possible. The effect of this gallium oxide, the application of this gallium oxide in various fields, the research on that, and all happened because of this company, which has been carved out venture of the Tamura, the basic company, wherein in the year around 2012, they could successfully grow gallium oxide bulk crystal. And now this company has evolved into not only bulk crystal growth, but bulk crystal growth and other activities, which I'll be talking in my coming slides. So basically, as I was telling you, it's an age-defined film-fed growth. So it's probably in the near future, India might also consider developing its own growth technology here. So I would like to spend a little bit more time on this particular growth method. So as you can see, it is the material of gallium oxide placed in the iridium crucible will be heated by the RF coil. Here, you will have a die which will be having a slit in between. So because of the viscosity, the molten material will rise through this capillary and it will make a film in this top. Once you touch your seed crystal to it, crystallization starts, and pulling it up will effectively increase the size of the crystal. And as you can see, the shape of the material is defined by the die size. So usually a rectangular shape die size is selected, and it is effectively the technology by this Novel Crystal Technology Corporation is in developing this growth setup. And so it was not by them, but it was a combination of and Koha and company that resulted in a 2-inch wafer, 2-inch bulk growth, followed by much more R&D, and now they reached a capacity of 6-inch bulk crystal growth possibility. Now, this is a general outlook of a age-defined film fill coat EFG growth setup. Now, why this melt growth is giving this advantage? As you can see, silicon carbide or gallium nitride, because of its constituent elements, cannot be grown by melt growth. It can be grown only by the wafer-based growth method, like mostly sublimation method. You make a wafer of silicon carbide or gallium nitride, and then you make them by sublimation, and then you make them to cool or get deposited over the seed crystal. So effectively, the growth rate will be very low, 0.1 millimeter per hour. But here you can see it's a melt growth method wherein the growth rate is now it is 3 centimeter per hour. And more importantly, what about the material? See, the hardness of silicon carbide is extremely hard. Therefore, the usage of it, the cutting, polishing, all those things is going to be cost. It's going to cost you. But also, handling is also going to be a little bit easier for you. But at the same time, for the case of device fabrication, tough. You don't need a brittle element, but you need some kind of a moderate in between both of them. And this perfectly suits. It's not that much hard. At the same time, it won't get healed so easily. And also, that means, and one more, what about the wafer processing? As we know, silicon carbide requires special equipment, but we don't need a special equipment. A general equipment is sufficient for metal gallium oxide. So the development of this silicon carbide, let us compare how the technologies are evolving. You know, silicon carbide started in the year of around 1998, and it required at least some 20 years for it to reach the 8-inch. But here, it requires around 6 years only, or 6 to 8 years only for this technology, gallium oxide technology, to reach the 6-inch stage. Now, right now, we are in the we have the capability of 6-inch, but because there is no takers, we have not yet released it commercially. But the reason behind such an easy evaluation goes back to the growth method itself. As I told, this is the growth diameter, and so the moment the RF coil is made in such a way that your crucible size, enhanced crucible size, holds that much amount of material, and the die change to that much kind of an 8 or 10 inch, then obviously the growth technology has to evolve a little bit more only as compared to the other growth technology. Here, the growth, increasing the growth size diameter is a bit more complicated as compared to this growth method. So it is essentially not because of the material, it is because of the material's growth method, which is adaptability, gives the advantages for the weaker gallium oxide. And for your kind information, silicon is something which is evolved because of that melt growth possibility. Now, so what about the cost? I think some of the researchers working who are already working in gallium oxide might not agree with me right now, but it is the early stage, because not only researchers like Professor Rajendra Singh and Professor Vijay and other people are using it. No industry takers have yet come. But once industry takers are coming in, it's going to be much cheaper than the silicon carbide. And this is the silicon carbide rate as compared to the rates of prices of beta gallium oxide according to the sizes. And I'm very hopeful that the prices definitely come down in the coming years, and we are going to have much more research and, of course, development activity on the gallium oxide. So this is for us to have a feel of how will be the bulk crystal. So this is a 4-inch bulk crystal, rectangular one, and it is a 2-inch rectangular one. And as I told you, 6-inch is already grown, and we have the capability, but we are it will be coming out as and when the researchers require that. Now, the important point here is, as I told, and the only production of the epitaxial of the substrate. So it has evolved into both production of the substrate, bulk crystal, substrates, and so on, as you can see here. So the production flow done by this company is, it makes the sample and then cuts it into rectangular blocks and anneal it, and followed by slicing into rectangular slices, and then coring, making it to circular, and then anneal it, start the lapping and polishing, and finally inspecting again, and it will be wet cleaned to give the substrates. So this is the substrate part. So like this, from the bulk crystal to substrate, it is evolved by the company in capability. And usually, an important question will come to researchers working in the field. Going from 2-inch to 4-inch to 6-inch, 8-inch, as the temperature, diameter increases, it always leads to deterioration of quality of substrate. But here, because of the good adaptation of growth methodology, we can see that the growth resulted in better characteristics. As you can see, the full width half maximum in the XRD working curves, you can see that it's between 23 to 68 arcsecond in this 2-inch wafer. But in the case of a 4-inch substrates, it's still less, it is 28 to 34 arcsecond. So that shows that as it is increasing, because of some better thermal management, we could get better substrate quality. And the results which we have until now reported are mainly due to the 2-inch substrates, and we are very hopeful that with this enhanced characteristics of the 4-inch substrates, the results are going to be, the scientific results are much more going to be heartening to the research community.
Professor Murthy.
Yes.
Sir, we have a paucity of the time. We have a common lecture from 6 to 7 p.m. which is common for all the CN. Can you quickly wind it up, sir?
Okay, I think you have given me about 15 minutes. Okay, anyhow, let me proceed. Okay, so now, as I told you, shall I have 5 minutes? Okay, so there will be MBE group technology is there, and we could get the epitaxial layer has to be obtained. For that, there are two methods, MBE, and I can say we are combining with Alvac company to make such kind of a water-cooled MBE to produce the epitaxial layers, and this is the system supplied by us to the NUS. But now, basically, HVP is the one which is giving a very good result, and this is set up by us. And
so, Dr. Krishnamurthy, sorry for interruption. Yes. Actually, yeah, it's for Dr. Manish Huda also. I just want to tell that we have to start actually our evening lecture, and Professor Venkatesan is waiting for that one. So can you finish within few minutes, 5 minutes or so, and then we will switch over to that one.
Yes, I'll take only 5 minutes. I will just
okay. Thank you, Dr. Manish Huda.
Okay. So basically, as I told you, we are able to have a 4-inch device process wafer, as you can see here, and this company, we could make devices, power devices, and to start with, it is the trench diodes. The characteristics are, as you can see, for the same lower leakage level as compared to silicon carbide and 2/3 of commercially available silicon carbide MOS SBDs, the forward voltage is lower by 30 to 40%. That is the first encouraging results I want to represent. And secondly, this material, as I told you, a conventional HVPE is giving a lot of issues because of the device killing defects. And by improving our growth methodology, we could get the eradication of all these device killing defects. And because of this improved epilayer, we could get very good characteristics of the results of the SBDs. And using these wafers and combination with Cornell University, we could get a first 1230 volts beta gallium oxide trench Schottky barrier diode with a very ultra low leakage current of less than 1 microampere per centimeter square. And of course, we also ventured upon MOSFETs. This is the in-house MOSFET fabricated at NCT, but in combination, it shows very good on-off ratio and current voltage characteristics, transfer characteristics. And this is an important slide. In combination with Cornell University, we could employ our HVP grown epilayer to get an enhanced mode vertical transistor based on gallium oxide with a breakdown voltage of greater than 1 kilovolt. And this will be my last slide. And you can see recently we have reported a breakdown voltage of over 2.6 kilovolt for the normally off gallium oxide vertical transistors. So in conclusion, I would like to say that we are the only manufacturers in the world who are supplying large and high quality beta gallium oxide single substrates and also high purity beta gallium oxide epitaxial layers. And we have already started development of the SBDs and effects for demonstration purposes. And this is the important thing. We are interested in to collaborate with public institutes. Unfortunately, now the institutes are asked to buy wafers, but once the results are very encouraging, we can start the collaboration as we have done with the Cornell University and other universities. I thank this opportunity given by Professor Rajan Singh, and I don't think I have time for any questions. Anyhow, it's up to you, Dr. Muda and Dr. Singh.
Thank you, sir. Thank you for a nice enlightened talk on the substrate technology, epitaxial technology, and telling us about the future of beta gallium oxide as for the power semiconductors technology. Thank you, sir. Thank you very much. It's over to you, sir. Rajendra, sir.
Okay. So thank you, Dr. Manish Huda, for chairing this session, and also thanks to both the speakers of this session. So now we close this session of this wide bandgap semiconductors. Thank you all.
Yeah, so now we are going to start this evening lecture of today's synthesis.
Wide bandgap semiconductors. The poster session we would like to continue. So, Dr. Monu Sharma, poster number 3. Or Ms. Minal Rajesh Gupta, Mrs. Barnali Patak. Okay, then we'll move 29. Mr. Anil Yadav.
Yes, sir. Am I audible?
Yes, yes, you are audible.
Yes, sir.
Uh,
Sir, can you share my poster,
yes,
sir?
we are doing it. We are just doing it.
Sir, am I audible? Minal Gupta?
Minal Rajesh Gupta, row 4. Yes, you are audible.
Okay, sir. Actually, my microphone was not working. That's why I'm not audible that time.
Okay. Okay. Do you have just a moment, please? Yes, Minal Gupta.
Yes, sir.
Please go ahead. You have only 1 minute left.
Okay. Good evening, all of you. So I am directly coming to the conclusion of this poster. I have substituted La in CO2, which shows wide gap. Remarkable change in the band gap. Like I am substituting 5% La, so it shows a band gap of 3.15 electron volt. Further, up to the substitution of 20%, decrement in the band gap has been found. Further doping, further substitution like of 50%, again band gap is increasing. So this non-uniform behavior of band gap is because of the decreasing particle size as shown in the SEM images, and also due to the presence of oxygen vacancies which were created due to the ionic and oxidation state mismatch of La3 plus and Ce4 plus ions and Ce3 plus defect levels. Thank you.
Thank you, Minal Gupta.
Okay, sir. Thank you.
Yeah. Next, Mrs. Banali Patak is there. Okay, we are just moving to question number 29. Mr. Anil Yadav, you have 1 minute. Just go for the final conclusions.
Okay, sir. Sir. Okay. Um, yes, sir. Sir, here I have deposited silver nanoparticles over zinc oxide nanostructures, and as zinc oxide has high exciton binding energy because of 60 milli electron volts. Because of that, uh, because of that, the recombination rate of electron hole pairs is very high. So the efficiency for the device photo detector is less. So I have deposited silver nanoparticles, and uh, because of that at the interface of silver and zinc oxide, there is an high built-in electric field, and the charge separation, and because of that, there is a very good charge separation, and hence the efficiency of the device has been increased. And in the conclusion, as we can see there, the NB near band emission of the PL has been suppressed, which indicates a good charge, which indicates a good charge separation. As the electrons are transferring from the conduction band of the ZNO to the silver nanoparticles. And also, as we can see an additional peak in the absorption spectra, we are getting, and this is due to the LSPR of silver nanoparticles, and and the sensitivity of the device has been increased from 7.9 to 38.4, and also the responsivity of the device has been improved by more than 30 times. Thank you, sir.
Thank you. We are moving to Mrs. Mansi Agarwal.
Good evening, everyone. I hope I am audible.
Yes, you are audible. We are just.
Okay, sir. So my poster number is 32. Yes. So good evening,
Please
everyone.
go
In
ahead
this
for your
work,
conclusions.
yes, sir. In this work, we have reported on the plasma-assisted MB grown gallium nitride nanowires on silicon 211 substrates for UV sensing applications. So we have utilized a high index silicon, as it consists of two planes, silicon 111 and silicon 00 planes. And so both the planes could be provided for the growth of gallium nitride nanowires. In this case, the nanowires were grown by MB system, as using MB we can grow catalyst free gallium nitride nanowires. So this is the advantage of the growing the nanowires by MB system. So the FESM images are shown in this figure. So first we have nitridated the silicon substrate. So we can see in the three images the effect of nitridation time on the silicon substrate. So as we increase the nitridation time from 1 minute to 15 minutes, we can see the distance between the ledges increases and the substrate gets nano patterned. And on then we chose a sample for which the nitridation time was taken as 15 minutes, and the gallium nitride nanowires were grown on that substrate. So the second image shows the growth of gallium nitride nanowires on the substrate, and we can see that the nanowires are oriented at 70 degree with respect to the substrate, as they as they are growing, as it has been reported that the nanowires grow perpendicular to silicon 111 planes, and silicon 211 planes consists of surface consists of mainly two planes, silicon 111 and silicon 100 planes. So using this fact, we could grow the nanowires at a preferential orientation. And secondly, we have performed the photoluminescence spectroscopy measurements, and we observed a peak at 3.42 electron volts, which corresponds to gallium nitride band edge emission, and no other peak was observed in our measurement. So it indicated that the nanowires had a very high optical quality. Then we performed HR-XRD measurements to measure the tilt in the nanowires. We performed X-ray pole figure measurements. So for gallium nitride 002 reflection, we observed that only one maximum intensity spot was observed in the pole figure measurement, which was corresponding to 18-degree tilt. So we can conclude from that result that the nanowires grow on the silicon 111 terraces. Then we performed UV measurements, UV sensing measurements on the nanowires. For that, we measured resistance as a function of time. So the response, as we switched on the UV, we found that the resistance increases.
We are just moving to 35.
So, excuse me, sir. Poster number 33.
33, you are there?
Yes,
Dr.
sir.
Rohit Singh?
Yes, sir. I'm Kiran Ji, sir.
33 crystallographic parameters and ordering in MGZNO alloys and AB initio study.
Yes,
Okay, please go ahead. You can directly go for conclusions for a minute.
okay, sir. Good evening, all. Today I'm going to talk about the crystallographic parameter and ordering in MGZNO alloy AB initio study. And in this work, the crystal structure properties of Woodside MGZNO semiconductor ternary alloys has been investigated using the DFT, that's density functional theory, full potential linear augmented plane wave, local orbital formalism, and here we have used the PBE method for the exchange correlation. The objective of this contribution is to understand the volume optimizations using the 2D optimization technique, which are available in the Y2K core, and we calculate the best value of the C by A as well as the energy of with respect to the volume. And thereafter, we just use this
Dr.
structure file
Rohit,
for the.
sorry to interrupt you.
Yes, sir.
Sorry to interrupt you. Your poster is not with us.
Sir, I could see.
Can
sir. Yes, sir. This only.
Okay. This one.
Yes, sir.
You can go ahead.
Okay, sir. So thereafter, we just take the structure file for the calculations of the material properties like electrical or optical properties. And if we talk about the full potential linear augmented plane wave and local orbiter method, and which is mainly used for DFT purpose, and this electron system ground state physical properties are accurately described by the GGA PBE. Exchange correlations will be available in the V2K code. Those are LDA as well as the GGA. And in the GGA, of course, we have four more methods, which are PBE and Hunkon and PBE Sol and TB modified Bekke-Jansen. But we are going for the PBE method, and which is very well suitable for the structural calculations. And if I talk about the wideband 2 and 6 semiconductor materials, these are very good material for electronics and optoelectronics, and these are
Can you go for
mainly due to.
conclusions, please?
Yes, sir. Yes, sir. And if I talk about the conclusion, the V2K code is a very high accurate code, and to calculate the material properties by using the FT, LA, PW, LO method. And this work have performed the optimizations of the volume performance of V2K core, and we reported the calculations of optimized energy versus of the volume graphs. And the optimized structural details can be used for further calculations, as I said, like electrical and the optical properties of MGZ. Thank you.
Thank you. Thank you. We are moving to 34 now. Mrs. Naina Ramesh.
Yeah, hello.
You are
I'm
audible,
audible?
and please
Yeah.
for conclusions in a minute.
Okay. You will share my poster, right? Or should I start? Hello?
Just a moment, we are showing your post.
Yeah, okay. Yeah, what I have done in this is we all know that when we are doing carbon doping, we could reduce the leakage current in GAN because of compensating the unintentional doping. But the issue here is when we introduce carbon, it will also it will also leads to current collapse. So what we have tried here is we introduce carbon in the 25% algan also so that it will reduce the current collapse in the sample. So you can see here we have tried sample A and sample B. In sample A only buffer is carbon doped, but in case of sample B, 25% algan is also carbon doped, and which will lead to an improvement in the vertical breakdown, lateral breakdown, and also in the three-terminal breakdown, which is given in figure 3A, B, and C. And also then we try to do some substrate sweeping measurement where we have observed that when we are having a 25% alkane carbon doped, the current collapse had decreased, and we could actually achieve a 89% channel recovery in the case of sample with 25% alkane carbon doped. Yeah, that is the conclusion of my paper. Thank you.
Thank you very much. Then we are moving to Mr. Faryanshu Kachawa. Are you there? You are
Yes, sir.
audible.
Am I
And
audible
go
now?
ahead for a minute.
Am I audible now, sir?
Yes, you are audible.
Okay. So in this paper, we have fabricated a gallium nitride based high electron mobility transistor, in which we have taken a GaN cap layer of 2 nanometer to reduce traps, and in situ passivation of silicon nitride of 50 nanometer has been done. So by optimizing this contact resistance, we have used a good contact resistance of 2.5 and 10⁻⁶ ohm centimeter square, and we have optimized the isolation resistance using ion implantation by using boron, nitrogen, and argon, and we have achieved a very good isolation resistance of 46 gigaohm per square. And while after fabrication, we have achieved a current density of 580 milliampere per mm for a gate voltage of 2 volt. And we have done Hall effect measurements also, in which we have shown 2 DAG carrier concentration of mobility of 1670 centimeters square per volt second, and 3-terminal breakdown also we have achieved. So we have got a depletion mode device, in which one we are just observing a more than 200 volt breakdown voltage, which is not yet it's breaking down. So we are in the future we are just hunting for the outsourcing of this characterization system, in which we are hoping that it can go for up to 650 volt or so. So in this regard, we are just searching for that outsourcing for proper characterization of our HMT. Thank you, sir.
Thank you. We are moving to next question number 36, Mr. Prabhan Tiwari.
Hello.
Yeah, you are audible, and you can go ahead now.
Okay, so in this work, we have used a high-K dielectric niobium oxide deposited by thermal ALD to demonstrate a niobium oxide beta gallium oxide heterojunction diode to overcome the problem of high tunneling leakage in beta gallium oxide Schottky diodes. So as we can see in the 2D electric field plot done by TCAD simulations, we can see that the heterojunction diode shows 5x reduction in field near the metal compared to the Schottky diode, and this results in a wider barrier for the electrons to tunnel. So we observe a 2.3 times improvement in reverse blocking voltage for the heterojunction diode. A numerical reverse leakage model based on WKB tunneling probability has been used to simulate the tunneling leakage as a function of barrier height, and the forward characteristics have been fitted with the thermionic emission model. Thank you.
Thank you, Prabhans. We are moving to 37 now. Mrs. Kanika Arora.
Hello, I'm audible.
You're audible now. You just go ahead for your conclusions for a minute.
Okay, can you share my post?
सॉक्स नीचे रखे हैं शायद.
do you have your own poster? Because we do not have your poster right now. Can you share it?
Yeah, I can share. Hello.
Yes, yes.
Are you able to see my poster right now?
Please share it.
Okay.
If you cannot do it, you send the PDF file to us. We'll share it at the end.
Yes, I have shared with you in mail also. A second. Just a second.
Miss Kanika
Hello.
Arora, are you able to see now?
Yes. Are you able to see my
Please go
poster
ahead
now?
for a minute. Direct conclusions.
Okay, so I'll conclude my talk. So here we report a facile and unique hand sketch bottom asymmetric pencil drawn graphite and silver electrode based disposable, eco-sustainable, lightweight, ultra flexible and cost effective paper based gallium oxide thin film photo detector. We have used the deep UV transparent enamel paint to make it water resistant.
Hello.
So, hello. Yes.
Chanchal, can you mute yourself, please?
So to
Yes,
best of
Kanika,
our
go ahead.
knowledge, yes. So to best of our knowledge, this is the first report on paper substrate based photo detector with a unique hand sketch asymmetric bottom electrodes, not even on the gallium oxide base, but with any optoelectronic device. Because of this unique feature of asymmetric bottom electrodes, we obtain a self-powered features, and we have got a very interesting results, very low dark current of 1.2 picoamps, large on-off ratio of more than 10 to the power 4, and high photo response in milliampere per watt, and very fast response time in milliseconds. So here I have compared the figure of merits with the other existing reports on rigid substrates as well in self-powered mode. And to our surprise, we have achieved a far superior performance because of these bottom asymmetric electrodes instead of that PN junctions, which limits the light correction. So at most important, we have done the rigorous flexibility test at various bending curvatures, as you can see from these figures, 12 centimeter, 20 centimeter and 30 centimeter. And we have done the intensive twisting angles plus minus 180 degree, which reveal the high reliable performance even after experiencing 100 twists under extreme deformation of sequential bending and twisting. We have reported the exceptionally stable operation even after 72 hours kept in a lab environment, in ambient environment. Along with that, we have obtained much enhanced performance with the tremendous capability of bearing a high voltage up to
Can you
100
please
volts
conclude
required.
it?
Yes, so so we coated the device with the UV enamel paint to make it completely protective over wettability, and the measurement reveals that the water impinging in bare device in terms of decreasing contact angle with time, while there is no significant change in the angle with enamel paint indicating high degree of hydrophobicity. So our
Thank
work
you.
is
Thank
in
you.
conclusive device symmetry
Thank
for the
you.
development.
Thank you.
Okay. Thank you.
We are moving to person number 38, Mr. Ravi Kiran Lingare.
Yeah, hello, sir.
You are audible and go for a minute, please. Just directly go for your conclusions.
Yeah, sure, sir. So in this work, we optimized the trench EMI Schottky diode based on the beta gallium oxide by the TCAD simulations. So the in EMI trench diode, we we get the leakage, improved leakage by the resurf effect, which means the reduced surface field. So after getting over the leakage, the main limitation for this diode becomes the field at the corners. So to manage the field at the trench corners, we propose two methods. One is the beveling of the corner, and another one is the rounding of the corner. So observing the field in this at the corners, we found that the field is minimum for the angle of 25 in the case of bevel, and the uh, and in the round corner case, for the radius of zero point 0.5 and greater, the field is optimum. So after optimizing device for these fields, we found that the actual breakdown is limited by the breakdown in the dielectrics. So for that, we propose the bilayer dielectric consisting of the high K and low K. In this case, HO4 and Al2O3. So bilayer enabled managing field in the dielectric, and which improved the figure of merit and breakdown voltage. Yeah, so yeah, this is the conclusion of my work.
Thank you very much. And we are moving to Mr. Rizzo Baby. Otherwise, post number 40, Mr. Suryavansh Upadhyay.
Hello, am I audible? It's Suryanshu.
Yes. You have 1 minute for your conclusions. Please go ahead now.
Okay, so good evening, everyone. In this work, I'm reporting a breakdown voltage of 500 volts at ID around 1 microamps per mm for a 100 micron Elgan hemp with a gate drain spacing of 9 microns. And also for a large area device, that is the 50 mm gate width, I'm reporting around 9 amps of on current and a 100 volt breakdown. High breakdown voltages here were achieved using an integrated gate field structure, and the process was optimized to reduce gate leakages, off current leakages, and MESA to MESA leakages for the small and big area devices as well. There's also a comparison between gate leakage current for the smaller area devices as well as big area devices presented in the poster. The device structure, basically for the 50 mm device, I have 51 mm interdigitated fingers with a source drain spacing of 17 microns each. So with this, I'll conclude, and the future work aims for the development of a 15 amp 650 volt Elgan hemp for power applications. Thank you.
Thank you. And we are moving to 41, Mr. Rajiv Ranjan Thakur.
Yes, sir. Am I audible, sir?
Yeah, you're audible, and you
Yes,
just
sir.
go for your conclusions straight away.
Okay, sir. Good evening, everyone. We know like nanostructures have been the one of the emerging structures for the MOSFET applications, right? So in this paper, we are reporting like this the currently emerging nanowire based FET, in which over the time it has been scaled up to ITRS report. But channel material is a crucial parameter that need to be taken care. So here we are comparing 3 different materials like silicon, which is the backbone of the industry till now, and GaN and ZNO. So what we have achieved is like there has been a reductions of around 47.42% in the sub-threshold swing, which is one of the bottleneck to be considered while designing the FET. And there are reductions of 23.75% in DIPL, which is another parameter which need to be taken care while seeing the digital applications. So the conclusion clearly shows that like if we integrate this GaN with this particular structure, which is a non-planar structure, so there will be a very good performance, and this can act as a integrated amalgamation of these two will act as a very good switch, and this will allow for the next generation digital application. It will be a very good combination. So we have done the performance comparison of these three materials to just analyze the performance for the digital switches. So that's what I conclude.
Thank you very much, Rajiv Ranjan.
Thank you, sir.
And we are moving to
Yes,
Mr. Prashant.
Okay.
Mr. Prashant Kumar. Mr. Maruti Jalte. Post number 44.
Yes, sir. Maruti Jalte, sir, here.
Maruti Jalte, you have 1 minute to go for your final conclusions. Please go ahead.
Yes, sir. So in this work, we have reported amorphous indium gallium zinc oxide thin film transistors, which are fabricated using low-cost solution processing. And we integrated this thin film transistor for sensing of toxic hydrogen sulfide gas. And we have showed the limit of detection of 8 parts per million. So we have, if you see in the poster, the IV characteristic, wherein there is an increase of drain current of around 8 times as you increase the concentration of the gas from 0 parts per million to 32 parts per million. And also there is a negative shift of the threshold voltage. So these two parameters and quite low voltages of biasing of 2 volt, we can get the sensitivity of 36 microampere parts per million to 4 in terms of drain current, and 40 millivolts per parts per million in terms of threshold voltage shift. And interesting thing is this sensor, like this transistor, showed the recovery after annealing it at after exposure to H2S at 150 degrees Celsius for 1 hour. So the recovery data is also suggested that it's almost come back to the recovery of its original characteristic. So that's all from my side. Thank you.
Thank you. Thank you very much. And we are moving to the next talk, Mr. Abhinav Pratap Singh. Abhinav Pratap Singh, or post number 45, Mr. Sajish VZ. Okay, we are moving to Miss Chanchal, 22, post number 22.
Hello, sir, I'm audible.
Yeah, you are audible, and can have your talk for 1 minute for direct conclusions.
Okay, sir. In this study, we have introduced helium gas to SF6O2 chemistry, gas chemistry for the SiC via hole etching for high power application of the Ganham MMICs.
Chanchal, just wait for a moment, please. We are displaying your poster. Just wait for a minute. Yeah.
This is mine. Okay. Hello. Hello.
Let's go for it.
In this work, we have added the helium gas to etching for the wire hole SiC etching for high frequency power amplifier for as again MMICs. Wire hole etching is the important for the reduce the connection through the ground of the wafer. And this is because of the air bridges introduces the inductance and which affect our frequency response. That's why we are using via hole etching. Including the helium to the SF6O2 chemistry is the best part is that we have etched achieve the high etch rates, smooth sidewalls of our wires, and observe the less micromasking and trenching and good electrical connectivity after the fabrication of the wire hole. Thank you, sir.
Thank you very much, Chanchal. Anybody is there who has to present their presentation poster? Please let us. We are just concluding things. I assume no one is there to present. We are just concluding the session now. Thank you very much. We are concluding it. Thank you all.